Sí, prueba de audio. Uno, 2, 3. ¿Nos podrían confirmar si nos escuchan en... Da un segundo. Sí, prueba de audio. Uno, 2, 3. Es una prueba de audio para los que están conectados en línea. Confirmar si nos escuchan.
Sí, sí los escuchamos.
Muchas gracias.
Sí, por nada.
también el láser. Ya quedó. Si quieres, déjalo en el estrado.
A continuación se dará. A continuación se darán unas breves indicaciones sobre medidas de emergencia ante alguna eventualidad en este recinto. Usted se encuentra en el Auditorio José Luis Sánchez Bribiesca, ubicado en el sótano de la Torre de Ingeniería. En caso de emergencia, le suplicamos que mantenga la calma y, de ser necesario, desaloje el salón de manera ordenada. Siga los señalamientos de evacuación que se encuentran ubicados en los pasillos laterales con dirección al lobby. Las puertas de emergencia están ubicadas al lado izquierdo y derecho de los elevadores y abren hacia afuera con la barra de pánico. Solo deben abrirse en caso de emergencia. Si llegara a ocurrir un incendio, el salón cuenta con 4 extintores, 2 al frente y 2 a las salidas, y las alarmas se encuentran en los pasillos laterales. Durante el desalojo del inmueble, el personal de la Comisión Local de Seguridad de la Torre de Ingeniería dará las indicaciones pertinentes. El punto de reunión se encuentra localizado en la explanada Oriente, saliendo por las puertas de emergencia de frente. Les recordamos que no está permitido el ingreso de bebidas y alimentos al auditorio y está estrictamente prohibido fumar. Esperamos que disfruten su estancia.
Ok. Bien, pues buenos días a todos ustedes que nos acompañan a esta ceremonia muy especial de ingreso de 5 nuevos académicos a la Academia de Ingeniería de México. Antes de empezar, quisiera dejar constancia y felicitación al Instituto de Ingeniería por sus 70 años de actividad notable que ha tenido desde su creación. Y bueno, señalaba que marca el interés de la Comisión de Especialidad de Ingeniería Civil por integrar prominentes profesionales de la especialidad al seno de nuestra Academia de Ingeniería de México. Su servidor, maestro Alberto Lep Zúñiga, su presidente, les da la más cordial bienvenida a esta ceremonia protocolaria de ingreso a los doctores Arturo Schultz, a Adolfo Matamoros Hidalgo, a JoAnn P, a Ellen Radji y desde luego al doctor Taylor Amy. Como académicos correspondientes de la Comisión de Especialidad de Ingeniería Civil. Este evento lo estamos celebrando en formato híbrido, presencial, en el Auditorio José Luis Sánchez Bribiesca de la Torre de Ingeniería de la UNAM y por Zoom y redes sociales hoy, 24 de marzo del 2026. Agradezco la presencia del doctor Guillermo Aguirre Esponda, vicepresidente de la Academia de Ingeniería, del maestro Alejandro Velázquez López, que es secretario de la Comisión de Especialidad de Ingeniería Civil, al doctor Sergio Alcocer Martínez de Castro, expresidente de la Academia, promotor e invitado especial de esta ceremonia, y a quienes harán los comentarios a los trabajos de ingreso y que en su oportunidad mencionaremos, así como a la audiencia que nos acompaña. Estimados todos, en el transcurso de este día, esta ceremonia de ingreso se llevará a cabo con el siguiente protocolo. Se explica la motivación que tiene la Academia para otorgar reconocimientos de académico o académicas de ingenieros destacados en su ejercicio profesional. Se expone el procedimiento por el que llega la Academia al otorgamiento de tal distinción. Se expone a la audiencia la vida profesional de cada académico con la que se muestran los méritos acumulados que los hacen merecedores a su reconocimiento como académicos. Acto seguido, cada nuevo académico presentará una síntesis del trabajo original que desarrolló como parte de los requisitos de ingreso. Posterior a su presentación, 3 académicos exponen comentarios a cada trabajo de ingreso. Enseguida, en acto simbólico, los nuevos académicos reciben el diploma, la insignia y la medalla que los acreditan como miembros de esta gran comunidad académica. Finalmente, el representante de la Comisión de Especialidad les dará la bienvenida y se presentarán las palabras de clausura, con lo que concluye el evento protocolario de ingreso. Bien, iniciamos este acto, estimadas académicas y académicos, señoras y señores. La Academia de Ingeniería va agrupando a las ingenieras e ingenieros que destacan por sus aportaciones a la ingeniería y que cuentan con reconocimiento por su eminente ejercicio profesional, sea en el sector académico, público o en la iniciativa privada. Hoy, la Academia cuenta con 360 miembros activos y en su historia de más de 50 años ha llegado a recibir a más de 1,128 notables ingenieros. La Academia de Ingeniería busca en sus miembros a los que se distinguen por su interés y compromiso por recorrer el camino del conocimiento que lleva a la elaboración de propuestas de solución de los grandes desafíos de la ingeniería mexicana y del mundo, a los que contribuyen a que jóvenes se conviertan en ingenieras e ingenieros con un sólido compromiso social y el más alto nivel profesional, a los que promueven el ejercicio ético y responsable de nuestra profesión, a los que se desempeñan sin límite a la libertad de pensamiento, expresión o actuación, a los que convierten los desafíos en oportunidades e inyectan fuerza, modernidad, innovación y calidad en las soluciones, a los que se unen en la aspiración de ser guía y motores del desarrollo económico y social de nuestro país. La Academia transita a su misión a través de realizar estudios estratégicos, mesas redondas, ciclos de conferencias, coloquios, foros de discusión, congresos, conferencias y trabajos de ingreso, como los que presenciaremos con la conferencia que nos brindarán el doctor Arturo Schultz, el doctor Adolfo Matamoros, la doctora JoAnn P, la doctora Ellen Radji y el doctor Taylor E. Ahora voy a pedir al doctor Guillermo Aguirre Esponda, vicepresidente de la Academia, y escucharemos de él cuál ha sido el proceso que se sigue para el ingreso de nuevos académicos. Tiene la palabra, Señor vicepresidente.
Con mucho gusto, señor presidente. El ingreso de un nuevo miembro de la Academia de Ingeniería se rige por su estatuto y por el reglamento de ingreso de académicos y designación de académicos de honor. En ellos se establece que son académicos titulares y correspondientes los residentes en nuestro país y fuera de él, de cualquier nacionalidad, que hayan realizado contribuciones relevantes a la ingeniería y sean propuestos por al menos 5 académicos facultados para el uso de sus derechos, los cuales argumentarán sus méritos y puntualizarán sus logros. Asimismo, cada candidato habrá manifestado su deseo de pertenecer a la Academia de Ingeniería, consciente de las obligaciones que contrae. Es muy importante destacar que todo miembro de la Academia de Ingeniería debe pertenecer a una de las 19 comisiones de especialidad que componen la organización troncal. En este caso, las doctoras JoAnn P. Browning, Helen M. Ratje y los doctores Arturo E. Schultz, Adolfo Matamoros y Taylor A. quienes ingresarán a la Comisión de Especialidad en Ingeniería Civil. En el proceso de evaluación de las solicitudes de los candidatos para ser académicos titulares o correspondientes, el Comité de Admisión solicita opinión que corresponda, revisa la candidatura y vota de manera individual y secreta para emitir su dictamen, el cual es ratificado por el Consejo Académico, el que incluye a los miembros del Consejo Directivo, a los presidentes de las 19 comisiones de especialidad y a los coordinadores de los programas multidisciplinarios. Cuando el dictamen es favorable para el candidato, este debe presentar un trabajo inédito relacionado con su área de especialidad, mismo que es comentado por 3 académicos. El proceso de ingreso culmina con la ceremonia protocolaria de ingreso. Sería todo, señor presidente.
Muchas gracias, doctor Guillermo Aguirre. Enseguida, el maestro Alejandro Vázquez López, que es secretario de la Comisión de Especialidad en Ingeniería Civil, expondrá la semblanza de nuestro primer académico que ingresa el día de hoy, el doctor Arturo Schultz. Sí, de aquí. Hola.
Good morning, everybody. Welcome. I'm going to read the biographical sketch of Arturo E. Schultz. Dr. Schultz is professor and director of the School of Civil Engineering and Environmental Engineering and Construction Management, as well as Robert F. McDermott Distinguished Chair at the University of Texas of San Antonio. He was previously professor and director of hybrid testing in the Department of Civil, Environmental, and Geoengineering at the University of Minnesota, Twin Cities. He has over 30 years of experience as a structural engineering researcher and educator with interest in masonry, concrete, steel, and wood structures. His work includes analysis, laboratory testing, and field monitoring of structural systems, as well as numerical simulation of structural response to extreme loading. He has authored or co-authored more than 200 publications based on his research and is one of the originators of the MAST multi-axial structural testing system. He is currently working on enhancement to hybrid simulation capabilities of the large-scale test, LST, the laboratory at UTSA. He is an active member of multiple technical societies and is fellow of the Precast Prestressed Concrete Institute and the Masonry Society. He has received numerous awards, including the John B. Scalzi Award, TMS, the Collingwood Prize, ASCE, the Charles Somal Award, PCI, the Martin P. Korn Award, PCI, and the George B. Nasser Award, PCI. Professional preparation. Southern Methodist University at Dallas, Texas, Civil Engineering, BS, 1980. University of Illinois, Urbana-Champaign, Civil Engineering, MS, 1982, University of Illinois, Urbana-Champaign, Civil Engineering, PhD, 1986. Professional appointments. the University of Texas at San Antonio, 2021 to present, Professor and Director, School of Civil and Environmental Engineering and Construction Management, 2020 to 2021, Professor and Chair, Department of Civil and Environmental Engineering. Per institutions, 2007 to 2020, Professor, Department of Civil, Environmental and Geoengineering, University of Minnesota, Twin Cities. 1996-2007, Associate Professor, Department of Civil Engineering, University of Minnesota, Twin Cities. 1993-1995, Research Structural Engineering, Building and Fire Laboratory, NYSCT, Gatesburg, Maryland. 1986-1999, Assistant Professor of Civil Engineering, North Carolina State University. He has a lot of publications related to shared behavior in precast and prestressed hollow core slabs, horizontal self-centering structural systems in steel structures diagrams, unbonded post-tension structural masonry wall with rubber interface, seismically robust ultra-high performance fiber reinforced concrete columns, stresses at ultimate and unbonded tendons in unrouted post-tension masonry beams, measurement and analysis of distortion-induced fatigue in multi-gilder steel bridges. Synergistic activities. Field investigations of bridge collapse at ACI, member the Masonry Society, chaired the Prestressed Masonry Subcommittee, member Precast Prestressed Concrete Institute, member of the American Concrete Institute, member of the American Society of Civil Engineers as chair of the Technical Administrative Committee and Concrete Masonry Structures. He's a little short sketch about all his professional life, and welcome. It's a pleasure to have you here.
Muchas gracias, maestro Alejandro Vázquez López, secretario de la comisión. Ahora escucharemos la conferencia del doctor Arturo Ernest Schultz, que lleva el título sobre el avance de la mampostería presforzada como sistema estructural. Dr. Arthur Ernest Schultz, you have the...
It is not necessary. You can look at the screen. Que bajemos. No, está la pantalla aquí.
Ok, vale.
Thank you.
Damas y caballeros, muchísimas gracias por haberme invitado a esta sesión tan importante. Para mí es un gran honor, para mí la Academia Mexicana de Ingeniería y la institución de la UNAM y todo el trabajo que se ha producido por tantos ingenieros tan conocidos en México siempre han sido un gran aliciente. Yo voy ahora a cambiar de español a inglés porque el español para mí es una lengua de familia y mi formación profesional y mi carrera profesional ha sido toda en inglés, así que con el perdón de ustedes voy a cambiar. So my presentation is on a topic that for me has been at the center of my thought, structural engineering thought for many, many years. At face value, it's very simple. We all know about masonry, we all know about pre-stressing, and this is just a combination of the two. But the devil is in the details, as we say in English, because of all of the small things that turn out to be very important things that come from differences between masonry and concrete when you pre-stress it. I have a very brief outline here on my presentation, including an introduction, history, a quick coverage of some important research that's been done over the years, some noteworthy applications, many which a lot of structural engineers aren't aware of. A little bit on code development, primarily focused on US codes. Then I'll talk very briefly about obstacles to further implementation of the system, and then my thoughts on strategies for overcoming these obstacles and creating greater acceptance. And then lastly, some tantalizing thoughts on future directions. So masonry has been around for 12,000 years in one form or another. The Pyramid of Khufu in Egypt, the Temple of Hephaestus in Greece, the Hagia Sophia in Istanbul. Different forms of masonry at different times in human history, but they're all masonry. And why? Well, masonry has inherent structural capabilities that make it an outstanding material for structural engineering. The variety and availability of materials that you can use for masonry, as well as the ease of construction. And we all know that masonry pieces are heavy, whether they're stone blocks or whether they're blocks made out of concrete. But nonetheless, it is easier to build out of masonry than it is to erect steel columns or precast concrete elements that weigh thousands of pounds. Unfortunately, there is a perception among some or many engineers that masonry is obsolete. And you please understand that my perception and my understanding is colored by where I live in the US. And masonry has sort of fallen out of favor in some regards. They look at advances in other systems, structural steel, cast-in-place concrete, precast concrete, now plastics. Timber engineering has made huge advances in the last 2 or 3 decades. But the chief issue with masonry is its low tensile strength. Because of these problems, back in the last century, some very well-known authors that produced one of the most common textbooks put it very simply in this manner. Masonry is one of mankind's oldest building materials and probably one of the most maligned and least understood. Such misconceptions have led over the years to serious misuse of the material. And I fully agree with that, not in a very broad sense, but in very specific applications. So how do we overcome low tensile strength? Masonry is like concrete. The tensile strength is 1/10, 1/20th of the compressive strength, sometimes even less, to the point where it's almost negligible. If you're in the concrete field, you would say it is negligible. But low tensile strength has not prevented concrete from becoming probably the most common modern engineered construction material throughout the world. So why don't we do the same thing? Use reinforcing elements, typically made out of steel, but nowadays you can use non-metallic reinforcement as well. The reinforcement itself can be pre-stressed or non-pre-stressed, meaning that you stretch the reinforcing element prior to applying load to the structure. Reinforced masonry is common to the US, and of course it uses bars and wires like concrete. There are certain issues.
that you don't face in reinforced concrete. Some of these have to do with congestion of reinforcement. Others have to do with very small cavities in which to place it, and the limitations on the configuration of this reinforcement. Pre-stressed masonry, which gives you more freedom, however, has been less used. You use reinforcing elements that are tensioned before you build the structure. Now, there are systems, and in Mexico, for example, confined masonry is very popular. In a sense, it's almost a type of pre-stressed masonry, where you're using the natural properties of concrete as it cures as a way of pre-compressing masonry panels. And it is a great system, though I'm not criticizing it. I will tell you that confined masonry has failed to gain traction in countries like the US that have high labor costs, because you have to build almost like two different structures at the same time. So in this presentation, I'll give you a brief glimpse at what I see for pre-stressed masonry, including my vision for this material. Up there you see the simplest of all pre-stressed masonry systems. This comes from the United Kingdom from the early 1960s. What you see is a cross-section of a wall, in this case a retaining wall. And you see the foundation here. You see the tendon itself has been anchored in the foundation. It extends through a cavity in the masonry. The masonry is indicated by the cross-hatching. And there is a cap through which the pre-stressing extends, and then using a nut and a bearing plate, you tighten the nut very simply with a torque wrench. And as simple as that sounds, as primitive as that sounds, a lot of structures, pre-stressed masonry structures, were built in the United Kingdom in the 1960s, 1970s, and into the 1980s using this system. I'll also trace a very brief history of this material. I'll discuss some of the tensioning or pre-stressing methods, discuss some relevant research, and so on. This is, as far as I know, the earliest instance in which masonry was pre-stressed. And this is the tunnel underneath the Thames River in London. It was built in the Victorian era, the end of the 19th century, and very thick, large brick caissons had to be built. And in order to increase the strength of those caissons, particularly in tension, holes were drilled through the brick, and then heated wrought iron rods were inserted in those holes, basically hammered into place. And when the rods cooled, they pre-compressed the masonry. So it's, you could almost say it was an unintentional effect, but they knew full well that it was going to pre-compress the masonry. Of course, at the time, they didn't know how much pre-compression they were going to get, nor how much pre-compression they actually got, nor how that pre-compression changed over time. There were other early innovators at the beginning of the 20th century who were looking for roof and floor systems made out of masonry. Not walls, roofs and floors. Initially, they weren't thinking of pre-stressing. They were using metal rods to hold the masonry units in place. Quite often, the system was flat at the top, but it had an arched bottom. And so they were building a very flat arch and using some pre-tensioning with rods that were tightened with nuts as a way of holding it in place. In 1932, Jagman proposed tensioning the nuts. Even though they had been building it, they didn't think that tensioning would actually have a mechanical effect that would help them. The first attempt to actually pre-compress roofs and floors this system came in 1935 in the US by Anderegg and Dalzell. And they had some initiation of calculations for trying to determine how to tension it and how to design these. However, another 2 decades passed before this really took on some traction. In the 1950s, there were several short span pre-stressed masonry bridges built in the state of Tennessee in the United States. So that's very surprising that without any technical basis for this other than common sense, they were actually building these small bridges in this manner. And here you see a picture of it. From the outside, it looks almost like a post-tension concrete bridge, but these are precast concrete pieces, like essentially a concrete block, not the concrete block that you would use for a residential foundation wall, but it is nonetheless a precast concrete element. And in the top figure, you can see the side view, and the bottom one, you can see them being laid in place. At some point, though, the interest switched to beams, okay? And this thought was introduced actually in Switzerland by Haller. Shortly after World War II, there wasn't a lot of steel to be used for construction, so much of it had been consumed by the war effort during World War II. And then it made its way to England, from England made its way to the US. What you see in the picture here is some research out of the University of Edinburgh. And you see a series of brick beams that have been pre-stressed. You can see in the bottom photograph, the pre-stressing strand. You can see the end block to apply the pre-stressing force to the brick, and you can see the chucks used to hold that in place. Other researchers were able to investigate a number of issues regarding the performance of these beams. They were looking at a wide range of pre-stress forces or pre-compression magnitudes in the masonry. In some cases, they saw shear and anchorage failures because they had short beams with very high pre-compression stresses. They also saw the two typical modes of flexural failure, which is crushing of the masonry and compression, or rupture of the steel. But pretty much after that point, because you don't need very high pre-compression levels, the most common form of failure is crushing of the concrete, masonry or brick masonry in the compression region. If we talk about pre-stressed masonry as a general term, we can distinguish pre-tensioned and post-tension masonry. Pre-tension masonry is seldom, if ever, used. It's too complicated. However, post-tension masonry is very common. The figure I showed you of the early British system is post-tension masonry because you erect the masonry wall, and only after the mortar has cured do you actually tension the masonry with your torque wrench, or if you want to use a hydraulic jack with that. So I will use the terms pre-stressed masonry and post-tension masonry interchangeably, even though that is not quite accurate in terms of the language. At some point, the interest shifted from beams to walls. Why? Because we like to build walls out of masonry. In addition to that, it's very efficient to build walls out of masonry. In addition to that, masonry walls are very efficient, and they can be very appealing as an architectural system. Some of the earliest documented pre-stressed masonry walls occurred in the second half of the 20th century. And that goes back to the work done in the United Kingdom. From there, it moved to Australia in the mid-1960s, and then to New Zealand in the 1970s. In both countries, they used concrete block masonry, and they used the pre-stressing as a way of increasing the capacity to resist lateral loads that are perpendicular to the wall. Over the next 2 decades, the work was then expanded from very basic concepts and very basic research to understand the mechanism to other issues related to specific mechanical behaviors that were observed in the laboratory and how to overcome them if those behaviors were not considered adequate. In addition to that, the type of masonry walls themselves changed. particularly in the United Kingdom. They are very partial to their brick, and it is a very beautiful material. So if they needed thick walls, instead of casting a very wide concrete block, which is what we would do in the US, they actually built massive sections out of brick masonry. At the top, you see what is referred to as a diaphragm wall in the masonry world. That wall has at least two faces. There's a big cavity in the center that doesn't necessarily get filled. Sometimes it might be filled with gravel or with rubble. And they place the post-tensioning tendons in that cavity, anchored in the foundation and then through a cap at the top. And then they tension it at the top when the masonry has cured. Another one that was developed in the United Kingdom is the fin wall. It's a wall basically that has a series of buttresses. The buttresses can be solid or hollow, and the wall itself can be solid or hollow. And you place a post-tensioning, at least in the fins or the buttresses. You may also place some in the wall itself. You can see the cross-section for each of these two walls at the bottom. They both create a very appealing appearance when viewed from outside. So these were quite often the exterior face of a building. Then interest in pre-stressed masonry, I say exploded in the United Kingdom. Maybe that's too strong of a word. But in the 70s and then on through the present time, there has been a great deal of work being done in the United Kingdom. Not only from the point of view of learning about the system, but learning enough that you can write design codes, draft design codes. In the United Kingdom, they actually wrote and published the first design provisions. It took a long time because they started in the late 1970s, and the document didn't come out until 1985. But the British Standards Institution document BS 5628 was the first set of code provisions for pre-stressed masonry that I'm aware of. Maybe there's something here in Mexico that I've missed. I don't know. And of course, we know about the British preference for brick. But they pretty quickly realized that concrete masonry gives you a lot of freedoms when it comes to size, shapes, properties. And so a lot of people have switched to concrete block masonry that is pre-stressed. They've focused on out-of-plane loads because that's primarily the most common set of hazards that they're going to face in the United Kingdom. High wind, earth pressures, if you're talking about retaining walls or foundation walls, differential settlement, especially when you build in regions where you're going to have land subsidence, some of the mining regions in the United Kingdom, blast loading, our new reality with, maybe it's not so new, but with terrorism, is that we need this kind of capacity. And then vehicle impact, when we build very close to roadways. I would like to call your attention now to one concept in pre-stressed masonry that's very important, and that is whether or not you restrain or guide the tendons. The tendons are the elements that are tensioned and that are used to pre-compress the masonry. In this figure, you see at the top a masonry section. It's shown horizontally, so it could be a beam or it could be a wall that's been flipped on its side. You see the tendon in the center has a solid line. In this case, there has been loading perpendicular to the face of the wall. It has bent the masonry. The tendon itself does not bend because it's in an air pocket. There's nothing to force the tendon to bend. And it has a negative effect of reducing the effective depth between the tendon and the compression face. So you lose moment arm. And so if you build that way, at the instant of the wall or the beam reaching its capacity, it's going to have less flexural capacity than if you did what's shown at the bottom. At the bottom, the compression, the elements along the compression face have tabs, okay? Those tabs, those extensions, are in contact, just touching, are in contact with the tendon. So when that element bends, it's going to push the tendon and it's going to force that tendon to accommodate to the same shape of the wall. It forces, if you wish, a lateral compatibility, not a longitudinal compatibility. That doesn't exist in post-tension masonry because you do not bond the tendon to the masonry. So there could be relative longitudinal movement, but not relative lateral movement. And that becomes very important because you maintain the internal moment arm and therefore the flexural capacity. A lot of work was done in the United Kingdom to apply pre-stressed masonry for office, retail, and institutional buildings. In most cases, we're looking at buildings where the gravity loads are light. So the weight of the structure and the weight of any permanent attachments is low enough that you do not have a lot of compression in the masonry. And so the pre-stressing introduces that compression that has a beneficial effect. Okay, other effects that you get from this are enhancing the shear strength. We know that for a cementitious material, if you pre-compress it, you can increase the shear strength, at least over a certain range of compression stress. You increase the stiffness of the structure because you prevent any joint opening or cracking. And as a consequence of that, you maintain a high degree of stability. Okay, it's not as if you have an element that cracks, loses stiffness, and then will buckle at a lower load. In the photograph at the top, what you're seeing is a pedestrian bridge, and here you're seeing the bridge at the bottom. This bridge was built vertically, like a wall. That's why I'm showing it here. It was built with curvature in the longitudinal direction and also curvature transversely to shed rain. It was post-tension. You can see the anchorages at the bottom. Those are VSL anchorages. And then it was lowered into place, as you can see at the top. So a very convenient way of building masonry elements. By the way, it didn't have to be built in place. It could have been built off-site. It could have been built at a plant and then transported to place. So there are possibilities for prefabrication in pre-stressed masonry that you don't have if it's not reinforced, or even if it's reinforced with bars, you may not be willing to move it, okay, for fear of cracking damage. So at the University of Edinburgh, Podreski and Sina did a very comprehensive study of brick beams. They used solid masonry. Pre-stressed masonry does not have to be solid, but they looked at solid masonry. They looked at very high levels of pre-stress, which is not common anymore in masonry. They used steel strand. They used standard fixtures from post-tension concrete. And they identified 4 failure modes that to this day are the ones that we worry about: shear, anchorage, flexural failure due to concrete compression, crushing, and then flexural failure due to rupture of the tendons. But they demonstrated stable and ductile response, which is the important thing. And they also were able to reveal that upon cracking of a pre-stressed element, if you still have pre-stress force when you unload it, the crack closes. Here you see, once again, the same beams I showed you earlier, the same pre-stressing I showed you earlier. But what you see here is a force displacement, a set of force displacement curves where you see load on the vertical axis and you see displacement on the horizontal axis. The points all represent results from their tests, and the lines are some calculated capacities for those beams. So a couple of things that they show is that it is a very stable response. It doesn't have sudden changes in stiffness and strength. It's able to deflect quite a bit, and they can estimate with a high degree of accuracy what the capacity is going to be. So that's very important. You may have an excellent system, but if you cannot predetermine what the capacity is, it's not going to serve you well for design. A similar study was done in India. In their case, they use steel wire, and that's why, for me, it's so important. They dramatically changed the pre-stressing system. Some of the wire was, I'm using the term draped very loosely, okay? It was bent, it wasn't straight wire, and then others were straight. And once again, they were able to demonstrate stable ductile response and crack closing ability. Here are some of the sections that they looked at. And you can see it's literally a series of courses of bricks in different configurations. And you leave a gap, a longitudinal hole to place the pre-stressing in grout. They used debonding elements, plastic sheeting, so that the wire itself was not touching the grout. And here you see the response of one of their beam tests. Once again, load on the vertical axis, displacement on the horizontal axis. Data very close to their calculated force displacement relationship, and a very stable system. Some later time, I worked with a group from the University of Medellin in Colombia, and we looked at hollow masonry. So concrete masonry, but the masonry is hollow. It's no grout at all. The tendons were restrained, and here you see the elements, or sorry, the beams. The blocks were actually turned 90 degrees, and they're placed in a soldier pattern. Concrete end blocks were used to distribute the pre-stressing force, and then high-strength bars were used instead of strand or wire. The eccentricity was varied, and contrary to what we expect from post-tension concrete, the eccentricity didn't have a strong effect. And here you see a box and whisker plot showing you on the vertical axis the ratio of calculated to tested tendon stress at ultimate. So the stress in the tendon at the moment that the beam reached its capacity is shown here. Why do we care about that? Because we need it for design. Because it changes from the initial pre-stress with the bending of the element. And it's shown for a variety of different design codes. We can talk about how the various codes do it, but there is some variability. Some do a better job than others. Let me just leave it at that. And then at the bottom, you see the same type of box and whisker plot, but for the moment capacity. So the moment is calculated using the stress that was used in the first plot, but is used now to calculate the moment capacity. And once again, some methods allow us to very accurately calculate the capacity of the beams. They were even more daring, and they looked at slabs that were pre-stressed. And they looked at concrete block slabs that were essentially two-way slabs. Here you see the top view of the slab. The checkerboard pattern that you see is because some of the blocks were restraint blocks. So they were a solid block with a hole that allows passage of the pre-stressing tendon. And here you see the plan view of the slab. It was supported on all four sides, and since it's a square configuration, it's a two-way system. And here you see the load versus displacement response for the system. The darker curve is for the system that had restrained tendons. The lighter curve is a system just like this one, but without any restraint blocks. You see that you get about more than twice as much capacity for the restrained blocks, plus you also get a lot more deformation capacity. So even for a slab, if you choose to go through the work of building this way, you can get a good system. Now, I grant you that this is an expensive system to build. I'm not proposing that this is something that we should be doing on a regular basis, but I think as an academic exercise, this really shows the capacity, the capability of pre-stressed masonry. So let's talk about out-of-plane loads a little more in a more modern sense. So in the UK, the work continued, and they looked at out-of-plane walls for other purposes. One of the things that was observed was that you increase the cracking strength from pre-stressing, pretty obvious. You get greater flexural stiffness. So the behavior under service conditions, the serviceability is improved. You get increase in out-of-plane resistance, okay, and reduced crack width. So cracking occurs at a later stage. If it cracks, the cracks can close, and the cracks themselves will have narrower widths. So from a serviceability viewpoint, this is a much more effective system than, say, reinforced masonry. Additional research identified a number of other things that I have mentioned before, so I think I'll just skip this one. And then, same thing here. The next stage was to look at very slender walls and what kind of impact does slenderness have on the walls. So a number of researchers, mainly in Canada, looked at tall walls to see what kind of effect you're going to get. And they observed the same improvements with pre-stressing. And they observed the same beneficial behavior in terms of guided tendons versus unguided tendons. They also observed the importance of P-delta moments, so it's not as if we're going to neglect P-delta moments, but the important thing is, from research out of Switzerland, is that the pre-stressing does not affect P-delta moments if you're using restrained tendon, because the force from the pre-stressing is moving with the deformed wall. It will affect the P-delta behavior if you do not restrain the tendons. So once again, the importance of restrained tendon. Another study, and this was conducted by one of my PhD students at Minnesota, Jennifer Bean-Popain. She built a series of very tall, slender walls. You can see in the bottom left a diagram of the wall. Some were solid brick, some were hollow block, concrete block. She designed and built a system for applying lateral load in a somewhat distributed sense. And of course, we observed a lot of the observations that others had made, but we were also able to see that using pretty common standard numerical techniques, we were able to get load deflection curves that simulated reasonably what we were getting in the tests. The test here is the solid line. The simulations, depending on the boundary conditions we were assuming, are the blocks and the triangles. And what you see here is for a brick wall, and here you see a similar plot for a concrete block wall. Some pre-stressed masonry research in New Zealand, of course, they were very daring, okay? So there was no code they could use in the 1960s to design and build these things. There was very little experience. So they actually worked with a builder who put together his own crude shake table in their yard, and they did their own shake table tests on pre-stressed walls. Here in Mexico, Hernandez and Meli summarized a series of monotonic tests on concrete block shear walls that performed very well. In the studies here in Mexico, they demonstrated dramatic improvements in performance over unreinforced masonry. They also verified that you have to tie the Ys in cavity walls, okay? And lastly, that you need bed joint reinforcement to handle shear or other, as I like to think of it, stray sources of tension in a localized sense. Later studies in Canada showed substantial increases in shear strength with pre-stressing. Now, we're no longer talking about flexure, we're talking about shear strength. And they're talking essentially of diagonal tension strength. And this, a lot of people got very excited about this and started doing tests to look at this effect. The other thing that they noticed in shear walls is that there's an evolution of the forces in the tendons having to do with the wall rocking and the compression and tension region seeing changes in the axial force demand. And of course, the increases in shear strength that I mentioned earlier. And this was studied by a great number of people. Here you see a series of research investigations that looked at this issue. But in summary, what they found is that essentially the friction coefficient, the coefficient that tells you how much increase in shear you're going to get relative to the amount of precompression from the Moore Coulomb theory, varies widely for monotonic loading, anywhere from 0.4 to 1.6. And there's a number of different things that are happening here, whether you have adhesion or just pure friction, the surface roughness, any number of issues. And that's why the variation is so large. Probably most important is from a study by Woodward and Rankin that for cyclic loading, where you get rid of some of that initial adhesion, you get rid of some of the asperities that give you a lot of capacity initially. For cyclic loading, we're looking at roughly 0.4. And that now is reflected in modern code provisions for pre-stressed masonry. Now, some of the most troubling issues for pre-stressed masonry, especially for seismic design, is energy dissipation capacity and potential yielding of tendons. Actually, there's a third one, and that's compression damage in the toes of the walls at either end. Some early research in Australia by Lawson and Ingham tried to address some of these issues. They added devices to increase energy dissipation. They strengthened the compression toes of the wall on either end to try to reduce compression damage. And of course, followed a design procedure that would prevent premature yielding of the tendons. Hassanli in 2015 in Australia tested a series of masonry shear walls. He was a little concerned about this notion of preventing potential yielding of tendons, and I think he's right. So what he did is he distributed the tendons over the length of the wall. Here's one of his specimens. So what Lawson and Ingham did, the tendons that you see in green, they suggested that they be concentrated towards the center of the wall. And that was actually a recommendation that Nigel Priestley had made for precast concrete shear walls. But Hassanli essentially said, well, I'm going to have a distribution, which is what we like to do in building practice anyway. We don't like to have too much reinforcement too close together, and see what happens. And he was able to get pretty good performance. You see here a low displacement result in cyclic loading, load on the vertical axis, displacement on the horizontal axis. And he's getting pretty good performance up to about maybe 2% drift. This is for a system with relatively low pre-compression. If you increase the pre-compression force, then you start getting some lack of symmetry because the compression side starts getting damaged prematurely. My last PhD student at Minnesota, Dimitrios Kalionsis, decided to investigate this, and he adopted a somewhat different approach. He used fiber-reinforced rubber pads below the compression toes. And these were not big pads. These are relatively small pads. They replaced part of the mortar at the base of the wall. And he was able to get very good response. The pads first reduce the compression damage tremendously. By reducing the compression damage, it also, if you wish, suppressed some of the diagonal cracking damage that you get from shear. So your wall held itself together better. And he was able to get performance with no deterioration of strength and very little residual displacement, up to about 4% drift, and up to 5% drift with a little bit of deterioration, still acceptable for a wall at the limit of its capacity. So here is his wall. Please notice the tendons are close to the edges of the wall. So he was not following the Priestley rules, and I respect Professor Priestley very much. May he rest in peace. But I think this notion that you have to put the tendons in the middle that's not something that we have to do all the time. It's hard to see, I know, but if you look at the front and back corners of the wall at the bottom, there's a slightly darker thing. That's the pad. It was 8 inches long, the width of the block, and then it was half an inch tall. And it is essentially a hard rubber with a cotton fiber mixed into it. Here is his force displacement curve. The displacement is shown at the bottom as a drift, and then the lateral load at the top. And if you can see, the drift goes almost to 5%. That's when we stopped the test because we were reaching the limit of the equipment that we were using for applying the lateral displacements. Up to 4% drift, no deterioration, and up to the end, just a slight amount of deterioration. So what we have here is a wall that is resilient. It goes against these negative notions that were that have been and continue to be promoted in the US that pre-stressed masonry is not adequate for seismic design. Okay, another criticism is losses under long-term loads. If you're using a tendon for the capacity of your system, what's going to happen when you have losses in your tendons? Does that mean your wall no longer has any strength? And the fact is, just like we handle this issue in pre-stressed concrete, we can handle it in masonry. You observe how much creep and shrinkage you're going to get, use low relaxation steel, and then do tests. And what we found is that for up to about 12 years, you can assume that your concrete is going to see somewhere between 24 and 31% loss. We actually recommend 35% loss for design. And for clay masonry, because of the differences in the material itself, 17 to 22%, we recommend about 15 or 20%. This is from a study by Langsner at the UK. What you see in the vertical axis is loss in stress, tendon stress. And on the horizontal axis is time. This goes up to about 200 days. And this is for concrete block masonry. The top curve and dots are for a column. The bottom dots and curve are for a wall. And you can see that at about 200 days, they both start leveling off. So whatever loss you're going to get is going to occur in the first 200 days. And for these, if you look at the average of those two, you certainly are within that range of 21 to 31%. In addition to that, Woodham and Hamilton monitored a noise barrier in the Denver area. These are concrete block pre-stressed walls. And they put sensors in the tendons and a number of other sensors to monitor other issues. And they found over a 2-year period that they had a loss of about 28%, which goes very clearly in hand with what Langsner had proposed. Let me talk about some other pre-stressed applications. In Canada, they've looked at CFRP tendons, in particular for retaining walls, especially if you're concerned with the retaining wall getting infiltration of water and corroding your reinforcement. Of course, there are other ways of protecting steel tendons, but they wanted to see if we could actually use CFRP tendons. They've been monitoring that system for some time now, okay? It's going on 20 years, and it's doing extremely well. Garcia, from the group at the University of Medellin, they were looking at earth retaining walls that were made with hollow concrete block masonry. The tendons themselves were wrapped in material to protect it from water. Very simple construction method, a method that they have found is cost competitive with reinforced concrete or reinforced masonry. And they've used this along roadways. They also did some tests, and this is a simulation of their retaining wall tests. In the bottom, you can see their low displacement response for one of these retaining wall specimens, and it does extremely well. Over the 2-year period that they included in this publication, no damage was observed in some of the walls in the field, cracking or corrosion of the tendons or anything like that. I want to show you this one because it just seems so daring to me. This is from the 1960s in New Zealand. They're so concerned about earthquake resistance, but here they're building a concrete block, a series of concrete block walls in a 6-story building. There is no frame. There are no other elements for lateral load resistance besides the concrete block wall. They're using 8-inch wide block. They're using 2 of them, leaving a cavity in between for the reasons that we always build cavity walls. And what you see coming out of the block, those are the tendons. They inserted them into into garden hoses. At the time, they couldn't find a cost-effective protection system, and they sealed the garden hoses at either end after they inserted the pre-stressing in there. One of the issues, of course, is how do you manage all of these tendons along the length of a wall, and you see that they end up going all over the place. It almost looks like they're building an arch structure. That's not the case. I can tell you it's just a typical building. And of course, they ran their shake table tests to make sure that this system was going to work. And that building, as far as I know, is still there. Strengthening is also a very good application. This is not new construction, but there was a series of buildings that were retrofitted in the Christchurch Arts District. Two in particular were partially strengthened using post-tensioning. And during the 2010-2011 Canterbury earthquake sequence, the buildings that were strengthened using post-tension had only moderate damage. Some of the others had very heavy damage and even collapsed. And the others were also strengthened, but not using post-tensioning. Here you see a section of one of the walls. They actually placed the post-tensioning outside of the masonry. So typically they would find a corner. So they would find a corner in the wall and they would place their post-tensioning there. They had to attach brackets, steel brackets at the top to serve to anchor the top of the tendons, and they built small concrete pads at the bottom to anchor the reinforcement. Of the buildings that had this kind of system, the only damage in the two buildings that survived this way was in regions that were not strengthened using post-tensioning. The gable ends, okay, and then there was a tower. Now, the tower they could have strengthened as well, but for whatever reason they ran out of money and they didn't. In Italy, Zampieri has proposed strengthening of arches using this concept as well. Now, they're placing the tendons in the horizontal tie at the bottom of the arch. No, that's not it. So this horizontal tie is the pre-stressing tendon. They built in line, they placed an actuator and a load cell, so they're able to monitor it. And then they also have, along the entrados, they have steel cables held in place using anchors that go into the masonry. And the point being that if you shorten that tension tie at the bottom, you're going to have the tendency of deforming the arch upward. And you don't want to do that, and so you restrain it that way. They've done a series of tests and analyses in the laboratory that shows that this is a very viable way of strengthening arch bridges. Some unique systems, and in the case of the VSL Corporation, what's unique is the post-tensioning hardware. They actually developed a system. You see it on the upper left. That's a cross-section of a wall. They use their standard ducts. They use their standard monostrand, and then they use the dead-end anchorages at the base so that when they insert the monostrand, it locks the strand into place, and then they have a stressing anchorage at the top. They've used it in a number of places in Europe. Here you see the elevation of a kindergarten building, and you can see the vertical elements which show you the pre-stressing this way. So the kindergarten building itself is not the noteworthy application. It's the use of this hardware. Now, unfortunately, this hardware is expensive, as is anything that the VSL Corporation sells. And because of that, it fell out of favor. For me, the most mind-blowing applications have been from Eladio Dieste, an architect from Uruguay, who designed beautiful brick structures comprising complex folded shells made out of masonry. No reinforcement, no other backup structure, just the masonry. You see the inside of one of these here. This is the Church of Christ the Worker. There is no flat surface in there. All of the surfaces are curved, and some of them highly curved. And in the bottom, you see the construction technique. So he used flat clay masonry pieces. You can almost say it certainly wasn't a brick, but they were pieces. They were made out of fired clay, so by all rights, they are masonry. And he would place the reinforcement in the joints between the pieces. And that way he could build these huge shells spanning long distances out of masonry. Okay, practical engineering. This is one that I really love. A very simple school building somewhere in the Midwest. Biggs reports that this building was originally designed using reinforced masonry. in the early 2010s, using the U.S. Masonry Design Code. The owner of the school district, then sought bids for someone to redesign it as a post-tension masonry building. And they were able to redesign it and save money from grouting costs. It still has some grouting, but a lot less than the original design. So it can be cheaper than reinforced masonry. I think that's one of the important things. And you retain those properties and characteristics that had you go to masonry in the first place. But you can build cheaper if you want. Biggs and I were looking at other applications. This is a contractor in Maryland who builds flat lintels and very shallow arches for lintels in a warehouse. And you can see his construction technique. He has a duct. You can see in the upper figure, he threads the brick onto that duct. When he's done with that, he runs a rod into the duct, and then he places plates and nuts at the end and just tightens them with a wrench. And he has sold hundreds of, if not thousands, of these lintels throughout the Maryland area. This is a list of codes that have been developed throughout the world. I don't want to bore you too much with it. I just want you to look at the countries. The first one, United Kingdom in 1985. The second one, surprisingly, South Africa in 1992. Well, maybe it shouldn't be surprising. They were following the British standards. The next one, in Canada, once again, they don't follow the British standard, but they do look at it a lot. Let's put it that way. Then in the US in 1999, we developed our own. Switzerland, 2003. New Zealand, 2004. The European Union adopted what the United Kingdom does and then made some modifications. And the most recent that I'm aware of is Australia in 2018. So a lot of work, and all of this has happened from 1985 on. So there is a great interest, and there's a great interest throughout the world. It's not just in one or two countries. This is how the code has changed in the US. We used to call it the MSJC, Masonry Standards Joint Committee. Then we changed it to TMS 402, and it had to do with the societies that were supporting the code. But here I list for the various editions, 1999 through 2022, some of the changes that have occurred. I think of greatest importance here is the number of commentary references that has increased by 50%, suggesting that we know a lot more now than we did when we started, and we're implementing that in the code. And then on the right, I show you some of the changes that have taken place in that time. Some obstacles in implementation, and these are obstacles that I have observed in the US. Knowledge gaps. If you have knowledge gaps, you're going to have a hard time convincing people to use a new system. In particular, those associated with seismic performance, but others associated with anchorage behavior, as well as durability of the accessories. User education. A lot of designers, whether they're architects or engineers or material specifiers, they don't know about the system very well in the US. They don't know what the design procedures are. They don't know what the specifications are for the system. They don't know about the architectural forms they can build. They don't know about construction methods. Okay, they assume that all of these are going to be detrimental to their efforts. Code limitations. We tend to have problems at least in the US, accepting new systems into codes, especially for seismic resistance. That is a serious limitation. We have codes that are very young for masonry in the US, and so that's also a bit of a problem. And then we have gaps, not just in how to design, but how to build these. And then what I call design fear. That's probably a terrible term. But if you ask a designer, why don't you build with post-tension masonry, they're going to list three or four reasons that scare them about pre-stressed masonry. Okay, that's the design fear. They're concerned that it's not going to work the way you're telling them it's going to work. So how do we fix that? Well, we have to address the knowledge gaps. We have to expend the money that it takes to do the research that is still needed. there is a program in the US called the Masonry Checkoff Program. For every concrete block that's sold, some money is placed into an account that can be used for research. User education. We need to start a program to educate users about this. Most colleges in the US don't have masonry courses. And if they do, they have one. They don't even have masonry in their construction materials courses. I know it's a lot better here because I've talked to some of the faculty here, and you do a much better job. So how can we expect designers in the US, builders in the US, to know how to build this system? Code limitations, and I mentioned a little bit of that before. If you have a code that the designers perceive as being limited in this particular system, they're not going to use it. And then how do we address the issue of design fear? And we have to tailor an educational program to address these concerns. And we have to, as we say in the US, we have to take it on the road and start informing designers throughout the US about this. We have to establish an organized effort to do all of these things and involve all of those organizations that claim to have an interest in masonry construction. We need to rely on a series of groups to help us with these, first defining, developing, and then delivering these. We have to put these plans into action. And one of the issues that I think is very important is who will manage it. In concrete in the US, it would be the American Concrete Institute. Excellent organization. I was actually heavily involved with ACI at the beginning of my career. At some point, I felt like a fish out of water because there were so many academics. And so I said, let me go to masonry. There aren't any academics there. But in masonry, our society, the Masonry Society, is very small. It's hard for us to manage this. So who's going to do it? And that's a question for which I don't have an answer, but we have to come up with one. Okay, some future directions, and then I'll be done. So some researchers at Harvard University looked at using modern technology as a way of developing, they don't even refer to it as masonry. Okay, they're so removed from the profession, they talk about it as ceramic extrusions. But basically, they're building things out of fired clay. And then they're putting it together to build structures. They're not engineers. They're not contractors or constructors. They are architects. So bear that in mind, because for them, what's important is something that is, first of all, very appealing, and second of all, that seems to defy all the laws of nature. So here's one of the sculptures that they've built that way. And the ceramic elements are the ones that are colored. That's not paint that was fired into the ceramic element upon building the element. And they use advanced computer applications for the entire process. So if they can do something like that, can't we build a simple rectangular square building? I think we can. Alternate methods of post-tensioning. Expansive, high-performance concrete that is used for chemical pre-stress applications in concrete can be applied to masonry. It's a little bit different, okay? You would be using it for the grout, and you would be placing the grout so that it expands and pulls on the rod, which then tensions the masonry. The question, of course, the key is, how do you know how much pre-stressing you're getting? The other one is the use of shape memory alloys, okay, that are sensitive to heat, the nitinol shape memory alloys. You can basically replace the jacking process. This is a very simple investigation, but it shows a beam. This is a concrete beam, but if we can do it for concrete, we can do it for masonry. And different types of SMA reinforcement is shown there with different properties. And as you apply heat, you can get these various layers to apply, to change, to go back to their original shape and pre-compress the masonry. So that could also be a very important addition to pre-stressed masonry. So let me finish here. I hope that I've convinced you that pre-stressed masonry has changed a lot over the past, it's actually more than 1 century. It's more like a century and a half. I hope that I've given you a flavor for the research that has been done, for what daring engineers have done in the field. I hope that I've given you an idea of some of the potential problems with masonry construction and how pre-stressed masonry can avoid them. Effectiveness in various type of structural elements like beams and walls. And then that despite this strong foundation, we still have a series of issues that are holding this, what I believe to be an excellent system, back. And then lastly, the coordinated strategy that I laid out towards the end of the presentation as a way of overcoming these problems. With that, I thank you very much for your attention, putting up with me, and I would like to very quickly make some acknowledgments. Hans Rudolf Ganz, formerly of the VSL Corporation, was the individual who came to the US and really lit the fire under a number of people to develop our pre-stressed masonry system, to develop a code. David Biggs, who has been a mentor for me for many years of Biggs Consulting Engineering, worked very assiduously at the beginning with Hans Ganz to get this effort going in the Masonry Society. Matt Scalforo was my first master's degree student when I was at North Carolina State. He then moved on to the Brick Industry Association. He, for his master's thesis, basically developed a draft code. Jennifer Bean Popane, one of my PhD students at Minnesota, that when she completed her degree went to the Target Corporation, that really helped us understand a lot about slender masonry walls. And then Dimitrios Kalionsis, my last PhD student at Minnesota, who's now at the University of Houston, who, in my opinion, has solved the problem of resilient masonry for seismic applications. So thank you very much.
Muchas gracias, doctor Arturo Schultz. Una presentación muy completa, líneas de tiempo, criterios, diseños, experimentación y termina con recomendaciones para que esto continúe progresando. Bien, vamos a tener ahora unos comentarios sobre el trabajo del doctor Arturo Schultz. Están con nosotros el doctor Arturo Tena Colunga, el doctor Bernardo Gómez González y el doctor Raúl JoAnn P, todos ellos pertenecientes a la Comisión de Especialidad en Ingeniería Civil. Y le damos primeramente la palabra al doctor Arturo Tena Colunga. Arriba.
Muchas gracias, maestro Alberto Lepe, presidente de la Academia, distinguidos compañeros. Arturo, un honor. Entonces, vamos a hacer unos comentarios a lo que nos acaba de presentar mi tocayo Arturo Schultz. Bueno, entonces, organiza así, bueno. Como creo que les quedará muy claro a la audiencia, el doctor Arturo E. Schultz es un experto mundial en el tema de las estructuras de mampostería y nos presenta un manuscrito muy rico en el tema de mampostería presforzada, el cual es muy relevante. Hace un viaje desde sus orígenes en la era victoriana hasta el resurgimiento en tiempos más modernos en Gran Bretaña en los años 70. Resume de manera sintética una gran cantidad de investigaciones, privilegiando las experimentales que se han realizado principalmente en Gran Bretaña, Suiza, Estados Unidos, Canadá, Nueva Zelanda y Colombia, aunque menciono una reportada en México en 1982 por los doctores Óscar Hernández Basilio y Roberto Meli, y tengo que aceptar este relator que él no lo conozco y no lo he encontrado, así que yo creo que nos las debes de pasar, el PDF de donde lo hayas obtenido. Entonces, de hecho, comento, no lo pude encontrar utilizando herramientas como Google Académico, lo busqué todo el PDF, no lo encuentro. Bueno, entonces eso nos da pie de por qué no se ha desarrollado la mampostería presforzada en México, ¿no? El trabajo que se hizo aquí, pues, no lo conocemos. También el doctor Schultz nos reporta algunas aplicaciones de interés, esencialmente en estos mismos países, incluyendo una en México para rehabilitar torres o campanarios de iglesias coloniales, que también me imagino que es trabajo de Meli de Hernández Basilio. El doctor Schultz presenta una síntesis muy valiosa de la evolución a través del tiempo de los reglamentos del mundo que se refieren directamente a la mampostería presforzada en orden de aparición: Reino Unido, Sudáfrica, Canadá, Estados Unidos, Suiza, Nueva Zelanda, la Unión Europea y Australia, donde se aprecia el mucho tiempo que ha tomado que aparezcan guías para el diseño de mampostería presforzada por primera vez en países como Estados Unidos, Nueva Zelanda y Australia, dado el interés y la investigación previa hecha en estos países. El doctor Schultz explica con mayor detalle la evolución de las normas de los Estados Unidos, dado que además de residir ahí, es miembro activo del Comité de Normas de The Masonry Society desde hace décadas. También reflexiona sobre temas que en su concepto se han convertido en obstáculos para una mayor aplicación de la mampostería presforzada a nivel mundial, los que agrupen 4 grandes rubros: vacíos de conocimiento, educación de los potenciales usuarios, limitaciones de reglamentos de diseño y miedo a diseñar este tipo de estructuras. Propone, desde su punto de vista, qué estrategias deben seguirse para que la mampostería presforzada sea aceptada y más empleada como un sistema estructural seguro en el mundo, cómo combatir a los obstáculos que identificó en la sección anterior y cómo emplear tecnologías y estrategias de diseño del siglo XXI para consolidar el uso de la mampostería presforzada. Digamos que esto sería un resumen, pero sí me gustaría ahondar y reflexionar sobre algunos aspectos que él comenta y que pues queremos darle nuestra opinión, que pues ya sabe, ¿no? Primero, citaremos lo que escribe en inglés cuando sea esto relevante y luego qué es lo que reflexionamos. El doctor Schultz escribió sobre áreas de oportunidad en la investigación y cito en inglés: "One such area is the seismic performance of resilient systems. As noted earlier, 2 aspects of stress masonry seismic behavior require further investigation: energy dissipation and compression to fragility. As code provisions evolve, additional areas is needed of." Entonces, en opinión de este relator, desde el punto de vista de diseño sísmico resiliente, el mayor problema sería la fragilidad del patín de compresión. Yo entiendo lo de la disipación de energía desde el punto de vista que tenga un sistema de utilidad de reserva, pero si nos estamos enfocando a diseño sísmico resiliente, tenemos que preocuparnos que se recuperen pronto, ¿ya? Entonces, en un enfoque de resiliencia moderna sí es bueno que tenga reservas para disipar energía de histéresis, pero no hay que gastarla toda con factores de reducción que lo que provoquen es que cuando vayamos después del sismo encontremos que ese muro está todo tronado y eso no nos lo va a aplaudir nadie ni la vamos a recuperar pronto, ¿ah? Entonces, eso es básicamente lo que yo pondría. Me parece muy bien y estoy de acuerdo que su alumno hizo un extraordinario trabajo para darle mayor capacidad de formación y de utilidad. Aquí el consejo es, bueno, qué bueno, pero no hay que sacarlo todo en un diseño moderno si es que de veras aspiramos a tener sociedades resiliencias ante sismo, ¿verdad? Ahora, desde el punto de vista resiliente, yo creo que lo importante sería determinar con certeza razonable 2 parámetros: las distorsiones en las que los muros postensados presentan un daño razonablemente reparable y por ende puede ser recuperada la estructura en poco tiempo y la gente no va a pedir que le tiren la estructura y construyan una nueva. Y la otra, cómo se estimaría la resistencia lateral que sea razonable y tengamos un margen. Por supuesto, sería aún mejor definir la curva primaria global de comportamiento, mostrando además cuánta reserva de formación se tiene después de la distorsión asociada al daño reparable. Eso es importante cuando la demanda real durante el sismo sobrepasa notablemente aquellas que se establecen en los reglamentos para su diseño y como bien sabe el doctor Schultz, pues los de movimientos del terreno siempre andan jugando a la lotería y pues tienen un riesgo de que de lo que hemos visto, de lo que suponen, pues tomamos algo menor para diseñar, para que sea económico, ¿ah? Entonces, esto es la razón por lo que frecuentemente en sismos de gran magnitud en muchos países del mundo, donde está incluido México, pues cuando comparamos los registros de aceleración y los espectros de respuesta asociados a ellos, pues rebasan el contemplado en las normas. Pero no nada más le pasa a México, le pasa a Turquía, le va a pasar a los americanos, les va a pasar a los canadienses, les va a pasar, bueno, ya le pasó a los neozelandeses, les va a pasar a todos. Bueno, en ese sentido, en una sección de su rico manuscrito que se llama Adopting 21st Century Strategies, en el último párrafo, el doctor Schultz aborda temas relacionados con un concepto moderno de resistencia sísmica, al comentar que structural performance objectives, such as crack suppression or crack closing, deflection control and dependable strength, can be met effectively because of a calibrated active pre-stressing force drives the system's behavior. Entonces, considero este párrafo en su texto muy importante y relevante para promover el uso de mampostería presforzada en un contexto moderno de resiliencia sísmica. El doctor Schultz también agrupa los obstáculos de la aplicación de la mampostería pensado en knowledge gaps, user education, design code limitations and design fear. En ninguna de estas categorías menciona un aspecto que a este revisor le parece muy importante, a lo mejor por parecerle muy obvio al doctor Schultz, porque pues, esto lo ve todos los días, dada su enorme experiencia en el tema. Entonces, al igual que para el concreto presforzado, debe existir una calidad mínima del material competente a compresión en función del tipo de acero que se emplee para pretensar o postensar, o en estas épocas modernas con estas barras de fibras sintéticas de carbono, etcétera. Como los reglamentos modernos se enfocan en construcciones nuevas, con base en la experiencia del doctor Schultz y conociendo los tipos de acero que se han empleado para pretensar y postensar exitosamente la mampostería en los países pioneros, Gran Bretaña, Estados Unidos, Canadá, Suiza, Nueva Zelanda, pues sería valioso que el doctor Schultz nos indicara qué resistencias mínimas a compresión de las piezas deben tener las unidades de mampostería y qué tipo de mortero de junta debe usarse como mínimo. Un mortero tipo 1 de nosotros, el mortero tipo S de los americanos, o se puede utilizar un mortero de menor calidad, por ejemplo el N de los americanos o el 2 de nosotros, para que la mampostería presforzada se pueda aplicar con confianza en países como México. De la misma manera, qué tipo y calidad del grout debe usarse cuando se use grout, si es fino o grueso. Esta información sería muy valiosa para su promoción en países como México, donde actualmente existen piezas de distintas calidades. Hay unas muy malas que se comercializan por todos lados, y lo peor de todo es que se usan, pero también hay piezas de buena calidad. Entonces, eso sí, bueno, hay que decir que las piezas, nuestras piezas, la calidad de nuestras piezas, las resistencias que se les piden como mínimo en las normas, no tienen que ver nada con las que se les piden como mínimo en los Estados Unidos. Entonces, eso lo estamos poniendo. Entonces, eso sería importante que se supiera para poder promover este sistema aquí en México. En opinión de este revisor, ¿verdad?, con esa información por sí sola se puede promover su uso, pues porque cuando los interesados en esta modalidad vean que pueden conseguir sin mucha dificultad la calidad de las piezas en el mercado local, pues se van a animar. Si en las normas existentes se favorecen las capacidades resistentes en función de F''P, indirectamente a través de F'' y el tipo de mortero o la resistencia del grado en su caso, entonces este hecho también va a promover que existan piezas de mayor calidad en el mercado. En México es una desgracia, a la hora que hicieron, por ejemplo, los experimentos del doctor Meli y Hernández Basilio, teníamos una calidad muy buena de piezas, que por una limitación miope de andar, restringiendo la resistencia de diseño B asterisco M a 3.5, y cuando hicieron su regla de 3, los ingenieros se dieron cuenta que nada más necesitaban piezas de 60 kilogramos sobre centímetro cuadrado, pues lo que acabó haciendo es que pues todos los amantes del ahorro pidieron las de 60 y los grandes productores dejaron de producir las buenas, ¿verdad?, porque no hay que salir del mercado. Y entonces, pues eso todavía lo estamos padeciendo, aunque parece que a partir de este siglo está empezando a volverse a mejorar la calidad de las piezas, pero nada que ver con las que teníamos en los años 70. Entonces, creo que eso es importante. También el doctor Schultz propone realizar más investigación como una solución fundamental a mejorar la normatividad sobre la mampostería presforzada, y en ese sentido tiene toda la razón. Los cambios en cualquier norma que se considere seria deben fundamentarse en estudios e investigaciones previas, no en ocurrencias del momento de los miembros del comité de norma. Ahora, lo que quizás se necesite para fomentar un uso más amplio, particularmente en aquellos países que actualmente no se emplea, es lo que se conoce a nivel mundial como los demonstration projects. ¿ya? O estructuras reales muestra. Por ejemplo, esta estrategia se llevó con mucho éxito para promover el aislamiento sísmico en la década de los 90, empleando programas con fondos de las Naciones Unidas, el programa UNIDO. Proyectos de muestra aceleraron muchísimo la aplicación del aislamiento sísmico, no solamente en los países que fueron beneficiados por UNIDO, que fueron China, Italia, Armenia, Chile, India e Indonesia, sino a nivel mundial, ¿ah? Porque pues, las buenas prácticas y la promoción se contagian. De hecho, también a mediados de los años 2000 se inició la promoción de buenas prácticas de mampostería confinadas en muchos países de Asia, ¿verdad? A través de organizaciones de cooperación internacionales, entre ellos muy involucrados los europeos, parte del ERI, y en el Caribe, en Haití, después del sismo de Haití, y el empleo de la mampostería confinada, podemos comentar ahora que es toda una realidad en esos países de Asia, y de hecho, ¿verdad? A mí me da mucho gusto haber sido árbitro de extraordinarias investigaciones que se hacen en Nepal, que se hacen en el sureste asiático sobre mampostería confinada, ¿verdad? Entonces, y bueno, también me está dando gusto lo que están haciendo los haitianos. Entonces, existiendo la materia prima para emplear la mampostería presforzada en todo el mundo, bueno, porque en todos lados se producen piezas de arcilla, de concreto, se puede fabricar el grout, el acero de presfuerzo no es muy difícil de encontrar, bueno, pues me parecería hasta más fácil promover la aplicación de la mampostería presforzada utilizando estas estrategias de proyectos muestra. Por ejemplo, sería interesante tener una escuela de mampostería presforzada en alguna localidad de México, así como la que hicieron y nos enseñó VIX de toda esta parte. Finalmente, pues el doctor Schultz presenta un resumen y conclusiones muy ricas sobre todos los aspectos sobre los que reflexiona en este trabajo propuesto para su ingreso a la academia en México. Entonces, pues básicamente, considero que este es un trabajo de gran calidad. Le agradecemos a Arturo que se haya tomado el tiempo de escribirlo y presentarlo a la academia, y pues te queremos felicitar por tu ingreso a la academia. Muchas felicidades, Arturo.
También.
Muchas gracias, doctor Arturo Tena Colunga. Enseguida le damos la palabra al doctor Bernardo Gómez González.
Gracias. Buenos días a todos. Señor presidente, distinguidos miembros de la academia, colegas, amigas y amigos. Es para mí un honor presentar los comentarios al trabajo de ingreso del doctor Arturo Ernest Schultz, titulado On the Advancement of Pre-Stress Masonry on Structural System. Me parece que nos encontramos ante un documento de gran solidez técnica y madurez intelectual, que no solo revisa el estado del conocimiento sobre la mampostería presforzada, sino que, de manera más importante, propone una reinterpretación profunda de su papel dentro de la ingeniería estructural contemporánea. Durante décadas, la mampostería ha sido considerada un material limitado por su baja resistencia a la tensión. Sin embargo, el doctor Schultz nos recuerda que este no es un defecto insalvable, sino una condición que puede ser resuelta mediante un principio bien conocido en la ingeniería, la precompresión. El preesfuerzo, aplicado de manera adecuada, no busca aumentar la resistencia a tensión del material, sino evitar que ésta se desarrolle. Y en ese simple pero poderoso cambio de enfoque radica la esencia de esta contribución. Y me parece que este concepto es muy bien conocido por todos los presentes en el concreto presforzado. Sin embargo, cuando lo trasladamos a la mampostería, al menos para mí, la verdad es que la lectura de este trabajo fue una gratísima sorpresa. El documento demuestra, con base en evidencia experimental acumulada a nivel internacional durante más de 50 años, que la mampostería presforzada retrasa o incluso elimina el agrietamiento, mejora significativamente la rigidez estructural, incrementa la resistencia a flexión y acortante y, de manera particularmente relevante, permite el cierre de grietas bajo la descarga. Estos beneficios no son teóricos, están ampliamente documentados en investigaciones realizadas en distintos países y bajo diversas condiciones. Otro aspecto destacable del trabajo es la amplitud y profundidad de la revisión experimental. Me parece que nos está dejando una tarea muy importante a todos los presentes para revisar justamente esos trabajos, empaparnos de ellos, entenderlos mejor y generar prácticas en México que nos puedan ayudar en los problemas del día a día que tenemos. El doctor Schultz presenta evidencia consistente de que tanto en elementos como vigas y losas, o sea, vigas y losas de mampostería, como en muros sometidos a cargas fuera del plano o en su plano, el preesfuerzo produce mejoras claras en desempeño estructural. En muros, por ejemplo, se observa un incremento importante en la resistencia fuera del plano, así como una mejora en la resistencia al cortante atribuible al aumento de la fricción inducida por la precompresión. Desde la perspectiva de la ingeniería sísmica, que es particularmente relevante en nuestro país, el trabajo adquiere una dimensión aún mayor. La mampostería presforzada introduce de manera implícita características que hoy asociamos con sistemas estructurales avanzados, y aquí voy a tomar el ejemplo de mi querido Arturo, avanzados, la capacidad de autocentrado, la reducción del daño estructural y un mejor control de las deformaciones permanentes. Pareciera con estas características que estamos hablando de los sistemas que hoy conocemos como de control de la respuesta estructural, disipadores de energía, aisladores, en fin. Pero a mí me gusta recordar, y qué bueno que hay muchos jóvenes aquí, que cualquier elemento estructural, convencional, correcta y sensatamente diseñado, también es un sistema de control de la respuesta estructural. Esto abre la puerta a estructuras más resilientes, con menores costos de reparación después de un evento sísmico y con un comportamiento más predecible. Sin embargo, el autor no elude las limitaciones del sistema. Reconoce con claridad que aún existen desafíos importantes, también ya los está mencionando Arturo en su participación, particularmente en lo que respecta a la disipación de energía y al comportamiento bajo cargas cíclicas severas. Las investigaciones recientes, como el uso de dispositivos disipadores, aleaciones con memoria de forma o elementos elastoméricos, son prometedoras, pero aún requieren consolidación para su adopción generalizada. Quisiera también subrayar un aspecto que considero fundamental, la honestidad técnica del documento. El doctor Schultz identifica con precisión las razones por las cuales la mampostería presforzada no ha sido ampliamente adoptada. Entre ellas, la ausencia histórica de normatividad clara, el desconocimiento en la práctica profesional, la percepción de complejidad constructiva y preocupaciones sobre costos y pérdidas de preesfuerzo. Este reconocimiento no debilita el argumento, por el contrario, lo fortalece. Asimismo, sería deseable avanzar hacia metodologías de diseño más accesibles para la práctica profesional, que permitan a los ingenieros incorporar este sistema con mayor confianza. Más allá de su contenido técnico, esta contribución tiene un carácter estratégico. Reposiciona la mampostería no como un material secundario o meramente arquitectónico, sino como un sistema estructural competitivo, eficiente y en muchos casos superior. Simplemente el hecho de ver a una empresa del tamaño de BSL haciendo mampostería presforzada debería de llamarnos la atención, porque eso nos deja ver que ya no es el material, desde hace mucho tiempo, que solamente implica pegar tabiques, sino que es un material estructural con amplias posibilidades y que con el cual se pueden lograr grandes obras de ingeniería. Para países como México, con alta sismicidad, amplia tradición en el uso de mampostería y necesidad de soluciones económicas, el potencial de este enfoque es particularmente significativo. En ese sentido, el trabajo del doctor Schultz no solo aporta conocimiento, propone un cambio de paradigma. Concluyo. Considero que esta contribución cumple plenamente con los más altos estándares de la Academia de Ingeniería de México. Se trata de un trabajo riguroso, relevante y con claras implicaciones para la práctica profesional y el desarrollo futuro de nuestra disciplina. Principalmente creo que nos provoca a la reflexión, a la discusión constructiva y sobre todo a que la Academia de Ingeniería aporte de manera específica soluciones hacia la práctica profesional. Por todo lo anterior expreso mi reconocimiento al doctor Ernst Schultz, le agradezco porque me ha iluminado de manera sensible en mi conocimiento y respaldo totalmente y felicito a la Academia por la incorporación del doctor Schultz a este grupo de ingenieros. Muchas gracias.
Muchas gracias, doctor Bernardo Gómez González. Le dejo la palabra al doctor JoAnn P.
Muchas gracias, maestro Alberto Lepe, presidente de la Academia de Ingeniería, estimado doctor Arturo Schultz, estimados miembros de la Academia, estimados asistentes. El trabajo del doctor Alberto Ernest Schultz se refiere a la mampostería postensada, mencionando las múltiples aplicaciones que tiene. La mampostería es sin duda el material más utilizado en la historia de la humanidad, lo cual yo lo creo y lo cual creo que es cierto. En muy diversos tipos y piezas. Podemos citar los grandes templos en Egipto, el Panteón, por ejemplo, en Roma, en París, las construcciones prehispánicas en México, las construcciones europeas, etcétera, y sin duda seguirá siendo uno de los materiales más utilizados por la humanidad por su facilidad constructiva, su belleza, y en zonas sísmicas por su buen desempeño estructural. Eso lo hemos podido constatar durante los temblores del 85-2017 en México. Los sistemas de mampostería especificada con respaldos de pruebas de laboratorio y estudios analíticos bien diseñadas, bien concebidas, bien construidas, etcétera, han demostrado tener un desempeño extraordinario. Como bien saben, el sistema de mampostería más utilizado en México es la confinada con refuerzo horizontal y en un pasado reciente la reforzada interiormente, que permite tener un sistema con mampostería aparente. Sin embargo, en México son contados los casos en los cuales se haya utilizado mampostería postensada, habiendo algunos estudios y aplicaciones. En un pasado reciente se hizo un intento por una aplicación de pequeñas piezas con grouts de alta resistencia para hacer mampostería postensada. Sin embargo, pues el estudio no siguió desarrollándose. El doctor Schultz, en su interesante artículo, menciona el desarrollo que ha tenido la mampostería postensada, las investigaciones realizadas, así como la reglamentación existente en varios países, entre los cuales se puede citar Estados Unidos, Nueva Zelanda, India, Colombia, Canadá, entre otros. Dentro de las ventajas que tiene la mampostería postensada se tiene, evidentemente, la disminución de fisuras, resistencia a cargas fuera del plano debido a viento o a empujes de suelo o agua, entre otros. Dentro de las aplicaciones de la mampostería postensada se tienen las siguientes: estructuras de mampostería aparentes, estructuras con claros mayores a los convencionales, que se utilizan en México normalmente, digamos 4x4, 3x3, por ejemplo, para casa, habitación, en zonas de sala, comedor, escuelas, salones de usos múltiples, museos, entre otras aplicaciones. Algo muy interesante que podría extenderse la mampostería postensada es al uso de muros de contención, por ejemplo, bardas, arcos, como ya lo ha mencionado el doctor Schultz. También se menciona la resistencia a fuego que puede aportar la mampostería y la termicidad tanto en climas cálidos como en fríos. En el artículo se mencionan los principios de la mampostería postensada y el desarrollo que ha tenido en varios países, tanto en aplicaciones como en el desarrollo de especificaciones. Por otra parte, la mampostería postensada se puede aplicar elementos prefabricados, disminuyendo la mano de obra y aumentando la calidad, aspecto que ha habido varios intentos en México. En el artículo también se menciona la comparativa en el desempeño a cargas laterales de mampostería postensada con la mampostería reforzada, así como con la mampostería postensada sin mortero de pega. Finalmente se mencionan los retos que se tienen para el desarrollo de especificaciones de la mampostería postensada ante distintas aplicaciones y que se refleja en la norma de diseño. Doctor Schultz, yo me quedo con la siguiente reflexión. Creo que en México debemos de aportar sus experiencias para desarrollar especificaciones y aplicaciones que tenemos para el uso, por ejemplo, de mampostería en aplicaciones de muros de contención, en mamposterías de grandes claros, y me parece que con base a lo que usted ha desarrollado podríamos hacer especificaciones, adaptarlas en México. Como bien sabe, la mampostería que han desarrollado los grandes investigadores que usted ya ha citado, Meli, Hernández Basilio, Alcocer, etcétera, pues tenemos un sistema bastante eficiente, pero no ha habido investigaciones en el campo que usted se ha desarrollado y me parece muy interesante para esas aplicaciones específicas. Yo lo quisiera felicitar por su artículo, muy interesante, lo leí con mucho gusto y bueno, pues bienvenido a la academia. Muchísimas gracias.
Muchas gracias, doctor Raúl JoAnn P. Le voy a agradecer, bueno, pues que nos hayan acompañado, se queda como próximo comentarista también, al doctor Arturo E. Schultz.
Muchas gracias.
Los comentaristas que nos acompañaron y pedirle al maestro Alejandro Vázquez López que pase por acá y al doctor Javier Alonso García Jarqui, si está.
Arturo.
¿Qué hacemos?
Ahora sí.
Gracias.
El doctor Matamoros aquí. Sí, el doctor Adolfo.
¿Estas tarjetas para los tiempos?
Sí. Javier Alonso acá.
Javier.
¿Está bien? El doctor Adolfo Matamoros. Bien, pues en lo que nos acompaña, vamos a presentarlo. A continuación, el maestro Alejandro Vázquez López, que es secretario de la Comisión de Especialidad de Ingeniería Civil, expondrá la semblanza del segundo académico que ingresa el día de hoy, el doctor Adolfo Matamoros Hidalgo. Adelante, maestro Alejandro Vázquez. Tiene usted la palabra.
Gracias. Presentaré una semblanza del doctor Adolfo Matamoros, quien se licenció por la Universidad de Costa Rica en 1989 y sus títulos de maestría y doctorado en Ingeniería Civil por la Universidad de Illinois en Urbana-Champaign en 1994 y 1999 respectivamente. Tras graduarse, trabajó como investigador postdoctoral en la Universidad de Purdue y comenzó su carrera académica como profesor del Departamento de Ingeniería Civil de la Universidad de Kansas, donde enseñó durante 15 años y alcanzó el rango de profesor. Desde 2014 es el profesor Peter T. Flaun en el Departamento de Ingeniería Civil y Ambiental de la Universidad de Texas en San Antonio, donde ejerce como subdirector y director del programa de doctorado en Ingeniería Civil. Durante su etapa en la Universidad de Texas en San Antonio, lideró los esfuerzos para la creación y la acreditación del programa de doctorado en Ingeniería Civil y el diseño y construcción del laboratorio de ensayos a gran escala de la propia universidad. Es el director de financiamiento del Instituto sobre resiliencia urbana sostenible. El profesor Matamoros es un experto en análisis experimental de esfuerzos con 25 años de experiencia de ensayos estructurales a gran escala. Ha realizado ensayos de laboratorio de componentes y sistemas de puentes fabricados con concreto armado, concreto pretensado, acero y materiales compuestos, bajo cargas pseudoestáticas y dinámicas. También tiene experiencia en instrumentación de campo y pruebas de estructuras de puentes. Ha sido responsable de experimentos a gran escala patrocinados por el Departamento de Transporte de Texas en vigas de puentes con hilo de grado 300, anclaje de barras con ganchos, cabezas de gran diámetro y tapas curvadas huecas. Durante su carrera ha liderado y participado en pruebas a gran escala de elementos y sistemas de concreto armado y acero en varios laboratorios del país, incluyendo la Universidad de California en Berkeley, la Universidad de Purdue, la instalación de pruebas multiaxiales de la Universidad de Minnesota, la Universidad de Kansas y el Laboratorio de Ensayos a Gran Escala de la Universidad de Texas en San Antonio. Ha liderado y trabajado en proyectos de investigación para varias agencias de diversa especie en los Estados Unidos, como para el propio Departamento de Transporte en Texas, el Programa Nacional Cooperativo de Carreteras, la Fundación Nacional de Ciencias, la First Energy Nuclear Corporation y Transet. Su trabajo en ensayos estructurales de elementos de concreto armado le ha valido el reconocimiento de miembro del Instituto Americano del Concreto y miembro del Instituto de Ingeniería Estructural de la SCE. Sus publicaciones han recibido premios del Earthquake Engineering Research Institute y de la Structural Engineers Association of California. Ha realizado muchos y diversos estudios que han servido de base para la introducción de nuevas disposiciones de diseño para el anclaje de refuerzos de alta resistencia con ganchos y cabezas para el código del ACI. Y finalmente, bueno, como se ha mencionado, es miembro del American Concrete Institute y del American Society of Civil Engineers. Bienvenido, doctor Matamoros. Gracias.
Está bien. Muchas gracias, maestro Alejandro Vázquez. Ahora escucharemos la ponencia del doctor Adolfo B. Matamoros Hidalgo, que se titula Reconsiderando la metodología para la evaluación sísmica de nivel 3 de edificios de concreto reforzado, utilizando procedimientos lineales en el estándar AC 41. Tiene la palabra.
Muchas gracias, maestro Lepe. Primero que nada, quiero expresar mi gratitud y pues soy muy honrado de haber sido invitado acá. Mi edad formativa en Costa Rica, pues siempre vimos con gran respeto y admiración la Ingeniería de México. Queda en mi memoria grabada la visita del profesor Meli a la Universidad de Costa Rica cuando yo era estudiante. Un ejemplo de muchas personas que siempre hemos admirado y respetado. Colegas en mis épocas de posgrado, como el doctor Tena Colunga, que coincidimos, el doctor Jaime de la Colina, y en mi carrera profesional, el doctor Alcocer, con quien he compartido en muchas ocasiones en comités técnicos. Así que muy agradecido con todos y sin más, pues voy a hacer mi presentación. Al igual que el profesor Schultz, me voy a disculpar y voy a hacer mi presentación en inglés, porque son muchos años de hacer trabajo técnico en inglés y no quiero confundir mi presentación por cuestiones de traducción. Okay, so I'm going to switch to English. Again, I think I may be able to express a little bit the technical content a little bit better in English. The motivation for this work that I presented to the Academy is that as I chaired the 369 S committee, which produces the 369 code that is used for seismic rehabilitation in the United States. And I fear, as chair, I see many proposals come in and go for changes to the code, that we focus a lot of attention on the nitty-gritty, on the small things, on whether this parameter should be adjusted by a little bit. And we don't spend enough time thinking about the validity of the methodology and the concepts behind the methodology. And so this work is aimed at exploring that a little bit in using the existing methodologies for new design, construction of new buildings as a framework, and see where there may be things that we're doing well and we may not be doing so well. So for my introduction, I'm going to provide a quote by Hardy Cross. This was very near and dear to my mentor, Professor Sozen, whom I'd had the honor of working with at the University of Illinois. In it, Hardy Cross states that we have a lot of examples in the literature about work focus on strength. And so he tells us that, and that's the last part that is highlighted. One might almost say that strength is essential and otherwise unimportant. So in that contradiction, Professor Cross is essentially saying we have a duty to design structures that are safe, but the real art of engineering extends beyond that. And this is taken from an essay that is called Standardization and Its Abuse, and it's all about codes and standards. And I think it speaks very appropriately to the topic of my presentation. So I wanted to start that because when we do design for new construction, we do it on the basis of forces. And that means that we have to make some compromises between complexity and simplicity. We also understand that when we design new structures, we can't design them for the expected elastic demand because that would be uneconomical. So we have to allow some level of inelasticity in the structure, which means that we need to have, if we're going to use forces as a construct for design, we need to make some compromises. So on the left-hand side, we have reality. There's a structure that is subjected to an earthquake and it deforms. On the right-hand side we have what we use for design, which is a surrogate model. We use a linear model. Most designs in the United States are done on the basis of linear models. And between the two, we have to make some compromises. There must be some rules. We can't have a very simple model without some restrictions to its use. And those restrictions are very important. And the overall goal of designing new construction, as stated in the ASC 7 standard, is to have a structure that has a very low probability of collapse. So we leave this with several questions that are important. First of all, what are the properties of the linear model? So that is a valid surrogate model to the nonlinear model. And if we're going to design for forces, what is the magnitude of the forces that we design for? That's kind of arbitrary, and it's a complex question. So in the paper that I presented to the Academy, I focused first on a methodology proposed by Professor Sozen and Shibata in the 1970s. It's called the substitute structure method. And in it, they proposed a methodology that is rather complex. It consists of taking every component in the structure and adjusting its stiffness depending on the amount of damage that component is going to incur. So it's a component by component approach. And then the idea is that if the component suffers more damage, it'll be more flexible and it will attract more deformation. Contrast that with what was developed as the basis for the ATC, or was produced by the ATC project. If those of you who are not familiar, the ATC project is the foundation for our modern seismic design codes. And it involved the who is who of earthquake engineering in the United States in the 1970s and 80s. Very wise people. They followed an approach that was significantly simpler. They just, instead of using this methodology of component by component, they just said, we're just going to smear the properties of the structure, consider simple adjustments. In that way, we can obtain a model that is adequate representation of what a nonlinear model would do. So I'm going to start with the rules. So Professor Sosen, in the work that he did with Shibata, set some ground rules. It's like, if we're going to use a linear model, you have to obey certain rules. You can't do that in an unrestricted fashion. And see, so he set these 5 rules in the substitute structure method. The first 2, I think, speak about regularity. That's very familiar to all of us in structural engineering. If we're going to use a linear model as a surrogate for a nonlinear model, we need to use it only for structures that are regular in plane, regular in height, regular in strength. You know, you see the picture there in the upper right. This is a building that was in Puerto Limón in the Atlantic coast. After the 1991 Limón earthquake in Costa Rica, I had the experience to go and do damage surveys after the earthquake as a young engineer a long time ago. And it is a perfect example of how things can go wrong in irregular structures. It shows you it has interruptions in elevation, it has interruptions in plan, all kinds of bad things in it. So it's a pretty clear example of why we don't want linear models to analyze a building like this. Second of all, I think the rule number 3 is about the complexity of the problem. Professor Sosen is setting some bounds. So we're doing a component by component analysis or modification, but it really doesn't make sense to have very different modifications in the same story. So one column making one column significantly different from the other column and so on is overly too complex and unnecessary. Rule number 4 is very important too, and it speaks to the diagram on the bottom right. It says that all components must be properly detailed. The idea is that we need to provide adequate detailing so that the deformation demands remain below the deformation capacity of the components. Because if the deformation capacity of the components is exceeded, we're going to have unstable behavior. That's the broken blue line. And now our model, linear model, is no longer a good representation of the nonlinear model. So things break down. The last is non-structural components must not interfere with structural response. And again, I referred to the picture in the top right, in which parapets created captive columns, and that led to collapse of some of the columns in this building. So that's clearly a problem. Okay, so why have all these rules? Why is Professor Sosen talking about these? And more aptly, what is this business about the deformation pattern in the structure? So when we think of deformations in a building and deformation-based design, we consider different metrics. There are different quantities that we worry about. One is the mean drift ratio. So if you look at the picture on the right, that's a pretty simple depiction. Is just take the displacement at the roof and divide by the building height, and that gives you an average. That's your mean drift ratio. In addition to that, the building deforms in some stories more than the mean, and some stories less than the mean. So there's a distribution pattern to the story drift ratios. So the story drift ratios are important parameters too. Why they're important? So I'll refer you to the two pictures on the left. In the top left, we have, these are two models. One is linear and one is nonlinear, and shows the distribution of drift ratio over the height. And in the case where everything goes well, in all the rules that say you may use a linear model in substitution of a nonlinear model, these patterns have the same shape. And so not only are we matching the mean deformation, but we're matching very much the ratio of the maximum story deformation to the mean deformation. That remains, the ranges of those parameters are about the same. The bottom left picture shows what happens when things go wrong. The linear model retains the same pattern, but in the nonlinear model, there is drift localization. The formation gets focused on a single story. I'm sure you have plenty of examples here in Mexico City throughout the earthquakes where you've seen a soft story. So what I'm saying is, essentially, that the soft story problem is not unique to our perception. I used to have this idea that soft story is, there's an interruption in stiffness or strength over the height. Ultimately, all structures eventually become soft story structures. And that was a little bit of an eye-opening observation for me. But you can see the difference between the blue line and the red line. The red line retains the same pattern. The blue line, all the deformation is concentrated in a single story. And as a matter of fact, in the higher stories, the drift ratios are way lower. So the mean is distorted, and they're introducing a distortion between the linear and nonlinear model. So in summary, there are three metrics. I've talked about two of those, mean drift ratio and story drift ratio. They're important. In the transition from mean drift ratio to story drift ratio, things can go wrong. If we have localization, then those patterns become distorted, and linear models can't reproduce the same deformation pattern as a nonlinear model can. Then, therefore, is no longer valid as a surrogate model. On the furthest right image, we have the component deformation. Professor Sozen, in the Shibata substitute structure method, dabbled with this a little bit. He later himself thought it was too complicated and produced work with Shimasaki and others where he went to a smeared stiffness model. But nonetheless, this is meaningful because this is what we do today in ASC 41. And I will offer more of that in a minute. So we have three types of metrics. The first two I would consider and call global metrics. The third one I call local metric, a component metric. Okay, so let's revisit the set of rules that Professor Sozen gave us for the substitute structure method. This made its way through ATC 3, which produced rules that were fairly similar, made it into what is today ASC 7. But along the way, there were a couple of additions that are highlighted there in red or orange. The first one is the column to beam strength ratio. And so there's a significant amount of work that has been done on this. The ACI code now has a provision that says that the column to beam strength ratio must be at least 1.2. Dr. Browning, who's sitting here in the back, wrote a very fantastic paper on the topic and found that that number needs to be as high as 4 in order to develop a full height structure mechanism. My dear friend Joe Bracci from Texas A&M wrote another in which he advocated for increasing that number up to 2. And the whole idea behind that is to prevent that drift localization in a single story and spreading the deformation so that the columns don't become triggers for drift being localized in a single story. So that was an addition that is important in what we do for design of new construction. Second one is in ASC 7 today, there are limits. And they say you shall design your structure, you shall compute your deformations, and you must check that your deformations, your story drift ratios remain below a specific limit, 1.5 or 2%. And the idea behind that, the concern, was that even if the deformation patterns are adequate, if the deformation is too big, P delta effects can take over and they can cause the collapse of the structure. But even more so, we agree that because we're not using a column to beam strength ratio of 4 or not even 2, that means that we're allowing some drift localization, little bit of a soft, we're dipping our toe in the pond of the soft story mechanism. And the way that we control that in new construction design is by establishing a hard limit on the drift ratio. Okay, why is that important? And again, I'm just setting a ground for the rules for new construction in the hopes that later I can compare and contrast what we do for existing construction, in case you're wondering. So how do we do new construction? What is the ASC 7 ACI 318 methodology? We build design spectra from single degree of freedom oscillators, right? Single degree of freedom oscillators, it seems silly, but they have only 1 degree of freedom, and we're designing buildings with many degrees of freedom, so that's kind of a bit of a problem there. So the first thing that we do is we go back to the initial dilemma. We don't want to design the structure for the elastic capacity. It's too expensive to do that, too complicated. So the ATC founding fathers agreed on R factors by which we reduce the elastic forces and we design for reduced forces. R factor is kind of an indication of how much inelasticity we're willing to allow in the structure. So the larger the number, the more inelasticity we allow, the lower the forces we design for. But now engineers like us, which are very comfortable designing for moments and shears and loads, now we can go in our way and design our structure on the basis of forces. We don't need to wrestle with deformations. But when we introduce the R factor, we introduce a distortion, because artificially we're designing for forces that are lower than the demands that the structure will see. And so we need to adjust the deformations that we calculate with those reduced forces to get back to what the expected deformations are. And so we use in ASC 7 C/D factors, we amplify the deflections. That is important because we use those to check that drift limit. And so that we don't exceed deformations and we don't put the structure at risk due to P delta effects or story instabilities. Okay, so all of this for new construction, like I said, just laying the groundwork. Let's talk a little bit about seismic assessment. And seismic assessment is done in several different ways. On the left is the simplest way, checklist, observations from things that have gone wrong in previous earthquakes. And so people can go and check for these deficiencies in structures. There's no need to build a structural model. Mathematics implied are very little. So this is the low-tech approach. Nonetheless, it is the wisdom approach. It's like where we failed in the past approach. So we learn from our failures, and this is a way to make sure. As a matter of fact, ASC 41, today there is a debate on whether this should be mandated as a means to make sure that structural engineers don't overlook some of these deficiencies in their modeling and with more complex approaches. There are other examples of methodologies like these, ratio of floor area to structural component area, and so on, where very simple metrics are used to determine whether a structure is safe or not. Then there are countries that have put all their eggs in the basket of drift control, meaning that if you limit the computed drift ratio to a low enough value, then everything else would take care of itself. The deformations will not be large. That means the story drifts will not be large, and the component deformations will not be large, and the structure will be safe. You folks in Mexico do that. The Japanese are very strong in this method. It involves a greater effort, right? But it gives maybe a more nuanced answer. And then on the right is what we do in the ASC 41 standard, which is the standard that is adopted by most jurisdictions in the United States for seismic assessment. In this case, we have an approach. It is a performance-based engineering approach in which, again, I must say there are different tiers of assessment. This is the more complex, so I'm going to the most complex approach in the United States. That means you shall build a model of the structure. There are rules on how to build that model, so you have to follow the rules for building your model. You compute the response on the basis of that model, and then you compare with acceptance criteria. So you can adjust your level of hazard and check if you meet acceptance criteria. The combination of acceptance or performance level and level of hazard give you a performance objective. It's complex, and it also tied to the reality that most seismic assessments in the United States today are done on the basis of linear analysis. So this methodology, I think, was envisioned from people who were thinking of nonlinear dynamic analyses. But in order for it to be applied, there had to be some compromises in implementing it day to day for linear analyses in a simpler way. And this is what they came up with. So we begin with calculating a base shear on the basis of single degree of freedom oscillators. In this case, we use the coefficient method. And I'm just going to mention this and run. The coefficient method is derived as a means to estimate what is the expected deformation in a structure. It's not, those coefficients have nothing to do with force, and yet we embed them into a base shear calculation. That has implications, but we'll leave those for another paper. We take those forces, elastic forces, we haven't reduced them by any R factors like we do for new construction. So is the elastic force. We applied that to a linear model. Of course, that's going to give us very large forces. And we didn't want that for new construction. We sure as heck don't want that for existing construction. So what do? We're going to take those component forces that we computed with our linear model under elastic forces, and we're going to reduce them, those component actions, using what is called an M factor. An M factor is an analogous concept to an R factor, except that the M factor is intended to be different for every component. The R factor is one R factor for the entire structure. So the main idea or concept behind an M factor is that the ratio of the deformation capacity to the deformation at yield is the same as the ratio of the elastic force, the force that you compute in an elastic system, to the force at yield or the capacity of the member. There is this relationship that says inelasticity expressed in terms of deformation is equal to inelasticity expressed in terms of force. Again, we do this because we're trying to be concerned or aware about the vulnerability that is tied to deformations, and we want to bring this back to forces because we're comfortable with forces. And lastly, then we compare those reduced component actions through M factors with the capacity to calculate demand to capacity ratios. So just in summary, differences and similarities, linear procedures, which is the focus of this paper. They both implemented in ASC 7 and ACI 318, also implemented in ASC 41 and ACI 369. One is for new construction, the other one is for existing construction. There's a parallel between the two. ASC 7 and 318 have a whole list of restrictions. We already went through the table that had all those limitations that you have to abide by if you want to use a linear model as a surrogate for a nonlinear model. In ASC 41, situation is much more loose. A lot of these restrictions do not exist. So there's a lot of emphasis and concern about regularity. So there's agreement between the two right there. And there are some restrictions in terms of the ductility of the members. If the members are, the deformation, demand to capacity ratios are too high, then it prompts you to move to a nonlinear analysis. But that's about it. So we got curious about this. We did a parametric study using moment frames. I'm going to describe very rapidly how the parametric study was structured so you have an idea what the conclusions mean. So we had families of frames of different heights. For each frame height, we had multiple configurations of frames. All of those we model with a lump plasticity approach. We did literally hundreds of thousands of these. So I know people get critical and say you could build more complex models, and they're absolutely right about that. But when you're running the cluster system at UT San Antonio nonstop for an entire summer, if you increase the complexity significantly, people get very angry at you. And the same is true for TAC at UT Austin, I'm sure. So it's a compromise. Like I said, these were modeled with zero length nonlinear springs, signifying rotation. All the models were built using ASC 41 rules. We focus on mid-rise structures between 5 and 17 stories. If the structures are stiffer, they'll end up in the nearly constant acceleration region. There are different sets of rules for structures that are very stiff. And then, experience has shown us that if we put a lot of walls in a building, it's really not that important if our detailing is not great, because the deformation will be so small that it will erase a lot of mistakes. Where we get in trouble and where the collapses occur is in that middle region that is shown in white. Because flexibility means larger deformations. Larger deformations means a greater chance that something will go wrong on our structure, will get us into serious trouble. And then we're going to leave out the range of the really, really flexible structures, because those are primarily concerned for wind design, not so much for earthquake design. They just simply become too flexible for the frequency content of the ground motion to be a concern. How do we model this? So when we look at rules for seismic detailing in the United States, UBC 67 and ACI 31871 are two really influential documents that sort of signify the transition between old detailing and inadequate detailing in modern detailing. So if I go and adopt detailing rules from ACI 31871, there are going to be differences with what we have today in 31825, but in terms of the behavior of the structure, those are unlikely to be catastrophic differences. But when I go in abide for deformations or detailing rules that don't meet UBC 67, those are the structures that are going to be in trouble, right? That's not by mistake. Engineers were there allowed to do their detailing based on their own opinions and thoughts on how structures should be detailed. So you have a wide range. You have structures that were at very good detailing, even though they're very old. You have others that don't have very good detailing. So we created 4 different categories of detailing. That was one of the salient parameters of the study. We had category 1 through category 4. Just to make it short, category 1 is equivalent to a structure that is modernly detailed, may miss a few things, but meets all the important criteria. And then when you go to 2, 3, and 4, things get progressively bad. In category 4, the spacing of the transverse reinforcement is approximately equal to the member size, which you think is crazy, but you do see it in some structures in California. So 4 is absolute worst. And then the graph on the right is an indication of deformation capacity for each of those 4 categories. So the higher up you are, the more deformation capacity you are. Level 1, you see the blue markers are higher in mean than the red markers on the right, which is the worst quality of detailing, very little deformation capacity. And these are hysteretic curves for level 1, 2, 3, and 4. The top are beams, the bottoms are columns, and you see how for level 1, which is the best, we see nice fat hysteresis loops in the computer models. On the right-hand side, especially in the columns, the bottom right, when we have very poor detailing, those loops have very little deformation capacity and are going to lead to building collapse very soon. So to do this parametric study, we also considered the seismic hazard. We chose a location of high seismicity. So this is a location in Los Angeles. And we pulled the spectral parameters for that location. ASC 41 has 4 different levels of earthquake that are considered for seismic rehabilitation. BSE is common to all of them. 2 is for higher intensity, 1 is for lesser intensity. N is for new construction, E is for existing construction. So 2 is higher than 1, N is higher than E. So we have 4 different levels. And then we wanted to do statistical studies, so we use a P695 methodology, which means P695 is a document. It gives a list of ground motions. In our case, we use far field ground motions, 44 ground motions that would have to be scaled to match the spectral shapes for each of the hazard levels. So there are the 4 spectral shapes that we consider. It shows you all the way from BSE 2N, which is the blue one at the top, to BSE 1E, which is the purple one at the bottom. It's the lowest meeting the criteria. And then, as we said, we scale ground motion. So for each ground motion, we calculated a spectrum. The figure on the right shows what happens when you calculate 44 different spectral shapes. They have a mean or a median response, which is shown in blue. And then there is a spectral shape that signifies the site hazard. So for each individual frame, we computed the main period of the frame, and we scaled the mean or the median response spectra to the ordinate of the spectral shape at the period of the frame. So this was done individually for each of the frames that were analyzed. And that created our set of response analysis, a lot of scaling for each of the frames. So we run a number of different scenarios. We run linear analysis, we run nonlinear analysis. We did linear time history, we did linear static analysis, and the same in terms of nonlinear. We did nonlinear dynamic and nonlinear static analysis. And the idea behind this was to compare what happens when you when you do a seismic assessment based on a linear model versus what happens when you do it on the basis of a nonlinear model. So I don't know how to make that movie work. Is there any, I see. I see the mouse. Okay, no? So that's that. We may have to go without the nice movies here. Okay. Apologies for that. But these will show animations of the frames as the ground motions work their way through the frames, and you see each hinge has a color. So as the ground motion progresses, we keep track of the deformations in each of the hinges, and they will change in colors until we achieve collapse of the building, which occurs when the deformation concentrates in one or two of the stories. So a short version of what you're missing there. So that allows us to compute collapse probabilities. We have a frame, 64 ground motions scaled, and so we run the frame 64 times. We count the number of times in which the building collapses, divided by 64, that gives us the probability of collapse. So first question that is focused on collapse probability, I go back to the rules of ASCE 7 and ACI 318. Rules 2 and 4, all structural joints must be reinforced detailed to avoid significant strength decay. Calculated drift ratio must be sufficiently small to prevent excessive damage and P delta instability collapse. The probability of collapse probably speaks more than 4, more to restriction 4. But in this case, we're also looking at the influence of detailing quality on the probability of collapse. It speaks a little bit about restriction too. So when you run all your, these are for 5-story frames, you run all your scenarios. You see at the top the drift profiles. So those are displacements over heights. The black line shows the mean response. And from left to right, you're going from better quality of detailing to worse quality of detailing. And what you begin to see is patterns where the individual lines begin to show kinks. And when you have a kink, is because the deformation is localizing in a single story and you develop a collapse mechanism. The bottom image is the same, but now instead of showing lateral drift, I'm showing drift ratios. So again, there's a black line and 2 red lines. Black line is the mean. The red lines represent mean plus minus 1 standard deviation. And so as you move from better detailing on the left, you see drift patterns that resemble linear model drift patterns. They're very much coincide with the same shape. But when I get here all the way to the right, you begin to see that the first story values have moved significantly to the right, indicating that we're seeing a very large number of cases where the deformation is localizing in the first story and we're getting collapses due to story mechanisms. And at the same time, the upper stories, the drift ratios are moving to the left. So the deformation demand on the other stories where the collapse is not occurring is actually getting smaller. So this is the same presentation, maybe a little bit cleaner. Black lines represent nonlinear analysis models, whereas the colored line represent different types of linear elastic models. And again, upper left means good quality of detailing. The shapes are somewhat similar. This is for very strong shaking though, so you're starting to see quality of detailing, the black lines in the upper left image. The squares are good detailing. The shape matches really well the colored shapes. By the time you get to the triangles, which is the poor quality of detailing, then that deformation pattern has skewed to the right and you begin to see drift localization. This is the same case for different intensities of shaking. So even when you have low intensities of shaking in the bottom row, you see that drift localization. The linear elastic models are developing smaller drifts, but retaining the same pattern. The nonlinear analysis models are showing indications of drift localization even at low intensities of shaking. So back to the probability of collapse. You take, for every frame you run the 64 or 44 ground motions, you count how many of them produce collapse. And that gives you 1 point in that chart. You do that for every model, for every intensity of shaking, every quality of detailing, and that gives you all the points in that graph. So on the y-axis, we have the probability of collapse. On the x-axis, we have the drift ratio that you compute, the maximum drift ratio that you compute from a linear model. And what we see for level 1, that's best quality of detailing, upper left, is that if the mean drift ratio remains below 2%, the probability of collapse is really, really small. That's very consistent with the rules that we have for new construction. Detail the structure well and keep the drift ratio below 2%, and the structure will have very low probability of collapse. It works, shows that we're good. On the bottom right, as we move from level 1 to level 2, level 3, and level 4, the probabilities of collapse are increasing as the quality of detailing gets worse and worse. And not only that, but if you look at the bottom row, we get to the point where the probabilities of collapse are extremely high, even at 2%, when the mean drift ratio is at 2%. We don't have any points lower than that because we didn't include structures that were stiffer in the study. We stayed away from that. So that's an area of study for future cases. But the probabilities of collapse are getting higher. The scatter is getting higher. So there are two problems to this. One, bad detailing means we have a higher probability of collapse. Number two, bad detailing means that the behavior is more unpredictable. So that notion that we can use a linear model as a proxy for a nonlinear model, as a surrogate for a nonlinear model, begins to be in shakier and shakier ground as our quality of detailing gets worse. Let's talk a little bit about drift localization. We're getting here in the final straightaway. I promise you, I won't stand between you and lunch for much longer. So again, I go back to that original list of requirements that are used in new construction. Again, we emphasize the quality of detailing is important. And then number three, in this case, we revisit this concept of beam to column strength ratio being greater than 1. This is not a requirement currently in ASC 41. There's nothing that says that if you have a weak column, strong beam structure, you're not allowed to use a linear model. Or that tells you, what that beam column strength ratio should be in order for you to use a linear model as a proxy. And so again, this theme is recurring. This is for 17-story buildings. I wanted to bring up here the case of the 17-story buildings because it emphasizes the story a little bit more. On the left, we have the best case scenario, adequate detailing, low hazard, all the frames regardless of story heights. So there you have 5 all the way up to 17. They all have regular patterns that are similar to what you get from a linear model. When you have inadequate detailing and high hazard, then you get drift localization in every frame, regardless of the number of stories. The ugly problem shows up. And we all are well aware what happens when we have drift localization. Again, this is a building from Costa Rica from 1991. There are many here in Mexico City that have experienced the same fate, some of which I can find in YouTube today and that show me the building collapsing. So this is a significant problem. So I wanted to look this through the lens of different metrics. First I'm gonna go and look at this through the perspective of global metrics. I have 4 columns. Hazard is strongest on the left and weakest on the right. And here, I'm just looking at the ratio of mean drift ratio that I compute with a nonlinear model versus the mean drift ratio that I compute with the linear model. So this is a comparison of linear versus nonlinear on the basis of mean drift ratio. And if you look at the left, for the strongest shaking, you see that in a well-detailed structure, that ratio is about 1, it's 0.9, which means deformation the mean deformation is about the same in a linear and nonlinear model. Life is good. When you get to the purple bar, that ratio is about 0.7. That means that the mean drift ratio in a nonlinear model is lower than the mean drift ratio on a linear model, which seems a contradiction in terms, right? But what is happening is illustrated in the two figures on the right. The blue line is represented by the top graph, where the deformation patterns are about the same, the means are going to be about the same. The purple bar is represented by the figure on the bottom, and in that case, there is drift localization, so you have a lot of drift in the nonlinear model in a single story. All the other stories have a low, very low amount of deformation. The mean is the average of all of them. So like, for example, if you have a 17-story building, you have 16 stories with very low deformation, 1 story with very large deformation. The average of 1 versus 16 is a low number. And when you have a good deformation pattern, like the red, the mean is higher because the deformation is uniformly distributed over the height, which is what we want to achieve. This is our objective when we design new buildings. So the mean drift ratio begins to break down as a metric when you have this problem of drift localization. This one shows drift localization in the context of nonlinear systems with different levels of detailing. So we have each set of bars corresponds to a different number of stories. Blue lines correspond to well-detailed structures. Purple lines correspond to poorly detailed structures. So blue line is showing me, for example, in the upper left for high shaking, that the maximum drift ratio is about 1.3 times the mean drift ratio. That's a number that I think a lot of us think in our heads when we're designing new buildings, 1.3 to 1.5, from maximum story to mean. When we get to a poorly detailed structure, that ratio was approximately 1.8 or is approaching 2. It's a much more larger number. And it gets larger, the difference gets greater as the number of stories increases. So it's not only a question of detailing, but it's also a question of the number of stories. And by the way, Dr. Browning's paper showed the same thing for column to beam strength ratios. The problems get worse as the number of stories get higher. So all of this is to say we have a problem because we don't have rules in ASCE 41 to account that the deformations, the maximum deformations are going to be higher in taller buildings. They're going to be higher in buildings that don't have adequate column to beam strength ratios. They're going to be higher in buildings that have poor detailing. All of those things we're just throwing by the wayside, where we should be either setting restrictions or telling people you're going to need to amplify the deformations that you calculate from the linear model by an additional amount when you evaluate them. Then there's the question of local metrics, because all of this is done element by element in ASCE 41. So we revisit the concept of the M factor, which is the R factor, but component on a component by component basis. So with all these studies, we took, for every structure, we actually computed those two ratios, the deformation ratio, delta U over delta Y, and we computed FU over FY. And we plotted them against each other to see how they vary. And this is what came up. So in a nutshell, every point that is below the line is a point where the deformation ratio is lower than the force ratio. And in those instances, the method is providing a conservative estimate of the deformation demand or deformation on the member. Every point that is above the line provides an unconservative estimate. And so top row is beams, bottom row is columns. If you look at a well-detailed structure, beams are mostly under the line, so it's a conservative approach, which I think is the intent. Green lines kind of like are there, maybe clumping around, but they're doing okay. When we get to level 4 detailing on the right, shown in red, we have a significant amount of scatter and a lot of points have migrated to the top. So poor detailing means that our metric is breaking down and is not being conservative anymore. And the problem in the columns is far worse than the problem that we observed in the beams. Contrary to that, we've done a lot of work at UTSA on this reinforced concrete building in Van Nuys. There are people in this room who work in the analysis of this building too. And the whole point is that we've computed the response. This was done for the ITG4 project. And the circles in that graph show the calculated deformations over the height of the building. The lines show the calculated deformation profiles for different models. This building had some masonry walls in the first story, so the red one is when those infills are neglected, is more flexible, and the others, the infills are considered, is stiffer. And we see that we can obtain very good estimates of the deformations in this building using ASC 41 rules. So global metric worked really well. This is the same comparison of drift ratio computed in the first story for the ASC 41 nonlinear model versus the measured values. And even as a function of time, we can obtain very good, very close matches. So global metrics work really well. Local metrics, not so well. And one last point that I want to make, this image on the right here is an equation to calculate deformation capacity of beams, something that I would like to introduce into ACI 369 code. I have to write the code change proposal, submit it, and take people's criticism on it. But that's kind of unimportant at this point. That's why I'm not even showing the equation. What we have is the ability of the model to calculate rotation versus the amount of reinforcement. So there are two parts to this. On the left-hand side, we have members with very little amount of reinforcement, and you see that the scatter is higher. On the right-hand side, the right circle shows members with a lot of reinforcement. The scatter is lower. Steel gives certainty. It reduces uncertainty. And yet, when we think of models like these, we think of a single metric to define uncertainty. We say the uncertainty of the model, the standard deviation for the model is X. We don't say is X for low amounts of reinforcement and Y for high amounts of reinforcement. So when we have methodologies like these, which are performance-based, in members that are very lightly reinforced, the deformation capacity is small, so differences between immediate occupancy, life safety, and collapse prevention compress. They're all closer to each other. The scatter, the standard deviations increase. So they're going to get to the point where these lines start to be on top of each other. You can't tell with any certainty whether you're achieving life safety in collapse prevention or even immediate occupancy. It becomes it's an illusion of accuracy that we don't really have. If we apply the same concept to a well-detailed structure. These things are further apart. We have much larger deformation capacity to work with, so each point is separated by a greater distance. The standard deviation is smaller, so there's much greater certainty in the outcome. Okay, so to finish, this is a long quote. In it, Hardy Cross is essentially saying standards are created as a means to be able to reproduce work, so you can provide a little bit of training to engineers. They don't have to be experts in the topic, and they can produce repeatable outcomes over and over again, right? And so he talks about an assembly line of brains. And I think that with our performance-based methodology and the way we apply it through to linear analysis, we've created a standardized or an assembly line of brains. And we are focusing too much on making minor adjustments about what each parameter is, without spending enough time in thinking, is this giving us the outcome that we want? So when we compare ASC 41 ACI 369 methodology to the 318 ASC 7 methodology, there's some important differences that come up in that we need to pay attention to. One, in ASC 41, we don't have a limit on deformation for linear analysis. We don't say if you have a mean drift ratio, if your computed mean drift ratio is 2% or higher, you can't use a linear model. Yet we set that expectation for new construction. To me, that seems horribly inconsistent and quite concerning. We don't adjust for column to beam strength ratios. We don't adjust for quality of detailing. All of those are triggered for localization that are controlled in new construction through the limit of column to beam strength ratio and through requirements on quality of detailing. So you have to meet those in order to be able to use a linear model. Here, we don't have those restrictions. That's also a source of concern and something that should be looked at so that people don't get too rosy a picture and think that a structure is okay when it's not. It is important to think a little bit closer about this ASC 41 linear procedure methodology. It is a sequence of steps where people were trying to bridge the gap to get from one step to the other, but I don't think there was ever an effort to understand whether all these steps taken in conjunction work together well. And when we do come up with a methodology, we also need to think about the level of certainty that we have in the metrics that we're using. And so we should place greater emphasis for linear models and global metrics, like is done in ASC 7 and ACI 318. We should be thinking of drift ratios, story drift ratios. I don't think that it is productive to center a conversation in component to component. In even cases where you might have 5 different columns in a story that have 5 different M factors, that flies in the face of 318 and ASC 7. It flies in the face of the substitute structure method as Susan postulated it. So again, the concern is that these force-based metrics convey a level of certainty that is not there. So we need to be rethinking. We need to be rethinking, and in this case, I think it's important to start to give up our comfort in designing for forces and focus on displacements. And we need to focus on doing or using metrics that are more reliable and simpler. That doesn't mean that we have to give up performance-based engineering. It means that we need to rethink the way that we're using performance-based engineering. So with that, thank you very much.
Pues muchas gracias, doctor Adolfo Matamoros, por muy completa e interesante presentación, y enseguida tendremos la intervención de los comentarios. El primero de ellos, el doctor Bernardo Gómez González, académico titular de la Comisión de Especialidad de Ingeniería Civil. Adelante, doctor.
Gracias, presidente, nuevamente. Bien. Pues es para mí un honor también presentar los comentarios al trabajo de ingreso del doctor Adolfo Matamoros, titulado Reconsiderando la metodología para la evaluación sísmica de nivel 3 de edificios de concreto reforzado, utilizando procedimientos lineales en el estándar ASCE 41. Nos encontramos en un trabajo con una profundidad conceptual y una relevancia práctica muy importante, que aborda uno de los temas más sensibles de la ingeniería sísmica contemporánea, la validez de los procedimientos lineales para evaluar estructuras que por definición responden de manera no lineal durante los sismos severos. Hay que recordar que el código o el estándar ASC 41 se refiere a procedimientos de evaluación y no de diseño. Se distingue de este al AC7. Hago la aclaración porque en ocasiones en México no distinguimos y más bien confundimos y mezclamos el objetivo de cada uno de estos documentos. Comenzaré por los puntos que considero más importantes sobre el trabajo del doctor Matamoros. El doctor Matamoros nos recuerda algo que, aunque sabemos, no siempre aplicamos en la práctica. El daño sísmico está gobernado por las deformaciones, no por las fuerzas. A partir de esta premisa, el doctor Matamoros construye una crítica sólida sobre el estándar ASC 41, en el cual el desempeño estructural se evalúa principalmente mediante relaciones entre demanda y capacidad en términos de fuerza, ajustadas mediante factores asociados a la ductilidad de los elementos. El problema, y aquí radica la contribución fundamental del trabajo del doctor Matamoros, es que este enfoque deja de lado explícitamente las demandas de deformación, que son precisamente las que controlan el daño, la degradación y en última instancia el colapso. El documento expone con gran claridad una contradicción que ha acompañado a nuestra disciplina durante décadas. Diseñamos estructuras para comportarse inelásticamente, pero seguimos evaluándolas utilizando modelos lineales basados en fuerzas. Para resolver esta contradicción, la práctica ha recurrido a simplificaciones como los factores R, que como ustedes saben en México es el equivalente al factor de comportamiento sísmico y al factor de sobreresistencia, los factores Sede, que son para regresar o para llegar al desplazamiento inelástico a partir de lo que calculamos elásticamente, y en el caso del ASC 41 a los factores M. Sin embargo, como bien señala el autor, estas herramientas solo son válidas bajo ciertas condiciones muy específicas, que no siempre se cumplen, especialmente en estructuras existentes. Uno de los aportes más valiosos del trabajo del doctor Matamoros es precisamente la identificación de estas condiciones. El doctor Matamoros establece, nos recuerda precisamente, que los modelos lineales solo pueden considerarse representativos cuando se cumplen, entre otras, las siguientes 4 premisas: que la estructura sea regular, que los elementos estén adecuadamente detallados para comportamiento dúctil, que existe una relación favorable entre resistencia de columnas y vigas y que las deformaciones se mantengan dentro de ciertos límites. Aquí tal vez el doctor Matamoros nos está trayendo una mala noticia para algunos de los aquí presentes, quienes estamos trabajando en las normas y que nos estamos devanando la cabeza entre qué preferenciamos, si el cuidado de la regularidad, si el control de las deformaciones, y aquí el doctor Matamoros nos está recordando que no es ni una ni otra, sino que son ambas, más un correcto diseño y una correcta conceptualización de la estructura que estamos concibiendo. Estas condiciones que en el diseño de estructuras nuevas suelen satisfacerse, no siempre, pero la mayoría de las veces sí, no están garantizadas en edificaciones existentes, que son precisamente las que evaluamos con mayor frecuencia. El trabajo presenta evidencia particularmente contundente sobre este punto. A partir de estudios recientes, se demuestra que en estructuras con deficiencias de detallado, como muchas de las que existen en nuestros países y en México no es la excepción. Los modelos lineales pueden subestimar de manera significativa la demanda real y además presentan una gran dispersión en sus resultados. Esto nos lleva a uno de los temas más relevantes del documento, la localización de las distorsiones de entrepiso. El autor muestra que en estructuras vulnerables la deformación puede concentrarse en uno o pocos niveles, lo que conocemos como sistemas de piso suave, generando demandas locales mucho mayores que las estimadas para modelos lineales. En estos casos, la relación entre la distorsión de entrepiso máxima y la distorsión de entrepiso promedio se incrementa significativamente y los modelos lineales dejan de ser representativos del comportamiento real. Este punto es crítico porque implica que el uso indiscriminado de metodologías lineales puede conducir a evaluaciones no conservadoras y, por lo tanto, a decisiones de rehabilitación inadecuadas. Otro aspecto que merece destacarse es la crítica a nivel de detalle del enfoque del ASC 41. El estándar propone el desempeño a nivel de componente individual, utilizando factores M derivados indirectamente de la capacidad de deformación. Sin embargo, el trabajo demuestra que existe una alta variabilidad en la relación entre fuerzas y deformaciones a nivel de elemento, particularmente en columnas, lo que introduce un nivel de incertidumbre que no es consistente con la precisión aparente de los criterios normativos. Desde la perspectiva de nuestro país, este trabajo adquiere una relevancia aún mayor. En México contamos con un amplio universo de edificaciones existentes, muchas de ellas construidas antes de la implementación de criterios normativos modernos de detallado sísmico. En este contexto, la aplicación directa de metodologías como el ASC 41, sin considerar sus limitaciones, puede implicar riesgos importantes. Aquí tal vez el trabajo que nos está presentando el doctor Matamoros le guste mucho a algunos colegas o a varios colegas que hoy por hoy han hecho un trabajo importante para que en México se desarrolle desde hace 10 años los análisis no lineales. Y me parece que en México, desde hace unos 10, 11 años, hemos tenido un auge de análisis no lineales. Creo que prácticamente cualquier despacho que se respete en México tiene 1, 2, 3, hasta 4 especialistas, jóvenes principalmente, que llevan a cabo los análisis no lineales, pero para algunos de nosotros este auge que hemos tenido en México sobre este tipo de análisis pudiera estarse convirtiendo en una pandemia, porque tal vez el hecho de que tengamos tantos análisis no lineales yendo y viniendo para diseñar en algunos de los casos es precisamente la señal del que algo tal vez no estemos haciendo correctamente. En este contexto, la aplicación directa de las metodologías como el ASC 41 sin considerar sus limitaciones puede implicar riesgos importantes. El trabajo del doctor Matamoros también pone en evidencia una diferencia conceptual relevante entre enfoques internacionales. Mientras que en Estados Unidos se ha privilegiado históricamente un enfoque basado en fuerzas, en países como México y Japón se han adoptado criterios más estrictos en términos de deformación, lo cual resulta más consistente en el control del daño. Aquí el doctor Matamoros está siendo muy generoso, pienso que así es, en México lo podemos constatar. La distorsión máxima que estamos utilizando en nuestros diseños es del 2%, justamente el límite inferior que mostraba el doctor Matamoros en sus gráficas, pero es en edificios nuevos. En los edificios existentes sí pudiéramos tener niveles de distorsiones que pudieran andar entre el 4 y el 5%, tal vez los mayores ya no los tenemos porque el sismo se encargó de quitárnoslo de enfrente, pero eso no quiere decir que estemos entendiendo claramente lo que estamos haciendo. Es un poco de lo que comentó al final el doctor Matamoros. Tal vez el objetivo de sistematización de los procesos de diseño se ha logrado, pero hay casos específicos, y son los que nos pueden generar problemas, en donde no estamos entendiendo correctamente lo que estamos haciendo a través de nuestros procesos de diseño. Quiero aprovechar la oportunidad para resaltar el uso adecuado de la instrumentación en edificios existentes que recupera el doctor Matamoros en su trabajo. No es uno de los objetivos del trabajo del doctor Matamoros, pero permítanme rescatarlo por lo siguiente. La instrumentación es una herramienta que aporta datos, que sensatamente utilizados generan información que coadyuva, no suple, a las evaluaciones numéricas y analíticas en la evaluación de las estructuras. En el trabajo serio de la ingeniería no caben las soluciones mágicas ni las falacias económicas. Para concluir, el trabajo que hoy nos presenta el doctor Matamoros no es solo una revisión crítica de un estándar técnico, es una invitación a reflexionar sobre los fundamentos de nuestra práctica profesional y es la parte que yo rescataría principalmente del doctor Adolfo Matamoros. Nos obliga a cuestionar si los métodos que utilizamos realmente representan el comportamiento de las estructuras que pretendemos evaluar. Y sobre todo, nos recuerda que la ingeniería estructural no puede reducirse a la aplicación mecánica de procedimientos normativos, sino que requiere criterio, juicio y comprensión profunda de los fenómenos que modelamos. Considero que esta contribución cumple ampliamente con los más altos estándares de la Academia de Ingeniería de México. Por ello, expreso mi reconocimiento al doctor Adolfo Matamoros y mi agradecimiento porque nuevamente nos invita a reflexionar, a pensar y a satisfacer también nuestras inquietudes que tenemos sobre lo que estamos haciendo. Muchas gracias, doctor, y felicidades.
Muchas gracias, doctor Bernardo Gómez González, muy claro. Le vamos a dar la palabra y va a participar en línea, a ver si no hay fallas, del doctor José Manuel Jara Guerrero, los operadores.
Muy buenas tardes, no sé si me escuchan.
Sí, le escuchamos bien. Adelante,
Muy
doctor.
bien. Muchas gracias. Con su venia, señor presidente, muy buenos días a todos los asistentes. Inicio con una disculpa por no poder estar con ustedes de forma presencial. Me siento muy honrado de participar en este acto protocolario junto a mis distinguidos colegas de la Academia de Ingeniería. Quiero agradecer la distinción que se me otorga por invitarme a participar como relator del trabajo de ingreso del doctor Adolfo Benjamín Matamoros Hidalgo. En particular, agradezco también al doctor Sergio Manuel Alcocer Martínez de Caso por su amable invitación. Bien, saludo y doy la bienvenida al doctor Adolfo Benjamín Matamoros. Para su ingreso a la Academia de Ingeniería, el doctor Matamoros presenta un trabajo original con una profunda reflexión sobre las metodologías de evaluación detallada de edificios de concreto reforzado, particularmente existentes, señalada en los documentos de la ASCE 41, la Sociedad Americana de Ingenieros Civiles. Se inicia el trabajo describiendo la filosofía de diseño basada en fuerzas que se utiliza todavía profusamente en muchos países del mundo. En algunos empieza a haber algunos cambios, como se mencionaba en la participación anterior, pero creo que en términos generales sigue usando en todo el mundo. La discusión comienza al reconocer que existe una contradicción en el uso de diseño obtenidas con base en métodos de análisis lineal y a su vez reconocer que las estructuras incursionan en el intervalo inelástico de comportamiento, lo que conduce a admitir que los daños esperados no provienen de la resistencia de la estructura, sino de la deformación. La utilización de la metodología basada en fuerzas y el uso de factores de reducción están establecidos en los códigos de diseño sísmico desde probablemente los años 70 del siglo pasado. Sin embargo, desde hace décadas se ha cuestionado su aplicabilidad en la estimación de las demandas de desplazamiento no lineal para todo el intervalo de periodos de las estructuras que se construyen, mostrando ser razonablemente adecuada esta regla para cierto intervalo. Aunque diversos textos y artículos publicados enfatizan lo anterior, el trabajo que se presenta el día de hoy tiene la virtud de identificar variables específicamente relacionadas con la aplicabilidad de los análisis no lineales para predecir la respuesta, adecuadamente diría yo, la respuesta no lineal, y sugiere también líneas de investigación que podrían mejorar el uso de la aplicación de estos análisis lineales. Resulta interesante y relevante la mención del método de la estructura sustituta, que viene desde los años 70, particularmente en 1976, de un artículo de Shibata y Sosen, en el que, a pesar de aplicar la filosofía de diseño basada en fuerzas, la metodología busca predecir el comportamiento no lineal al modificar la matriz de rigidez de la estructura como función del daño de los elementos estructurales. Esto conduce, desde luego, a una predicción del comportamiento inelástico esperado diferente a la manera en que se hace actualmente mediante el uso de factores de reducción de los espectros elásticos de diseño. El doctor Matamoros logra mostrar con claridad la diferencia entre el trabajo pionero de Shibata y Sosen y los enfoques actuales del diseño sísmico que emplean factores de reducción. En estos últimos, se discute la validez de la regla de igual desplazamiento establecida en los reglamentos de diseño actualmente para determinar las demandas de desplazamiento lateral no lineal. Aquí se introduce la importancia de las derivas de distorsión angular en la aplicación para estimar los desplazamientos inelásticos con base en análisis lineales. En este contexto, resulta muy relevante la relación entre la deriva de Sauté y la de entrepiso, lo que muestra por qué se busca concebir estructuras regulares al aplicar la filosofía de diseño de fuerzas. El trabajo también analiza con claridad las propuestas de documentos de la ASCE para la evaluación y el diseño sísmico de estructuras existentes y nuevas. Se destaca, en un caso, el uso de factores de reducción por componente, que se acerca a la metodología de Shibata y Sosen, y en el otro es mediante la aplicación que ya mencionaba yo de factores de reducción para todo el edificio. El doctor Matamoros, me parece que en forma muy acertada, refiere con frecuencia a trabajos históricos como el libro de Hardy Cross, donde se hacen reflexiones muy relevantes sobre la ingeniería estructural, que por cierto, muchas de ellas siguen vigentes. El estudio destaca también la importancia de los efectos de segundo orden en la inestabilidad estructural cuando los análisis se realizan en el intervalo elástico y el comportamiento esperado es no lineal. Los desplazamientos que puede originar inestabilidades, desde luego, muy diferente en ambos casos. También se muestra que la probabilidad de colapso de una estructura bien detallada sísmicamente puede acotarse al limitar la demanda de deriva obtenida a partir de los análisis no lineales. No ocurre lo mismo en estructuras con un detallado inadecuado. El estudio también hace una reflexión respecto a la posibilidad de colapso de edificaciones con un mecanismo de falla no deseado que, a pesar de ser conceptualmente estas estructuras regulares, tienen un detallado pobre o una relación de resistencia de columnas a vigas baja. Se muestra que un detallado pobre es un parámetro muy importante que hace que los métodos de análisis lineal sean inaplicables para predecir la demanda de desplazamiento no lineal de las estructuras. Un aspecto que me parece también destacado del trabajo de ingreso es presentar resultados que ilustran la relación del cociente de la demanda máxima de deformación no lineal entre la deformación de fluencia de los elementos estructurales con el cociente de la demanda máxima de fuerza del análisis lineal entre la fuerza de fluencia del modelo no lineal. Interesante resaltar la mayor dispersión de los resultados en columnas que en vigas de este cociente y la importante dependencia con respecto a la calidad del detallado de los elementos estructurales y esta importante dependencia con la dispersión de los resultados. A mayor detallado, menor dispersión observada y resultados más conservadores con respecto a la estimación de las deformaciones que son claramente observadas en vigas y en mucho menor grado en columnas. Con base en la discusión de los resultados que anteriormente se presentaron, el doctor Matamoros identifica y propone que para mejorar la aplicabilidad de los métodos de análisis lineal en la predicción de las demandas de deformación en el intervalo no lineal de deformación, deben estudiarse con mayor profundidad tres aspectos fundamentales: el efecto del cociente de resistencia de columna viga, la calidad del detallado de los elementos estructurales y los límites de deformación. Esto es lo que él llamaba en sus conclusiones establecer barreras de seguridad. Como colofón del estudio, se sugiere apropiadamente reevaluar por completo la metodología de análisis lineal propuesta en el documento ASCE 41 con el objetivo de eliminar inconsistencias derivadas de la conjunción de diversos conceptos de diseño sísmico presentes en el estándar. Por todo lo anterior, es para mí, lo decía en un inicio, lo reafirmo ahora, es un honor participar como comentarista del trabajo de ingreso del doctor Adolfo Matamoros Hidalgo, como en su calidad de académico correspondiente de la Academia de Ingeniería de México. Estoy yo plenamente seguro que sus aportaciones, nos lo ha mostrado en su presentación, impulsarán proyectos conjuntos entre México y los Estados Unidos, lo que seguramente abrirá nuevos nichos para impulsar estudios relacionados con el diseño sísmico orientados a mejorar el conocimiento y sobre todo la mitigación del riesgo en ambos países. Su trabajo también contribuirá a fortalecer aún más la relación gremial de la academia con instituciones extranjeras, lo cual creo que va a redundar en el desarrollo e impacto de nuestra profesión en México. Por ello, finalmente, felicito ampliamente al doctor Matamoros por su ingreso a la Academia de Ingeniería, convencido de que todo esto coadyuvará significativamente a consolidar los objetivos fundamentales de esta asociación. Muchas gracias.
Muchas gracias, doctor José Manuel Jara Guerrero. Enseguida toma la palabra el doctor Javier Alonso García Jarqui.
Muchas gracias.
Adelante.
Muchas gracias, señor presidente, maestro Alberto Lepe, estimados colegas, amigos todos. Es para mí un honor poder hacer algunos comentarios al trabajo del doctor Adolfo Matamoros Hidalgo desde el punto de vista de la práctica profesional. Doctor Matamoros Hidalgo, quiero iniciar mis comentarios felicitándolo por un excelente trabajo que ha presentado a la Academia, porque además ha mostrado con gran claridad un tema que resulta ser fundamental para entender el buen desempeño de las estructuras sujetas a sismos intensos. En la primera parte de su trabajo, relacionada con los criterios de diseño sísmico para edificios de concreto reforzado en los Estados Unidos, indica de forma muy atinada que desde hace décadas se ha considerado que el buen comportamiento de una estructura puede medirse mediante las relaciones demanda-capacidad obtenidas desde la perspectiva de las fuerzas actuantes y resistentes. Ha sido muy común en la práctica profesional obtener estas relaciones a través de análisis lineales. Adicionalmente, se le ha otorgado a estos cocientes una importancia básica para estimar el buen desempeño de las estructuras sujetas a los efectos dinámicos. Sus estudios claramente demuestran que las relaciones demanda-capacidad basadas en fuerzas, aunque son importantes, no son el único parámetro requerido para una adecuada estimación del buen desempeño, obedeciendo la máxima del profesor Harry Cross, y que los métodos lineales utilizados hasta ahora tienen limitantes en su aplicación. Ciertamente, códigos como las normas técnicas complementarias para diseño por sismo en la versión 2023 del reglamento de nuestra ciudad reconocen la importancia de otros parámetros esenciales como las distorsiones de entrepiso. Por otra parte, reconociendo la considerable mayor complejidad que implica el diseño sismo resistente comparado con aquel requerido para las cargas gravitacionales, se tiende a abusar en la reducción de las fuerzas sísmicas para lograr diseños más económicos, obviando en ocasiones que esta consideración de diseño basada en la capacidad de la deformación de las estructuras produce deformaciones inelásticas en los elementos estructurales. Deformación es igual a daño. Coincido con usted en la contradicción que se genera en la práctica profesional de la ingeniería sísmica al seguir utilizando análisis lineales basados en resistencias reducidas a pesar de reconocer el consecuente daño. Queda claro que la metodología presentada por los profesores Shibata y Sosen hace 50 años no resultaba de aplicación práctica sencilla y reconocía limitantes como las irregularidades estructurales y el uso de análisis lineales. Resulta también oportuno en su trabajo recordar que implicaciones de la aproximación de iguales desplazamientos y la influencia de parámetros como la resistencia de cortante en función de la relación de los periodos es muy importante. Finalmente, en esta primera parte de su trabajo, resalta el efecto de la razón entre la resistencia de la columna y la resistencia de las traves en la formación de mecanismos de colapso, concepto esencial en el diseño sismo resistente y que los ingenieros de la práctica debemos de tener muy presente. Este compendio de dificultades que usted adecuadamente resume en el proceso de diseño de estructuras sujetas a sismos deja claro que los problemas pueden ser entendidos por los ingenieros de la práctica profesional. Sin embargo, no siempre han sido adecuadamente atendidos. En la segunda parte de su trabajo, presenta la metodología para la evaluación sísmica de las estructuras. Usted hace mención a la norma de nuestro país, que mencioné hace unos momentos, y que establece diversos valores de distorsiones máximas permisibles para cumplir con diferentes estados límite de servicio. Esta ha sido quizás una de las aportaciones más importantes de la normatividad en nuestra norma, en nuestra ciudad. Aunque queda evidente el castigo que implica la irregularidad estructural, la concepción arquitectónica aún parece ser transparente a estas implicaciones. En su trabajo se estipula que la normatividad ASCE 41 para la evaluación sísmica se desarrolla considerando objetivos establecidos por el propietario. No puedo dejar de coincidir plenamente con usted en involucrar a propietarios, desarrolladores y clientes en la toma de una decisión tan importante. Sin embargo, en nuestro país, esta corresponsabilidad en toma de decisiones parece estar muy lejos de ser posible. En los resultados de los análisis realizados por usted y sus colegas, resalta de manera sobresaliente la correlación entre parámetros como la resistencia y el nivel de detallado en la distorsión y la probabilidad de colapso. Es evidente la importancia de un mejor detallado y la reducción de la probabilidad del colapso. Vale la pena recordar la premisa del profesor Vitelmo Bertero, quien decía que un buen detallado en las estructuras de concreto reforzado podría marcar la diferencia entre la vida y la muerte de la estructura. Por último, creo que es importante resaltar los análisis que evidencian la dispersión de los resultados en diferentes parámetros de la respuesta estructural. La dispersión se hace evidente al comparar resultados de análisis lineales y no lineales y aumenta a medida que disminuye el nivel de detallado. Es oportuno resaltar que los análisis no lineales no tienen como objetivo hacer diseños más económicos, sino evaluaciones más confiables en la respuesta estructural. Concluyo confirmando que su trabajo debe ser una referencia obligada para todos los ingenieros de la práctica profesional y me atrevería a decir para los arquitectos que entiendan la complejidad. En el análisis y diseño de estructuras sujetas a sismos. El entendimiento oportuno de este problema llevará a un mejor diseño y un mejor diseño se traducirá en un mejor comportamiento de las estructuras que al final es lo que la sociedad nos demanda. Muchas gracias y enhorabuena por su ingreso a la Academia de Ingeniería.
Gracias, doctor Javier Alonso García Jarqui. Después de una fotografía del recuerdo que nos vamos a tomar, vamos a regresar a las 2 de la tarde. Tenemos 3 conferencias muy interesantes y además la entrega de la medalla y los diplomas a nuestros nuevos académicos. Así es que están todos invitados. Tendremos la conferencia de la doctora JoAnn B. Browning, la de la doctora Ellen McRadji y la del doctor Taylor Egme, presidente de la Universidad de Texas. Así es que están todos invitados a regresar a las 2 de la tarde.
Muchas gracias.
Bueno, pues aquí ahorita nos vemos.
Un recuerdo para los revisores de agradecimiento es pequeñito. Son artes hechos por artistas, son pequeñitos, de Bernie, Texas.
Ah, ok, gracias.
La foto.
Si quieres pasar un poquito.
Sí, simetría muy importante. Damos la botella de agua. Muy agradecido a todos.
Felicidades.
Muchas gracias. Muchas gracias.
En Texas casi no tiembla, ¿o sí?
No, tenemos pocos. Sí, lo más que experimentamos es la explotación petrolera por fracking. Está comenzando a generar un poco de vacío. Sí, cerca de la frontera con Texas. Eso también es un peligro en la zona de explotación cerca de la frontera por creo que es nivel. Esa zona
Se está midiendo el efecto. Sí, hay algunos estudios.
hay estudios que lo han correlacionado, ¿no? Sí. Muy generoso sobre los comentarios, no merecido.
No, pues vamos. Esto no se puede quedarse aquí. No,
Perdón, doctor, no lo escucho. Deme un minuto.
si es por el
Sí, vamos a hacer una prueba con la presentación. Con el apuntador, si me ayuda a correrla para ver que se reproduzca el video. Si gusta con el apuntador, correr la presentación para... En automático se reproduce. Sí, por nada.
Probando, probando. Probando, probando. 1, 2, 3, probando.
Sí los escuchamos. Probando, probando. Lo estoy probando. Probando, 1, 2, 3, probando. Hola, hola. Sí los escuchamos.
Yeah, this is me. It's so nice to meet you. Thank you so much for taking time to read my paper.
Nice to meet you.
Your article is very interesting.
I will read your brief.
Okay, that sounds
A few
good.
words.
Just a few words, yeah, please. Please don't
Because
read
of the
everything.
time.
Yeah, no worries.
Nice to meet you.
So nice to meet you as well. Thank you. Thank you for everything.
Have a nice stay here in Mexico.
Oh, already a wonderful stay. Sergio hosted us for dinner last night.
Oh, good.
Amazing. So nice. When did you arrive?
Yesterday.
We leave tomorrow.
Very short.
It is a very short time. Next week.
Oh,
so,
okay,
yeah. So we're just really happy to be here.
Thank you.
Thank you.
Bien, pues muy buenas tardes. Bienvenidos a esta segunda etapa de la ceremonia de ingreso de realmente distinguidos académicos correspondientes, vamos a iniciar pidiéndole la palabra al doctor David de León Escobedo, que es protesorero y miembro de la especialidad de Ingeniería Civil, que expondrá la semblanza de la doctora JoAnn Browning, que ingresa el día de hoy. Doctor David de León Escobedo, tome usted la palabra.
Muchas gracias, doctor Lepe. Muy buenas tardes a todos. Es para mí un honor y un gran placer participar en esta insigne ceremonia y en el marco de los 70 años del Instituto de Ingeniería. Una magna ceremonia de ingreso de distinguidos académicos, entre ellos la doctora JoAnn Browning. Y voy a leer una muy breve semblanza solamente en aras del tiempo. En la sección de educación hizo su doctorado en Ingeniería Civil en la Universidad de Purdue, su maestría en la Universidad de Kentucky y su carrera de Ingeniería Civil también en Kentucky. Entre los cargos académicos que ha tenido, ella es profesor de Ingeniería Civil en la Universidad de Texas en San Antonio desde 2014. Ha ocupado la cátedra Lutcher Brown de la Universidad de Texas también, de 2025 a la actualidad. Ha sido catedrática distinguida David y Jennifer Spencer de UT San Antonio, de 2014 a 2023. Fue profesora de Ingeniería Civil en la Universidad de Kansas, de 2010 a 2014. Profesora asociada de Ingeniería Civil en la Universidad de Kansas también, de 2004 a 2010. Y profesora asistente de Ingeniería Civil en la misma universidad del 98 al 2004. Entre los cargos administrativos que ha ejercido fue vicepresidente interina de Investigación en la Universidad UT en San Antonio, de 2023 a 2025. Ha sido decana del Cleese College of Engineering and Integrated Design de UT de 2014 a 2023. En el ramo de investigación se ha centrado en la prolongación de la vida útil de estructuras de hormigón mediante la resistencia a los temblores, la mejora de la durabilidad y la sostenibilidad. Ha trabajado dentro de la comunidad de ingeniería en riesgos naturales. Los equipos de investigación que ha creado son vía para que las personas puedan avanzar en su educación universitaria, en la educación de posgrado y el profesorado para descubrir formas innovadoras de mejorar la sostenibilidad de nuestra infraestructura. Como presidente del Código de Edificación ACI 318, procura proporcionar estándares seguros, eficientes y resilientes para el edificio y construcción en hormigón. Ha sido investigadora principal y coprincipal en proyectos con presupuestos de más de $10.5 millones. Ha escrito más de 39 artículos revisados por pares en revistas indizadas. Ha dirigido y codirigido 12 doctorados y ha dirigido y codirigido a 27 graduados de maestría. Entre los diversos premios y honores que ha recibido fue el Salón de la Distinción de la Ingeniería en la Universidad de Kentucky en este año 2026. Premio al logro distinguido de egresados de Ingeniería Civil de Purdue en 2024. Membresía distinguida en la ASCE de 2024. El Salón de la Fama de Mujeres de San Antonio en 2024. Premio al Liderazgo Femenino del San Antonio Business Journal de 2018. El premio Inspiring Women en STEM de 2016, Insight into the Diversity Revista. Becaria distinguida mujer de la Universidad de Purdue en 2015. El premio Henry E. Gold de la Universidad de Kansas en 2012. El premio Miller Scholar de la Universidad de Kansas 2011. Y miembro del ACI desde 2009. En su desarrollo profesional ha ocupado diversos puestos, por ejemplo, la Junta Nacional de Administración de 2015 a 2018. Comités hay un gran número, voy a leer solamente 3 o 4, actividades técnicas desde 2012 a 2018. En el comité 318 fue presidente de la sección sub C, análisis y funcionabilidad, y del mismo comité sub D, flexión y cargas axiales, de 2002 a 2014. Junta directiva del capítulo de Kansas de 2006 a 2012, vicepresidente 2009 y presidente 2010. En el Aura Noir Lab, Consejo de Supervisión de Gestión, de 2024 al presente. En el Consejo de Seguridad Sísmica de Edificios, parte de diversos comités, entre ellos vicepresidente del Consejo de Administración 2022-2025. Y en la infraestructura de investigación en Ingeniería de Riesgos Naturales, líder de la educación y el alcance comunitario de 2015 al presente. Es un placer recibir aquí a la profesora Browning. Es todo. Gracias.
Gracias, doctor David de León Escobedo. Ahora escucharemos el trabajo de ingreso de la doctora JoAnn Browning bajo el título Investigación, Reglamentos de Construcción y Práctica de la Ingeniería en una era de información, innovación y resiliencia. JoAnn.
Good afternoon. I'll try to keep you awake after you've had a nice lunch, I'm sure. It is such an honor to be here. I'm truly humbled to be a part of this class of inductees into the Mexican Academy of Engineers and to be a part of this ceremony today. I want to thank the Academy for all of their support. I want to thank UNAM as well for hosting us today and truly express our gratitude for all of the support that we've had over the last 24 hours, and I'm sure we'll have even more tonight. Thank you. So my talk today really draws on some of the experience that I've been working in over the past 30 years, maybe more closely in the past 15 years with natural hazards engineering and helping to lead different networks of infrastructure and how we can research ways to make our infrastructure safer from the hazards that we see in place today. But also in the work that I'm doing with building codes. I am currently chairing the American Concrete Institute Building Code Committee, and I'm also chairing the Building Seismic Safety Council committee that oversees the provisional update for NEHRP in the United States. And so the talk that I'm going to give today is going to be, if we are looking at where we are today, and maybe the first two talks were very technical and amazing, and I'm honored to be a part of the group with you, we're going to take more of a 9,000-meter view in the next 30 minutes or so. Back up a little bit and talk about some overall concepts in code development and how research and practice work together to put in place standards that are usable in today's modern construction and design. And to do this, my paper really takes a fresh look at a paper that was published by Chet Cease in the ACI Journal in 1960. And I want to thank Adolfo for bringing this back to my attention. I really hadn't looked at this paper for so many years. And looking at it again and some of the areas that I'm working in right now really was meaningful for me to be able to talk about it today. Now, this paper written by Chet I think is even more appropriate to talk about in the context today, because when he wrote it, the American Concrete Institute was holding its regional conference here in Mexico City. And the engineers at the time were getting ready to develop a new concrete building code and take some of the lessons learned out of the 1957 earthquake here in Mexico City to create something that would be more resilient and safer for their own structures. And so Professor Cease was writing this paper in collaboration with the Mexico City engineers to talk about how we see research, building codes, and engineering practice working in the US, and some of its intricacies in building that together. So before I go any further, though, I want to talk a little bit about Chet Cease himself, so you have an idea of where his perspectives were coming from. Dr. Cease was born in Louisiana in like 1916, got his bachelor's degree from LSU in 1936, so 20 years young. And when he graduated, they were in the middle of the Depression, so you're really looking for whatever job you can get at the time. And so he did a number of jobs. He worked as a survey crew, the leader of a survey crew. He also helped establish the first soils testing lab in the Louisiana Highway Department. And through that experience, he thought, I think I'll go and get a graduate degree. And he moved to Illinois, University of Illinois, Urbana-Champaign, to pursue that master's degree in their very famous Theoretical and Applied Mechanics department, known as TAM. And after he received that, he went into practice for a little while. He worked on the Chicago subway system, and he worked for the New York Railroad Bridge Association before coming back to Illinois and getting his PhD there. So he had not only the academic preparation, but he was also getting some experience working in practice as well, and not just in civil engineering structures, but branching out into transportation and soils as well. And from this experience, he really took a practical viewpoint on how research should be developed. And he went to work in the Talbot lab, the structures lab in Illinois, to see how this work could progress under that observation mindset. The part that he's had a number of accolades over the years, but the part that I want to point out today was his work with the American Concrete Institute. He did serve as president of ACI at some point, but even more on the nose for this talk, he was on the ACI 318 Building Code Committee from 1952 to 1995. And so when he wrote this paper that I'm going to talk about today and refer to several times, he'd been on the code committee for about 8 years. He was still kind of a young guy on the committee. And he also had that engineering experience, and he was a researcher in academia because he became a professor at University of Illinois. And so all of that together is how he brought forward his ideas on developing codes. And he did serve as the chair, if I can get this to work. I think, there we go. The chair of the 318 Building Code for the 83 edition. There you can see my ragtag version of it from my office. And so he also later was able to bring those perspectives too. So in his paper, he talks about this relationship, and I've reproduced this figure. It's a little crude, but I think it'll do our purpose today, between research codes and practice. And you can see that he really emphasizes those thicker lines that connect research into the code, so what we've learned new and how can we codify that, and then the thicker line that goes back to practice, so the practice rely on the code to build safe, reliable structures, and a little bit thinner but still substantial connections from practice back into the code, so giving the feedback on what they're seeing and how it's working in modern design. And then also some questions on the code going back directly to research. So we have this in the code, but is this really the most efficient, or is this really the best use of our standardization? And then the smallest lines there are the connections between research into practice, where research may go to practice to ask the questions, or maybe going to practice to give them straight information on how it can be applied, and practice coming back to research with particular questions. And so I want to refer to this model a little bit today, and maybe how it might be refreshed. Now, the other thing he talks about is knowledge in general, and where does it come from? And when we're building a code, we're trying to take our wealth of knowledge that we have on, if it's a building code, structural performance, and put it in a way that when we design, we're going to get the performance that we expect. And he follows the career of a young engineer and how she gets her original academic preparation in the existing wealth of knowledge, and then you know, in modern days, we might actually have a little bit more than just that existing knowledge. She might do an internship or she might work in a research lab, but it's likely that most of the knowledge she's gaining is in the classroom or with her professors. And then when she goes to her profession, either in practice or in research, there's going to be a combination of her own work as well as observing the work being done by others that will hopefully bring back more knowledge into the general knowledge that we have for civil engineering, but will certainly improve her ability to comment on modern day challenges and opportunities. And then today, I also want to talk about how important it is that we bring those two circles closer together. And in order for us to really build the best guidance for the practice, we need to have researchers and practitioners making those observations together. So today I'm going to reflect on some of those concepts and how modern codes incorporate interdisciplinary performance requirements, but also for an internationally connected society and how we leverage that to make our codes even better. And I'll do that in three main portions. I'll talk about the basis for building codes, the pace at which we go around revising and updating codes, as well as just a couple of concepts around multidisciplinary and multi-performance systems that we live in today that need to be brought into codes as well. So first about the basis for modern codes. And here I'm going to talk about something that Chet Cease pulls on in his paper that has that tension between observation and calculation. Those of us that are working in research, we often want to sharpen our pencil and get the very best answer. And after we've done a large-scale research project, we're ready to get it into the code. People need to benefit from the new knowledge that we've put together. Those that are in practice may be a little more reluctant. And they say, you know, it's working, it's not broken. Why do we need to make that change? And so there's always this tension about how quickly can we get innovation into a code versus what's the right speed for doing that so we can understand all of the implications of those changes. And I'm going to touch on this by talking about a couple of examples. And I'll start with what we have in the US is a really nice, I believe, earthquake engineering research infrastructure and sort of its history and how it evolved based on our opinions on observation versus calculation. So in 2004, the National Science Foundation put a substantial amount of funding into standing up a network for earthquake engineering simulation. And it was named after George E. Brown Jr., who was a very influential politician in California and was doing a lot to try to protect the citizens of California from the effects of earthquakes. And outside of the cost of actually building that infrastructure, it still took another $200 million just in operating 15 sites around the country over a 10-year period. Now, these sites are really amazing, and they still exist today. But for example, one was the large-scale shake table at the University of California in San Diego, where you could build a 4 or 5 story full-scale structure, subject it to realistic earthquake ground motions, and get realistic responses out of those structures to understand how different types of research projects and innovations were actually going to influence a system response. Another one was in Lehigh. And at Lehigh, they have what they call a hybrid testing system, where you can build the components of that building system in full scale, but you actually take the rest of the system and you have it in simulation. And so you are doing a feedback loop between the realistic response you see in the lab to the simulated response of the entire building system or whatever system you're looking at, and then feeding back its response to the component to try to get a better idea of the boundary conditions that you're testing that component under. And so these facilities are tremendous, but what I really want to point to is the name of this network for Earthquake Engineering Simulation. They don't really talk about in the name the infrastructure at all and the experimental facilities. The focus was, at the time, a feeling that we could get to the point where we would be able to do simulation and get the answer and maybe not have to invest in the research that has to be done in the lab that is so much more expensive. And you can see that with the hybrid testing technique, right? Trying to move more into a cheaper way of testing things and still get the full system response. And Chet Cease points to this in his paper in 1960. There's a line in there that says something like, maybe someday we'll be to the point where we won't need research in the laboratory or observation in practice, but we're not there yet. And that was 1960. And I would say we're still not quite there. In fact, the next generation of NEIS was known as NERI, the Natural Hazards Engineering Research Infrastructure, and that's in place now. And so it went down to 12 sites, $180 million in operations over about 10 years, and brought in different types of natural hazards. And so we have wind now, and we talk about flooding and tsunamis and so on. But the idea here is, in the name, is infrastructure. And it was a real emphasis on the fact that we need to keep that infrastructure available to understand better real performance under real conditions. Here's another one I want to share. It's a little bit more around code development. And this has to do with the last version of the 318 building code and some equations we had put in for amplified shear under earthquake loading. So again, in 2019, the version of the code that came out that year had a new equation in it for amplifying the shear forces in special structural walls. And this was something that we were familiar with for a while. In our calculations, we could look at a structural wall and understand that, as Dr. Matamoros presented earlier, in our linear analysis methods, we would calculate a base shear demand, we'd put it under probably in a linear distribution over the height of that wall, and then we calculate the shears in that wall itself. But we've known for a while that just based on the design aspects of that wall and under a linear analysis procedure, you may underestimate the actual amount of shear that you need to design for in that wall. And for a couple of reasons. One is the material properties we design for, we say it's a grade 60 steel, 60 KSI in the US, may actually have 72 KSI or 75 KSI capacity. And so when you yield that structure and you yield the steel, you actually get larger stresses than you may have designed for. You design conservatively based on gravity loads, but under dynamic loading, you may actually invoke higher stresses. So that's one element. And the other element is that we pretty much assume a single mode distribution, although we may have a few extra wiggles along the height of that wall. And so it's something that the industry calls a higher mode effect. And so the equation that was brought into the 318.19 version of the code took V sub U, which was the original shear demand that you would calculate for, and amplified it for overstrength and for higher mode effects to come up with a higher value of shear that you should be designing that structural wall. So when we put out a new code, it takes a while for it to be adopted by municipalities. First, it gets adopted by the International Building Code in the US, and then municipalities or states around the country will adopt it one at a time. So even though the 2019 code came out 7 years ago, it's just now really starting to get adopted by different states. And so we had some time where we got feedback from the practice. And the practice was finding it a little confusing on how to apply this new equation, when it applied, what types of safety factors to use. In some cases, in some extreme cases, they were finding that the thickness of the wall they had designed under the 2014 version of the code was doubling under this new provision, which was not the intended effect. So code cases were submitted, and code cases are an opportunity for the public to ask for clarification from the committee. And we received code cases from the Structural Engineering Association of Washington, of Northern California, and the LA Tall Building Council asking for clarification on why they were seeing these problems. And so revisions were put into the 25 code that clarified the application, the strength reduction factor that should be used, and there were modifications to both those omegas, the overstrength and the higher mode effect. to bring it back in line with what was observed in practice. Even though all the calculations that we know that it's there, the amount of amplification was just not tolerable. But the really interesting piece that I wanted to point out here as well is that lowercase omega factor, if we show it here in this graph versus the height of the wall in feet, that top yellow line is the amplification factor that was used in the 2019 code. And the lower orange line, that's the lowest line on the far right, is the new amplification factor in the 25 code. So you can see a substantial reduction. But when the questions came out about, well, what is reasonable, we turned to our friends in New Zealand and what they were using as amplification factors. And that's the line that we ended up following. And so even when we don't have our own observations to make, we can rely on the observations from international partners to find a better fit for that code. And so from this part of my presentation, I would say we're still not to the point where calculation can replace observation. And that means that we need to continue supporting having experimental research infrastructure. And we need to make sure that the people that have influence over that understand why it's so important, because we can't just do it on our computers. We have to have something that we observe as well. But we also need to value these strong partnerships between the research and the practical evidence that exists on a world scale. Okay, the second piece that I want to bring up is the pace of modern code. Another familiar tension that we can see in code development, I think in just about every area and probably every place around the world. And that is this tension between the new knowledge that's being developed and how quickly can it become working knowledge? How quickly can we get it into code development? And again, I'm going to use just a couple of examples here to illustrate some sticky points within this conversation. And I think the answer to how can we find the best pace for bringing new information into our building codes is the idea of making sure we're partnering research and practice as close as possible. And the first example I'm going to use is one around performance-based design for earthquakes. And I want to thank Sergio and his comments for pointing this one out, because I thought this was an amazing illustration of this partnered approach. First of all, what is performance-based design? Adolfo mentioned it a little bit earlier, but the idea is that we can set a level of performance for the structure we're designing, whether that's based on the amount of damage we think we could allow, the losses that we could sustain and still be viable, or the functionality of the building after an event occurs. And this is all done within a given hazard, the hazard that you're designing for. And it's required that you use the most detailed analysis to understand the behavior of that structure. There are certainly linear analysis procedures, but the nonlinear response is going to be the one that gets you closest to that actual performance. And so if we were to show a common nonlinear representation for a building system, we might show one that has base shear on the vertical axis versus the roof displacement on the horizontal axis. Just as Dr. Matamoros was talking today about mean drift ratios, this is a representation of that drift ratio under different levels of force, pushing it over. And for performance-based design, you might describe different levels of deformation in your building for different levels of performance. And so up to the yield point might be what we would call operational. And then from yield until to that peak strength point might be the immediate occupancy. And then in the shorter part of the backward leg, it would be life safety, and then you're just trying to prevent collapse near the end. Okay, so that's what performance-based design is. We're defining where those points might be, and we're trying to keep our structure from having enough deformation to go past that performance point. So how did this come about? Well, back when Chet wrote his article, pre-1970, we were all about static lateral loads. That's what we used in our analysis. After the 1971 San Fernando earthquake, we found that there was obvious brittle failures in our elements, and something more advanced in our analysis and design needed to be put in place. And so in ATC, the Applied Technology Council, 306, so this is, they started outlining ways to control inelastic behavior. This was more of a performance implicit design method. And then, but again, let me say that real quick. ATC is not a code. It is a pre-standard. It's a guide. It's something you can look at, but it's not going to hold legal weight when you're designing your building. Then we had 2 really large earthquakes in California in 89 and 94. And we saw that the designs that had been built to the current standards and codes had great performance for life safety. We didn't have a lot of loss of life in buildings. We had some horrific collapses of bridges, but in the buildings we did better. But what we did see were really large economic losses and loss of functionality as well. And so research at the time in structural engineering really hit the ground on we've got to be more prescriptive on performance and how can we keep our systems at that level of performance. And we built a number of pre-standards during this time that outline the framework for performance-based seismic design. But again, these were pre-standards, not into code. Then we get into the 2000s. Somewhere around, I think, 2006 is where ASCE 41 came out that had performance-based design concepts in it, but that was for existing structures. And for new construction, we still didn't have a code format. We had FEMA 440, which was a pre-standard. And then, so during this time, it was really incremental updates that we were seeing. The real acceleration started somewhere around the mid-2000 teens. And this came about because research started partnering with practice in getting this implemented and finding a way to make it codified. And so at this point, and to now, we start getting those practical applications. And even today, you can design one of 2 ways. You can take the code approach, which has certainly the code-based capacity design with ductility concepts in it, but you could also do a more advanced design if you have a specialized structure that's based on these performance-based design concepts because they are in a format that is legally adoptable. But this would not have happened today, and notice it took 25 years of working on this, but really the acceleration in the last 5 to 8 years to get it implemented because of the work that we got from and the input that we received from the practicing community. They helped us to translate the theory into usable code standards. They helped us to develop consensus documents. Under real design constraints and giving it professional legitimacy. They took these concepts and put them into real projects so we could discover the feasibility and we can identify gaps. There was regulatory engagement. They helped us to define acceptable analysis techniques. They helped us to document the standards that needed to be used along the way. And they also helped to institute the peer review process that made it truly feasible for building officials. And then there was also, of course, this feedback loop, this iterative improvement constantly. And LA and San Francisco adopting these concepts and allowing tall buildings to be constructed under these techniques was really a turning point so that now many cities can adopt these as well. And you're seeing them come into mainstream codes, these performance-based design concepts. ASCE 7 is now risk-targeted ground motions with nonlinear options in it. ACI 318 is still mostly capacity-based design with these deformation awareness concepts, but the 25 version of 318 also has 2 appendices. One is performance-based design with wind, and the other is nonlinear analysis techniques, which has actually been there a couple of cycles. So they're in the appendix, but usually those find a way to work their way in. And so I think the biggest thing that happened during this period and with this partnership is that we went away from practitioners saying, does this design meet code forces to how will this building actually perform, which is the real objective in any design. Okay, the second example I want to get is around the NERI research infrastructure that I described to you before. And the idea of trying to accelerate research that's done in those labs into practice as well. And one way we do this, in fact, at the end of the NEIS project, we questioned, well, we brought back the biggest question that we always receive whenever we were reviewed or whenever we were trying to talk about the impact that our work had had. And the question was, well, what impact are you making? Where are you seeing design change and people being safer because of the research that's being done in Nice? So for NERI, we became a little bit more focused on how to get this in place. And we built a technology transfer committee that is filled with renowned engineers in the US that are very active in building code design. Bill Holmes is the chair. He's the member of a US National Academy, and there's several other members there as well. And they do a number of things. They have webinars and they talk to panels. They've also done a review of NERI research and looked for those diamonds that maybe could be taken into practice and then tried to partner with those PIs to make it happen. But one of the things they do is they present every year at our annual Summer Institute for early career researchers. And so instead of waiting around for practice to say, okay, let's work with performance-based design and then get the acceleration, how can we start building those partnerships between early career researchers and the practice early so you can start building trust, and then that can pervade the rest of their careers. So here's one example. Elena Sutley is an amazing structural engineer at the University of Kansas. She came to our Summer Institute. She met Bill Holmes there and got to know the Technology Transfer Committee. After that, she won an NSF Career Award. I think this past year, she just got the Blatvinik, did I say that right? Young Scientist Award in the US. And so she's really making a strong impact in our area. But she was looking with her career award at modular construction and the damages that they were suffering during windstorms, coastal storms, because there really weren't a lot of design guidelines for how to protect that region and those people under those conditions. And she was also looking at coastal structures built on stilts to escape the water, but the wind is another element that, again, wasn't in building codes, so you didn't have a way for anticipating the level of damage that could occur. And she worked with people not only categorizing the damage that occurred, but also using social science techniques to survey people, to do focus groups, and to follow them over, I think it was an 8-year period, to understand what were the key elements that helped them go from devastation back to thriving in their community. And she did these observations in the field, but she also had some laboratory work at a NERI facility called the Wall of Wind at Florida International University. And I should mention that the social science work she did was coordinated with Converge, which is also a NERI facility. And all of the data that she did is in DesignSafe, which is also a NERI facility. But this work in itself is tremendous, but getting it into a code format was not something she knew how to do. So she partnered with Bill Holmes, and he helped to get her in touch with the ASCE 7 code committee, which does the minimum design loads and associated criteria for buildings and other structures. And in the 2022 version of the code, that we now have equations that can be used to calculate the demands on these coastal structures. Again, I'm not sure it would have happened organically as fast if she didn't have a partnered approach with the practice to build that trust and to bring it into code format. So when we talk about the pace of modern codes, we know society benefits from our research, and we know we need to get it into the codes, but that means having a level of trust between practice and research to understand how it can impact in ways you may not foresee. And this means that we need practice to stay invested in our research, but that also means researchers have to be intentionally connected to practice. And finally, I'm going to talk about a few perspectives for today. And I'm going to do that talking about, as a designer, all the different performance design criteria that need to be considered for modern design, but also all the different disciplinary influences that we've been seeing over time now and need to make sure that we're continuing to build into our codes. So for civil engineering design, I've picked out a few performance criteria. There may be others, but let's start with this. We've always had, number one performance criteria is life safety. You have to make sure that whatever you've designed will protect the public. But the secondary one has always been serviceability. We also want to make sure it serves the purpose that it has and that we have comfort level in the designs that we have put forward. More recently, there's been a big push, I think a lot of it coming from the public that we serve, to have more elements around sustainability, equity, and resilience in our designs. Because design itself, we're seeing, just safety and serviceability may not be enough to protect the needs of the people that are occupying that infrastructure. I want to point and touch on these two that I've just highlighted in red there, resilience and sustainability, just a little bit more. And I'll do this within the context of natural hazards engineering. So you may ask yourself, why is it that there's so much work going around natural hazards engineering? Why do we need NERI to begin with? This is a plot that I've taken from the NOAA website. I actually took it in June of 2024. It's no longer accessible through NOAA, but we're hoping in a few years it'll be back. It has been captured other places, and so we still have the data. But what it shows, and it's a little small, I think, probably for people in the back, but it shows for, on the left y-axis is the number of disaster events that have occurred in the US for a given year. And on the right y-axis is the cost that has incurred in billions of dollars. And the different colors you see are different types of disasters, whether it's from drought or flooding or freeze, severe storm, so on. The green area is severe storm, and that has been probably the largest number that we've had in recent years in the US. But the costs are the lines there, and the black line, if you can see that, is the 5-year average of those costs. So in 2023, the last year I accessed this data, we had about $120 billion 5-year average in costs because of disasters. And it's not just the cost of lost infrastructure that we need to think about. It's also the health and viability of the communities. So let me show you another piece that was done. This is a paper that was published in 2020 in Nature Sustainability that took a look at a hypothetical 7.2 magnitude earthquake on the Hayward Fault near San Francisco. And you can see a number of communities there listed close to that fault. And the tan bar, well, let's start with the blue. The blue bar is what was calculated from housing and asset losses. The orange bar, those are the smaller ones kind of there, are from the loss of labor income. But the tan bars is what they defined as a loss of well-being. And you can see how much that eclipses the other losses put together. And they define well-being as access to water, access to food, access to healthcare, transportation, and much of what social science does now in disaster response is figuring out how in a given region you can maintain those health benefits and those important benefits and how quickly you can get back to them. But when you put these two together, it's a crisis. It's really something that we have to be delivering on in the US. Now, we have some other tricky pieces in the US right now. Because of those levels of cost, we're starting to see that insurance companies are balking at paying for those costs themselves. They're raising premiums. They're also raising the amount that you have to pay out of pocket in the beginning. And in some cases, they're pulling out of complete areas and just saying we won't cover it anymore. And another element that we're dealing with is the fact that the safety net that we've had, which has been FEMA, has been a little bit of turmoil right now. And so we're looking at the point where people that are investing in their properties, in the infrastructure they're building, cities that are investing in infrastructure, may not get the full life cycle out of it, and they won't have the safety net to come in to try to repair it. So it's more and more on us to provide that resilience in the structures themselves. Now, one key to this, especially at this time, is international research agreements and cooperation. Because where we find a stalling in certain viewpoints in a particular region or a particular country, we can reach out to other civil engineers, other structural engineers in other countries or regions and continue the momentum of what we've been working on. And so I really want to point out and thank President Amy and the president of UNAM for helping us to build this relationship that we're going to sign later today between UTSA and the Klesse College of Engineering and the Institute of Engineering at UNAM. And these types of relationships are critically important. Now let me do one that's a little bit closer to code development. In the 318.25 version of the code, we brought in a new appendix that has sustainability and resiliency in it. And in it, we developed a new, or not new, we brought in the terminology and language that may not have been well understood by our communities in the past. And I tell you, it was a battle to get this appendix in. There were people that said, we don't need new performance targets, and we don't want to have to consider that. But the common will and common wisdom said, no, this needs to be brought in and start to understand. Under current political climates in the US, sustainability is not really the element that people are pushing for. But when you look at the life cycle of our structures, if we don't have the right resiliency, the cost of that structure goes up enormously because the life cycle is completely cut off. And again, even though sustainability may not be the common word phrase used in the US, it's not this thing that we're looking for the most. The 318 building code is used in 71 countries around the world in one way or the other, either referenced or used in some part. And we can rely on our colleagues around the world to keep that momentum going. The other piece I wanted to point to was the multidisciplinary aspect of working in civil engineering, and we've known this for a long time, but it just seems to keep growing, the number of disciplines that we have to consider as we're building codes and designing. And I think this leads to an idea that we need to be thinking about how we prepare the next generation of engineers to engage in all these disciplines and make sure they're represented in our codes as well. And so when we go back to that academic preparation piece, knowing that we've shown the importance of interdisciplinary work and how they can understand the languages and terms used in all these other disciplines will help to build better practitioners, researchers, and better codes. In NERI, we do this very deliberately again. We have a very clear pathway built on interdisciplinary collaborations. And this is for undergraduates, for graduate students, and for early career researchers. And you can see some of the numbers here and the success stories that we've had. But what I want to point out here is the interdisciplinarity and the undergraduates and the graduate students that are reported here. And we have these numbers for early career, but I don't have it on this slide. But you can see, out of all of the undergraduates we've worked with, only 66% of them are civil engineering majors. Because we're talking about natural hazards as a whole, and there's so many other elements to that. In the Graduate Student Council, with over 800 registered members, it's only 58% in the civil engineering field. So they're getting that kind of experience from the beginning of their career. Can't go too far without saying the influence of computer science and AI. Absolutely, do we consider that in code development? And how is knowledge being generated and being put out for public consumption? Yes. I think a primary responsibility for us as engineers is to make sure that we are including very diverse sets of data. And from these different disciplines that are tagged in a way that are discoverable by these AI tools, so that when knowledge is generated and put out for consumption, that it's done, we know, with a well-versed perspective from all these different disciplines. But communication is always going to be key for us, and it's something that we're always working with students, is to get them more communication skills. But we've got to think about not just communicating among ourselves, but how we engage with the public and how we engage with those other disciplines as well. And we do this with NERI too. We're building coalitions among different disciplines and other countries to make this effective. Internationally, we work with the EU Center out of Italy, eDefense in Japan, and INCRE in Taiwan. We also have close relationship with EERI. President of EERI is going to talk to us next. We do a lot with the wind engineering communities, and we're starting to forge new agreements with near-surface geophysics because there's a lot of infrastructure with them, and we need to be talking with a common voice to advocate for the resources that are needed to protect the public. And another one that's coming out is the United Nations has a Decade of Ocean Science, and we're working closely with a number of researchers to try to take advantage of that recognition and make progress around coasts around the world. So in terms of perspectives for today, I have to say, to best serve society, codes need to reflect this multi-performance interdisciplinary concepts. And that means when we build our code committees, it's not just about research and practice balance, but it's also a balance between the disciplines and the performance aspects that we want to reflect. And this means leveraging international perspectives is going to be key, and having these specialized or collaborative career pathways to prepare the next generation is also going to be key. And finally, we need to partner research, practice, and policy communities to speak with one powerful voice so we can get the resources needed to complete this important work. So my last reflection here is to come back to Chet's model and say, well, would we change anything about this model? I think it's still a pretty good model. But what I might add is a little bit here on the left side, and a call to always keep the constituents at the center of everything we do. So going back to the 3 areas that I talked about today, when we talk about the basis for code development, we need to be advocating for research infrastructure and for innovative applications in designs. Let's get it in the field, make the observations, and let's get this trusted partnership so that we can iterate as needed. And this means keeping those constituents, the policymakers, the funding agencies, and the owners of those structures within the conversation. When we talk about the pace, we have to be pragmatic, but we need to get innovation into our codes and into practice so that we can better protect the public. And that's probably the orange lines there. Maybe thicken those up a little bit. They were really skinny in the 1960 paper, but maybe we should make those a little thicker. And then as for today's challenges and opportunities, we have to have multi-performance and multidisciplinary approaches in our research and practice and how we come together to build codes. And that means having constituents that are domestic and international communities within the loop, the workforce developers, and the disciplinary partners. We have to build common vocabulary so we can work together, and we've got to speak with one voice to make sure that those who have the decision power to provide the funding for the research infrastructure or for enabling innovation to get into practice understand the impact and the challenge that we're facing today with natural disasters or whatever loading condition we're talking about. Thank you very much for your attention.
Muchas gracias, doctora JoAnn P. Muy interesante el tema que nos acaba de ofrecer. Enseguida tenemos la opinión de los académicos que comentan este trabajo, que serán el doctor Sergio Manuel Alcocer Martínez de Castro, que es expresidente de la Academia de Ingeniería y académico titular de la Comisión de Especialidad de Ingeniería Civil, la doctora Sonia Elda Ruiz Gómez, académica titular de la Comisión también de Ingeniería Civil, y el doctor Gustavo Ayala Millán, académico también titular de la especialidad de Ingeniería Civil. Y en primer término le solicitamos la palabra al doctor Sergio Alcocer Martínez de Castro.
Maestro Alberto Lepe Zúñiga, presidente de la Academia de Ingeniería de México, doctor David de León, protesorero de la Academia, doctora JoAnn P, académica correspondiente, señora y señor comentaristas, colegas académicos titulares de honor y correspondientes, señoras y señores. Muy buenas tardes. Inicio mi intervención agradeciendo al doctor Naún García, presidente de la Comisión de la Especialidad de Ingeniería Civil, su amable invitación para participar como comentarista en esta ceremonia de ingreso de la doctora JoAnn P. Constituye para mí un honor y una gran satisfacción personal y académica poder comentar el trabajo de una ingeniera cuya trayectoria ha tenido un impacto profundo en la investigación, la práctica profesional y de manera muy destacada en el desarrollo de normas y códigos estructurales con implicaciones dentro de su país natal, los Estados Unidos de América, y en otros países como México. Esta misión me es especialmente grata y honrosa debido a la amistad personal, así como el alto respeto y admiración profesionales que guardo de la doctora Browning. Doctora Browning, reciba usted una muy cordial felicitación por su ingreso como académica correspondiente de la Academia de Ingeniería de México. Su designación es reflejo de una carrera ejemplar caracterizada por la excelencia académica, el liderazgo profesional y un compromiso constante con la seguridad, la calidad y la evolución de la ingeniería estructural. El trabajo de ingreso que nos presenta la doctora Browning aborda un tema de gran importancia: la relación entre la investigación, los reglamentos de diseño y la práctica profesional. En un entorno de aceleración tecnológica y creciente complejidad social, este análisis resulta no solo pertinente, sino indispensable. Uno de los méritos centrales del trabajo de la doctora Browning es que nos invita a reflexionar sobre las tensiones naturales entre la investigación, los reglamentos y la práctica. Tomando como referencia la propuesta que hizo hace varias décadas el doctor Chester Sees, académico de la Universidad de Illinois, quiero destacar que el profesor Sees visitó a México y dictó un curso de diseño de estructuras de concreto en el posgrado de nuestra universidad hace más de 60 años. El doctor Sees dejó muchos amigos y alumnos tras su estancia en nuestro país. La doctora Browning nos recuerda que el conocimiento no fluye de manera lineal, sino a través de un proceso iterativo que integra la evidencia experimental, la observación del comportamiento real y el desarrollo y la aplicación del juicio profesional. Particularmente valiosa es su discusión sobre el rezago entre la investigación y la práctica. Lejos de ser esta una deficiencia, discute JoAnn, este rezago es un elemento constituyente del juicio y la responsabilidad profesionales al aplicar las normas en proyectos cuyas necesidades no están del todo cubiertas por aquellas. Las normas y reglamentos avanzan mediante pasos graduales, equilibrando innovación con prudencia, lo que deja al proyectista la sensible tarea de ejercer su juicio profesional bajo estrictos estándares éticos. Esta discusión es por demás pertinente en estos momentos, en que 11 comités técnicos revisan y actualizan sendas normas técnicas existentes y 3 más desarrollan nuevas normas para la Ciudad de México. En efecto, la tensión entre los integrantes de los subcomités revisores y la práctica profesional de lograr normas más completas, robustas y entendibles se enfrenta a 2 tipos de colegas de la práctica profesional. Un grupo que desearía el menor número de cambios de una versión a otra, así como requisitos de aplicación sencilla, y otro grupo que aspira a apoyarse en normas que estimulen la innovación y la calidad sin sacrificar la seguridad, la durabilidad y la funcionalidad. Otro rasgo de la tensión entre las normas y reglamentos y la práctica profesional en México es con un amplio número de desarrolladores inmobiliarios, quienes desean que las normas no encarezcan sus procesos y con ello disminuyan sus ganancias, con poco o nulo interés por la seguridad y el bienestar de los usuarios de los edificios. Los redactores de normas y reglamentos enfrentan entonces la delicada tarea de establecer requisitos mínimos dirigidos a proteger la vida de los ocupantes de los edificios, de dar certeza jurídica al proceso de diseño y construcción, de fomentar la innovación, así como de mantener la competitividad de la industria de la construcción. Ello entraña un ejercicio de optimización multivariado, en donde la percepción del riesgo y daño de la sociedad, así como sus aspiraciones de calidad de vida, se deben considerar bajo una revisión del ciclo de vida completo del proyecto y un conocimiento de las expectativas sociales. Justamente, sobre las expectativas sociales, sobre el desempeño esperado de los edificios, se desarrolla actualmente un proyecto multianual para la Ciudad de México en colaboración con el Centro Regional de Investigaciones Multidisciplinarias de esta universidad. De manera consistente con lo anterior, la doctora Browning nos recuerda el papel del ingeniero civil en la sociedad. Más allá de resolver problemas técnicos, el ingeniero tiene la responsabilidad de proteger la seguridad, la salud y el bienestar de la población, así como de contribuir a la sostenibilidad y equidad de nuestras ciudades mediante el ejercicio profesional, ético e íntegro. Justo es mediante el ejercicio ético que la sociedad desarrolla un aprecio, respeto y confianza hacia las y los ingenieros civiles. Asimismo, nos reitera el papel fundamental que tiene el ingeniero estructural, el proyectista, en la evolución de las disciplinas. Como lo explicó la doctora Browning, el desarrollo, hasta como lo conocemos actualmente, del diseño basado en desempeño, ha sido gracias a un grupo de proyectistas que, con sus inquietudes e ideas, provocaron una mayor y más efectiva interacción entre la práctica y la investigación para lograr avances reales. En un entorno dominado por herramientas avanzadas de simulación, JoAnn nos recuerda lo importante que es observar. Observar antes que pensar, decía el doctor Mette Sossen, alumno de SIS y maestro de la doctora Browning. La evidencia experimental sigue siendo la base del conocimiento confiable. El trabajo también nos invita a reflexionar sobre la evolución del ingeniero estructural en un contexto inter y multidisciplinario y sujeto a varios tipos de niveles de desempeño, donde la inteligencia artificial y las nuevas tecnologías están transformando nuestra profesión. ¿Cómo se construye ya la relación entre normas y reglamentos y el ejercicio profesional con la inteligencia artificial? ¿Cómo debe ser un agente de inteligencia artificial en la ingeniería estructural? Uno que permita revisar reglamentos y normas, que ayude en la modelación estructural, que revise los resultados de modo automático, que genere documentos, como el caso de memorias de cálculo o informes, que apoye el diseño por sostenibilidad, que gestione el conocimiento y que apoye en la toma de decisiones de dilemas éticos. Estas y otras interrogantes son ya parte de las discusiones presentes para un futuro realmente inmediato. Y justo sobre este tema, y antes de concluir, quisiera reflexionar sobre el significado de este ingreso. Ser académica correspondiente implica no solo un reconocimiento, sino un compromiso con la ingeniería y con la sociedad, así como con el logro de un mayor y profundo acercamiento y cooperación entre las y los colegas de México y los Estados Unidos de América. Una cooperación que nos permita conjuntamente plantear soluciones y esquemas de atención a los problemas y condiciones que afectan a los dos países. Soluciones que sean innovadoras y viables, si bien basadas en información y evidencia comprobables. Justo cuando la doctora Browning hablaba del proyecto, el enorme proyecto NIS, que lleva el nombre de George Brown, congresista de California, caía en cuenta que el principal motor de generación, de creación de la Fundación México-Estados Unidos para la Ciencia fue justamente el congresista Brown. Y así lleva su nombre. De hecho, la oficina de la Fundación en Estados Unidos lleva el nombre del congresista, justamente un punto que no había caído en cuenta sino hasta ahorita, que une a los Estados Unidos con México, justamente a través de la Fundación México-Estados Unidos para la Ciencia. Doctora Browning, además de su destacada trayectoria académica y profesional, quienes hemos tenido la oportunidad de interactuar con usted, reconocemos su apertura al diálogo, su claridad conceptual y su genuino interés por fortalecer los vínculos entre comunidades de ingeniería de distintos países. Su liderazgo en el desarrollo de códigos, su compromiso con la formación de nuevas generaciones y su visión sobre la integración entre investigación y práctica han dejado una huella profunda en nuestra disciplina. Para México, su presencia en esta academia representa una oportunidad invaluable para enriquecer nuestras discusiones, fortalecer nuestras capacidades y avanzar hacia una ingeniería más sólida, más responsable y más cercana a las necesidades de la sociedad. Hago votos porque su participación en la academia sea activa y fructífera. Estamos seguros de que sus ideas y liderazgo contribuirán significativamente al desarrollo de nuestra ingeniería. Reciba usted nuestra más cordial bienvenida. Muy querida y respetada JoAnn, muchas gracias por años de amistad y esfuerzos e interés por promover y lograr acercamientos entre la ingeniería estructural mexicana y estadounidense. Y quisiera destacar que en el auditorio nos acompañan varias alumnas mujeres de licenciatura, maestría y doctorado, allá arriba, que seguramente para ellas será un motivo de gozo el que ingresen 2 mujeres a la Academia de Ingeniería Académicas correspondientes. Muchas felicidades por este muy merecido reconocimiento, el cual es uno de los muchos que tendrás en los años por venir. Muchas gracias.
Gracias, doctor Sergio Alcocer Martínez de Castro, de gozo y ejemplo. Ok. Le damos la palabra a la doctora Sonia Elda Ruiz Gómez, académica titular de la Comisión de Especialidad de Ingeniería Civil de la Academia.
Muchas gracias. Con su permiso. Con su permiso, señor presidente. Agradezco la invitación de la Academia a ser comentarista de este interesante trabajo. La doctora Browning presenta un artículo original en el cual primeramente hace una revisión de la relación entre investigación, códigos de construcción y práctica profesional, como la formuló el profesor Cis hace 66 años aquí en la Ciudad de México. Posteriormente presenta un análisis de la evolución de los lazos de comunicación entre estos tres grupos y propone cómo enfocarlos con el fin de elaborar códigos que incluyan conceptos de resiliencia, sostenibilidad y cubran necesidades sociales. El artículo se refiere principalmente a la elaboración de códigos estadounidenses y presenta ejemplos sobre sistemas estructurales de concreto reforzado. Sin embargo, mi opinión es que su propuesta es muy útil para la formulación de otros códigos de construcción en el mundo. La doctora hace ver que la comunicación entre investigación y práctica profesional se ha ampliado en las últimas décadas, principalmente debido a las siguientes tres razones. La primera, porque existen requerimientos cada vez más amplios para que los ingenieros de la práctica adquieran nuevos conocimientos. Efectivamente, en el mundo cada día hay nuevos y mayores conocimientos y cada día se requiere estar actualizado e inclusive contar con mayores habilidades en varias disciplinas transversales. En segundo lugar, porque los patrocinadores de proyectos de investigación requieren contar con datos e información técnica. A propósito de esto, en México cada día contamos con menos patrocinio para proyectos de investigación. Es muy deseable y necesario que se incremente dicho patrocinio por parte de instituciones tanto del gobierno como privadas. En tercer lugar, porque es más fácil el acceso a publicaciones técnicas a través de Internet. El uso de herramientas como por ejemplo el sistema Design Safe, que va a presentar nuestra compañera, la doctora, en la siguiente plática, está orientado a ayudar a resolver problemas ingenieriles relacionados con riesgos naturales en Estados Unidos de América. Ojalá que en el futuro pudiéramos tener en México un sistema similar. En realidad contamos con bases de datos, pero están dispersos. Lo que se necesita es unificarlos, que haya alguien que los unifique. La doctora Browning hace énfasis en que a medida que han avanzado las herramientas de análisis estructural, se han entrelazado aspectos interdisciplinarios con el fin de considerar los efectos de múltiples peligros naturales. En México, como en la mayoría de los países, el efecto de los sismos y del viento, por ejemplo, se considera independiente de otros riesgos naturales. Los espectros de diseño que se especifican en las normas técnicas complementarias para diseño por sismo se basan en estudios en los que se maximiza la utilidad. Sin embargo, al igual que en otros códigos del mundo, su formulación no considera de manera directa ni explícita la maximización de la sostenibilidad ni de la resiliencia, ya sea estructural ni social. En México, En México estamos prestando gran atención a las especificaciones para el diseño sísmico de edificaciones con disipadores de energía y con aisladores de base, lo cual constituye un avance sobre el tema de resiliencia, que por supuesto es un tema que va más allá de usar dispositivos de control de la respuesta sísmica o dinámica. Me llamó la atención un párrafo del artículo de la doctora Browning que dice que en algunas ocasiones se ejerce presión a los comités que formulan los códigos con el fin de beneficiar a la industria del concreto. Opino que esto es aplicable no solo a la industria del concreto, sino a la industria de otros materiales, inclusive a sistemas estructurales, por ejemplo, conexiones, sistemas para controlar el daño en estructuras, etc. Un gran tema de actualidad que toca la doctora es el uso de la inteligencia artificial. Menciona que debemos educar a los estudiantes de manera que sepan diferenciar qué resultados son aceptables y cuáles son erróneos. A propósito de esto, celebro que recientemente, hace 8 días, se haya creado el Consejo Coordinador de Inteligencia Artificial de la Universidad Nacional Autónoma de México. La doctora también hace referencia al cuidado que debemos tener al emplear grupos de datos, debido a que pueden no reflejar en lo que pasa en un medio local. Personalmente considero que algunos de estos datos podrían utilizarse selectivamente como información a priori en un análisis bayesiano. La doctora Browning opina que para la evaluación de los ingenieros investigadores debería tomarse en cuenta su contribución a la práctica de la ingeniería y a la sociedad, así como su servicio y participación en la elaboración de códigos, y no solo considerar la cantidad de publicaciones o de los ingresos extraordinarios para la institución donde se elabora. Coincido totalmente con ella y sugeriría que el Sistema Nacional de Investigadoras e Investigadores de México tomara en cuenta esta opinión. Como resultado de sus análisis, la doctora propone que en medio de la interrelación investigación, código y práctica profesional, existe un grupo de ingenieros que ella llama constituyentes, que sirva como centro de discusión y que dicho grupo haga participar al público, a formuladores de políticas, a planeadores urbanos y a científicos sociales. Añade que debe alentarse a los ingenieros de la práctica a participar en investigación y en la elaboración de códigos. Esto último es precisamente lo que estamos haciendo para la formulación de las normas técnicas complementarias para diseño por sismo, así como para otras acciones, del Reglamento de Construcciones del DF, que se editará en 2029. Finalmente, aunque no menos importante, me llamó la atención que la doctora Browning se refiriera a una estudiante de ingeniería mujer, en lugar de referirse a un estudiante del género masculino, como es muy común hacerlo. Esto demuestra el decidido apoyo de la doctora a las mujeres estudiantes que cursan ingeniería, lo que aplaudo efusivamente. Con esto termino mis comentarios. Muchas gracias, doctora Browning.
Muchas gracias, doctora Sonia Ruiz Gómez. Por último, tenemos la intervención del doctor Gustavo Ayala Milián, también perteneciente a la Comisión de Especialidad en Ingeniería Civil.
Con su anuencia. Con su anuencia, señor presidente, buenas tardes, estimados colegas, señores y señoras. Antes que entrar en materia sobre el trabajo de ingreso a nuestra academia que nos presenta la profesora JoAnn Browning, debo mencionar que ha sido un gran placer y un honor haber sido nombrado comentarista del trabajo de una profesional de la ingeniería de calibre de esta candidata a miembro correspondiente. Agradezco plenamente a la academia el haberme invitado porque nos permite mostrar que estamos vivos y que seguimos y seguiremos estando vivos. El texto de su trabajo y su brillante presentación aborda diversos temas de considerable relevancia tanto para la comunidad internacional como para la mexicana, ambas en la ingeniería estructural. En mis comentarios, en beneficio de los tiempos asignados, me concentraré en solo algunos de los puntos que en mis capacidades considero importantes. La galardonada retoma con evidente autoridad el marco conceptual articulado por Chet Sis en 1960, un documento originalmente preparado para ingenieros mexicanos en la Ciudad de México, que en ese entonces estaban elaborando un nuevo reglamento de construcción. Esta simetría histórica entre el público original y la presente presentación a la Academia Mexicana de Ingeniería resulta apropiada y constituye una de las más principales fortalezas de su trabajo. El argumento central de que el desfase temporal entre la investigación y la adopción de reglamento es una característica de la responsabilidad profesional y no una deficiencia del sistema, es sólido y defendible. La autora escribe con claridad y desde una perspectiva basada en la participación directa en comités de reglamentos, lo que confiere autoridad práctica a la obra. Las tres afirmaciones formuladas en respuesta a las preguntas que plantea el propio artículo representan conclusiones razonables para un público orientado a la formulación de políticas. Desafortunadamente, el trabajo poco se enmarca dentro del contexto mexicano, ni tampoco del latinoamericano, a pesar de la conexión institucional directa del artículo con el público original del trabajo de SIS. Sin embargo, se entiende que dado el objetivo del trabajo y la composición del público al que se dirige, la autora no presenta un tratamiento riguroso del análisis estructural no lineal y el diseño basado en desempeño. Sin embargo, sí los menciona como los pilares técnicos que vinculan la investigación con la normativa. El trabajo de ingreso a la Academia de Ingeniería reconoce explícitamente que SIS escribió su artículo en 1960 para ingenieros mexicanos, abordando de manera sustantiva la experiencia mexicana. Sin embargo, su enfoque es casi exclusivo en reglamentos como el ACI 318, el AC 7, entre otros, desarrollado en instituciones y por gremios estadounidenses. Al respecto, es de mi interés mencionar que en México el reglamento de construcciones del Distrito Federal y las normas técnicas y sus normas técnicas complementarias que se han ido configurando desde la década de los 1970, gracias a una tradición investigadora que incluye contribuciones fundamentales de personas como Emilio Rosenbluth, Luis Esteva, Roberto Meli, entre otros, todos ellos prominentes investigadores de este Instituto de Ingeniería. Estos representan precisamente el camino de la investigación a la codificación que este artículo defiende. El sismo de Michoacán de 1985 fue un evento empírico, decisivo, que demostró la brecha entre lo que se analizó y lo que se construyó en la Ciudad de México, y transformó tanto las disposiciones sísmicas de las normas técnicas complementarias como la dirección de la investigación experimental en la UNAM. Este es el análogo mexicano del colapso del depósito de la Fuerza Aérea Wilkins en 1955 y del terremoto de San Fernando de 1971, que la autora analiza en detalle. Su análisis de la infraestructura de investigación interdisciplinaria se centra exclusivamente en el NIRE y en el sistema Design Safe. En México, este análisis lo realizan las plataformas propias de la comunidad mexicana, incluyendo el trabajo del Centro Nacional de Prevención de Desastres, la red sismológica de los institutos de Ingeniería y de Geofísica, entre otros, que merecen al menos una mención comparativa. En su texto, la autora escribe: el marco propuesto por SIS proporciona una valiosa perspectiva para examinar cómo interactúan la interacción, los reglamentos y la práctica. Sin embargo, aunque el trabajo identifica correctamente el contexto histórico mexicano, reconoce explícitamente que su análisis se centra en las normas estadounidenses basadas en el consenso. En sus reflexiones sobre el análisis y el diseño estructural avanzado, incluyendo enfoques multidisciplinarios, la autora aborda lo que posiblemente sea el desarrollo más transformador desde el punto de vista técnico en ingeniería estructural desde los escritos de SIS. La transición del análisis elástico lineal bajo trayectorias de carga simplificada a métodos no lineales basados en desempeño nos describe cómo la ingeniería sísmica básica de desempeño formalizada a través del trabajo PIR y sus sucesores alteró fundamentalmente la relación entre la investigación y reglamento al introducir funciones probabilistas de demanda y fragilidad, modelos de pérdida y métricas de tiempo de actividad como objetos inmediatos que vinculan la simulación con los objetivos de rendimiento previstos en el reglamento. No se trata simplemente de un análisis más complejo, es un modelo epistemológico diferente sobre lo que se considera conocimiento válido para la codificación. Su afirmación del postulado de que las pruebas físicas siguen siendo indispensables es correcta e importante. La transición de NIS y NERI se cita como evidencia de que las pruebas físicas no podían ser reemplazadas únicamente por la simulación. El comentarista considera que su afirmación que cito, el programa NIS se basaba en parte en la idea de que las pruebas físicas podrían reducirse o eliminarse si existieran suficientes estudios y datos para validar los modelos de simulación. Este resultado, en gran medida, no se ha materializado. Termino la cita. Es la afirmación técnica más importante de su trabajo. La erudición que se evidencia en este artículo, junto con la experiencia profesional directa de la autora en comités de ACI y en la comunidad de investigación del MIRI, le confieren una autoridad genuina en el ámbito estadounidense de la materia. La tesis fundamental es correcta, la prosa es clara y el enfoque basado en los modelos de SIS proporciona una estructura conceptual útil. Este comentarista considera que las objeciones encontradas, no técnicas, sino contextuales, no son sustanciales, por lo que de atenderse son fácilmente alcanzables. En síntesis, el que comenta considera que el trabajo contribuye significativamente a la literatura sobre gobernanza de la investigación y de desarrollo de reglamentos. Antes de concluir, cabe mencionar que México cuenta con una destacada tradición en el campo de investigación, reglamentos de construcción y práctica de la ingeniería. Nuestra comunidad de ingeniería estructural ha aprendido valiosas lecciones de su historia sísmica, lecciones directamente pertinentes para el argumento de ese trabajo de ingreso. Incorporar dicha tradición de este trabajo lo fortalecería considerablemente y honraría el contexto para el que fue elaborado. Por lo que conmino a la autora a incorporar en evoluciones de este valioso trabajo esta sugerencia. En definitiva, el trabajo presentado y la trayectoria de la doctora JoAnn Browning refleja un nivel de madurez científica y profesional excepcional. Su incorporación a la Academia de Ingeniería como uno de sus miembros correspondientes no solo es plenamente merecida, sino que constituye sin duda un valor añadido a nuestra propia academia. Permítame terminar con una sincera felicitación a la candidata, expresando mi reconocimiento a una carrera que ha seguido, sigue y seguirá sin duda contribuyendo de forma definitiva al desarrollo de la ingeniería para el beneficio de nuestros países. Por mi raza hablará el espíritu.
Gracias, doctor Gustavo Ayala Milián. Bien, como nos damos cuenta, el crecimiento del conocimiento es enorme. El conocimiento crece. Crece también las profesiones, se están atomizando. Por eso debe crecer la multidisciplinariedad. La academia está cercana ya a contar con 20 comisiones de especialidades y está llamada a ello. Y hoy hemos estado viendo cómo la ingeniería civil se enriquece y enriquece a otras especialidades. No podemos solos, tenemos que integrar capacidades. Bien, vamos a pasar a nuestra siguiente ingresante, pero antes vamos a tomar una fotografía de este grupo y a cambiar por los que comentarán el siguiente tema.
Sí, para que no se vea la foto.
¿Se acabó el agua?
Something for you. Oh, this is art from the hill country in Texas. It's got a bio in there. Thank you so much for your kind remarks. Sir, I have this for you as well. Thank you for your contribution.
Thank you very much. I'll give you, I'm sorry, originally I wrote it in English, but I didn't mean it.
No worries.
But I'll give it to you when
We'll get it later.
all right. Thank you very much. Thank you, I appreciate it.
Sorry. Gracias.
Hope to see you again.
¿Qué? Esto ya no se perdió. Órale. Ellen.
Hello.
Hi.
Hey, good to see you.
Good to see you.
Thank you for coming today.
Thank you. Your bio is too extensive, so
I know.
I will have to do very short. Sorry. ¿Qué tal? Yes, because of the time. Sorry about that.
It's material to use at your discretion.
I will pick jumping some of
That's
the
fine,
things.
please. That's what it's there for.
Only 10 pages.
Cinco páginas.
Ok. Donde Dios. Bien, pues continuamos primeramente con la presentación de nuestra siguiente expositora del tema de ingreso, la doctora Ellen Ratji o Ratje. Ratji. Le voy a pedir al doctor David de León Escobedo, que ya lo hemos presentado, por favor, lea la experiencia de vida de la doctora Ellen Ratji.
Gracias, maestro Lepe. La maestra Ratji, la doctora Ratji, tiene la cátedra del centenario Janet S. Cockrell en Ingeniería. Hizo su doctorado en Ingeniería Civil en la Universidad de California en Berkeley en el 97. Su maestría también en la misma universidad y en Ingeniería Civil en el 94. Y su carrera en la Universidad de Cornell en el 93. Entre los cargos académicos que tiene es profesora desde 2018 al presente de la Cátedra del Centenario Janet S. Cockrell en Ingeniería, del Departamento Massey de Ingeniería Civil, Arquitectónica y Ambiental de la Universidad de Texas. Fue profesora de profesor centenario Warren S. Bollows del Departamento de Ingeniería Civil, Arquitectónica y Ambiental, también de la Universidad de Texas. Ha sido investigadora científica senior del 2015 al presente de la Oficina de Geología Económica, Universidad de Texas, y profesora adjunta y asociada desde el 98 al 2004 y de 2004 a 2009 del mismo Departamento de Ingeniería Civil, Arquitectónica y Ambiental de la Universidad de Texas. Algunas de sus contribuciones a la investigación ha sido consultora internacional para evaluaciones de riesgo sísmico en instalaciones nucleares en todo el mundo. Por ejemplo, laboratorios nacionales de Estados Unidos, centrales nucleares en Taiwán, Reino Unido, Sudáfrica y Polonia. Y debido a sus contribuciones significativas para comprender los efectos de las condiciones del suelo en las vibraciones sísmicas y técnicas para integrar estas evaluaciones en aproximaciones probabilistas de riesgo sísmico. Inició el desarrollo de estratos en un código llamado Strata, que se refiere a la propagación sísmica y que combina la teoría de vibraciones aleatorias con simulaciones de Monte Carlo para evaluar la respuesta del suelo. En todo el mundo se utilizan estos algoritmos para proyectos de riesgo sísmico. Strata ha sido citado más de 500 veces en artículos técnicos y ha sido descargado más de 20,000 veces desde noviembre de 2016. Otro aspecto de su contribución es la utilización de enfoques de rendimiento sísmico en laderas de tierra y presas, usando desarrollos de modelos sustitutos basados en física que predicen deslizamientos de laderas y que pueden implementarse a escala de sitio o regional. Ha evaluado estos enfoques usando historias de casos de campo e inventarios regionales. Ha desarrollado enfoques probabilistas que combinan con modelos sustitutos y toman en cuenta incertidumbre y variabilidad. Y ha demostrado que estos enfoques se pueden implementar de manera realista en la práctica profesional. Ha promovido el uso de enfoques probabilistas desarrollando scripts y herramientas computacionales que están disponibles en acceso abierto a ingenieros de la práctica. Lidera un cambio cultural en la evaluación de riesgos naturales y el enfoque generalizado en ciberinfraestructura, IC, y la publicación y reutilización ubicua de datos a través del portal de investigación Design Safe. En la ubicación en el internet www.designsafe-ci.org. Design Safe está permitiendo el uso más amplio de simulación computacional, análisis de datos, flujos de trabajo automatizado en la ingeniería de riesgos naturales. Design Safe reporta más de 10,000 usuarios de todo el mundo, alberga más de 500 teras de datos y ofrece más de 60 millones de horas centrales HPC al año. Design Safe representa el liderazgo técnico porque trabaja para impactar en la comunidad de investigación en riesgos naturales en general y en última instancia en la práctica de la ingeniería de riesgos naturales. Entre sus reconocimientos, voy a simplificar solo a 3 o 4, ha sido elegida miembro de la Academia Nacional de Ingeniería de los Estados Unidos en 2025. Impartió la conferencia Kenneth L. Lee del capítulo del Instituto Geográfico de Los Ángeles de la ASCE en 2025. Premio a la conferencia William B. Joyner de la Sociedad Sismológica de América e Instituto de Investigación en Ingeniería Sísmica 2018. Premio de la Investigación Samsher Prakash de la Fundación Samsher Prakash 2007. Premio Jared Shah a la Innovación del Instituto de Investigación en Ingeniería Sísmica 2006. Entre sus ponencias magistrales está la aplicación de la IA y el aprendizaje automático en ingeniería geotécnica, conferencia Kenneth Lee, ISCE, de Los Ángeles, Geo Institute, Long Beach, California. Aplicación del marco SSHAC para tomar en cuenta incertidumbres en el análisis de respuesta de sitio, en la conferencia de la Society for Earthquake and Civil Engineering Dynamics de la Universidad de Cambridge, Reino Unido, en septiembre de 2023. Avances en la evaluación regional de deslizamientos sísmicos, conferencia magistral en la 17ª Conferencia Colombiana de Ingeniería Geotécnica en Cartagena, Colombia, en 2022. Entre sus actividades profesionales de liderazgo, fue presidente del Instituto de Investigación en Ingeniería Sísmica de 2025 al presente. Es directora de Design Safe Cyber Infrastructure de 2015 al presente. En su servicio profesional, presidente del Consejo Asesor Científico Internacional del Centro Quake Core para la Resiliencia Sísmica en Nueva Zelanda, de 2021 al presente. Comité Asesor para Ciberinfraestructura de la División de Ciberinfraestructura Avanzada de la Fundación Nacional de Ciencias, de 2019 a 2022. En su experiencia en consultoría está su participación en el Polski Elektrowine Jądrowy, Energía Nuclear de Polonia, presidente del panel de revisión participativa por pares para el análisis probabilístico de riesgo sísmico nivel 3 de SSHAC para instalaciones nucleares en Lubiatowo, Copalido, de 2024 al presente. Ha participado en Alberta Justice, compareciendo como testigo experto técnico en cuestiones relacionadas con los impactos en una presa por el temblor causado en el por fracturación hidráulica, desde 2023 al presente. Participa en el Slate Geotechnical Consultants, miembro del equipo de integración técnica para actualización aumentada del análisis probabilista de riesgos sísmicos nivel 2, SSHAC, en el Laboratorio Nacional de Los Álamos, en Estados Unidos. Miembro del Consejo de Ciencias en Sudáfrica, participa en la integración técnica del estudio SSHAC nivel 2 de riesgos sísmicos aumentados y evaluación de respuesta de sitio para la central nuclear de Doinefontein en Sudáfrica. Participó como consultora de Pacific Gas and Electric en un proyecto de desarrollo de herramientas de riesgo para deslizamientos en el área de la Bahía de San Francisco de 2022 a 2023. En la Alianza de Energía del Instituto Batel, miembro como revisora de el análisis probabilista de riesgo sísmico, SSHAC, nivel 3, para instalaciones nucleares en el Laboratorio Nacional de Idaho, de 2019 a 2022. Y con la empresa Riso International, miembro del equipo de integración técnica para el análisis de respuesta del sitio SSHAC nivel 3 para la instalación Pantex 2021-2022. Y en el Centro Nacional de Investigación en Ingeniería Sísmica, NCREE, miembro del equipo de integración técnica también para el proyecto SSHAC nivel 3 del espectro de respuesta del movimiento de suelo para instalaciones nucleares en Taiwán, de 2018 a 2021. It's our pleasure, Professor Razi. Thank you very much.
Gracias, doctor David de León. Ahora escucharemos el trabajo de ingreso de la doctora Ellen Ratji, la evolución de la ingeniería de peligros naturales mediante la ciberinfraestructura Design Safe.
Well, thank you so much for all being here. It really is truly an honor and a privilege to be part of this cohort of inductees into the Academy. It's wonderful to have this opportunity today to talk to you about Design Safe, and specifically the evolution that has taken place in natural hazards engineering due to the presence of Design Safe, but not only Design Safe itself, but some cyber infrastructure projects that were predecessors to Design Safe. As Dr. Browning mentioned earlier today, Design Safe is just one component of NERI, and so as such, Design Safe has benefited so much from collaborating with all of the NERI components. And additionally, I would be remiss if I did not say that we have an excellent partner at the University of Texas with TAC, our computing center, who really does a lot of the heavy lifting and software development for some of the advancements we're going to see today. So with that, I will try and get to the next slide. There we go. I don't need to tell people in Mexico City the impacts of natural hazards, in particular earthquakes. You have experienced it firsthand. You've seen how soil impacts ground shaking and ultimately influence damage patterns here in Mexico City in 1985 and another earthquake since then. So earthquakes has always been kind of my foundational natural hazards that I'm interested in, but over the years we know, and we saw in JoAnn's presentation, that other natural hazards are also having a big impact on our cities and our societies. We have hurricanes where the storm surge can take out incomplete coastal towns, or the wind can cause considerable damage over huge areas. So we're worried about windstorms as well as earthquakes. And now with climate change impacts, we see so many more wildfires. We need to understand how wildfire evolves, how it moves, and how it can take out large-scale communities. And similarly, large-scale landslides, which are also being influenced by climate change due to differences in precipitation, et cetera. So these are the natural hazard impacts that we're trying to minimize through natural hazards engineering. So if we think of the role of natural hazards engineering in reducing those impacts, it starts with the hazard themselves. So we want to improve our hazard forecasts. And of course, for every type of hazard, it's a different science that we're dealing with, a different type of physics. So whether we're talking about earthquake shaking, hurricane or tornado wind speeds that we need to design our structures for, storm surge or tsunami, where will the water go and how far inland will it go? How does wildfire spread from one home to another home or go from the countryside to the urban interface? And then those movements of landslides and how they can impact large-scale communities. So all of these things start with understanding the hazard forecast, but a hazard is only a hazard if there's no infrastructure. And it becomes a disaster or a risk when we're worried, when we know that there will be infrastructure to be impacted. So with those hazard forecasts, we need to understand the response of our buildings, our bridges, our pipelines, et cetera, as well as our societal responses. How do people respond? Where do they go? How are they impacted? And then, of course, what is the ultimate infrastructure damage and damage to our societies? So we're trying to really understand and minimize all these things through our research. Now, if we think about any research, and I want you to think now not even only about natural hazards, it could be any type of research you do, there's really three main components, and it all starts with data. Now, for many years, we've thought of data as simply being experimental data, something we pull in the lab. But I want to challenge us all to think that data is not just experimental data. It can be simulation data. It can be simulation outputs. It could be simulation inputs. It could be data we collect in the field. But generally, everything starts with data. And then we want to do something to it. We want to analyze it. We want to throw it through an algorithm. We want to use a tool for which it is input. And so that data gets integrated with these tools, and those tools have to run somewhere, and so then we need to worry about computational resources. So we have these three components, but the key is, how do they get connected? And that has often been coined the missing middle, and that is where cyber infrastructure resides. So for many of you, cyber infrastructure may be a new word today, and so this hopefully describes and explains where cyber infrastructure and what that means within our context. And it is here where Design Safe resides, where we're really trying to co-locate the data, the tool, the computational resources, so that we can enable research that couldn't be done otherwise. So with that as a little bit of background, here's the outline of what I'd like to present today. I'm going to start with a historical perspective, and JoAnn did a good job kind of starting that historical perspective with NEAS, because I will also be talking about the George E. Brown Network for Earthquake Engineering Simulation. But I'm going to first make the case for data publishing, which is one of the initial focus areas of the NEAS cyber infrastructure. Then, after going through the previous perspectives, we'll talk about Design Safe specifically, which has been operating since 2015. We'll talk specifically about our data repository called the Data Depot, as well as our tools and applications that are available to the global research community. And then we'll get a little bit more into the specifics of Design Safe, some usage metrics, which you heard a little bit about. And then, since everything is a bit abstract, I'm going to want to try and give you some concrete examples. I just had to say that for my concrete friends. Some concrete research examples that are actually related to slope stability, where you can see how the cyber infrastructure has influenced the work that we've been able to do. So with that, let's think about this traditional workflow. We generally generate data, and I'm a geotech, so you can see it could be lab data, triaxial testing, it could be out doing some cone testing, it could be some simulation data. We then analyze it. Back in the day, we might use Excel. Today, we might be using Python or MATLAB or more advanced tool analysis approaches. And then it ended with disseminating the results. We wrote a paper, we, cheered ourselves on, we congratulated ourselves, and we were done. But the question then became, what if you wanted to use that data again a few years later? It might be in a filing cabinet. It might be on a certain type of floppy disk that you have absolutely no idea how to access. And that's even if you know where it is, right? And the question then becomes, can you even reproduce what you did just a couple of years ago? And can you integrate those data with other data that has now come along and can supplement and complement that data. Now at Design Safe, we really wanted to hammer this idea home, so we made this little kind of infomercial commercial that I'm going to want you to watch.
Dear Vasant, I hope the new job is going well. I have good news. The reviews for our paper are back, and we just have to update figures 6, 8, and 10 with the latest data. Can you do that within the next week or two?
Well, Peter Lee has those data sets. I don't know what those data are.
Can we ask Peter then? Do you have his contact info?
He's in China.
I know, but do you have contact info?
No.
Do you know where the data might be? Or where he left his lab notebook with all the metadata?
The meta what?
Metadata. The labels for all the columns of data. Units for all the data. That kind of thing.
Oh, well, maybe the wind tunnel computer? Maybe the portable hard drives? Maybe that white box in the grad student office closet? Maybe the Google Drive project folder.
So, has that happened to you? You wanted to find data and you did not know where it was. And I have to acknowledge Fred Hahn, who is a partner in Design Safe, a wind engineer at Calvin University, who thought up that idea of putting that video together. So, you can think about publishing and sharing data can be a benefit for you, and that's exactly what that video was about. But let's also think about how making data available can help the broader research community. And let's think back. What about if we had access to data from some of the landmark studies that we read about as graduate students? And I don't mean the paper, I'm talking about the actual data themselves. So just as two examples, and I did make them structural engineering examples, at the University of Illinois, Meta Sozin, we've heard a lot about him today, he was one of the first to really build a large-scale shake table where you could test large-scale structures and understand their hysteretic response. Well, in this 1970 paper, it was really the first time they had published hysteretic responses from shaking tables and compared it to analytical predictions. Now, these are great graphs from that paper, but I'm sure there was a lot of data collected during those experiments that never made it into the paper that today could be used by others to understand other phenomena. A little bit closer to home here for you, what about the damage statistics from the 1985 Mexico earthquake? This is an amazing data set published in Concrete International by Rosenbluth and Professor Melli from here at UNAM. But most of what we have here is just a table of buildings of different types of structures, the extent of damage, the year built, the number of stories, which is amazing. But this was really a synthesis of a much larger data set that could be explored in so many different ways if that data were available. And it may be in one of the offices somewhere in this campus right now, but it's not available to the broader research community. So, and in fact, even to get this paper, I actually had to ask the ACI president to download it from me because I could only get Concrete International if I was an ACI member, and I'm not an ACI member. So I think what you can see here is that the availability of broader data can really enhance research discoveries today. So if we think about the past, it can affect today, and if we think about today, we can affect the research that happens tomorrow. So NICE started about 26 years ago with one of its goals was to have data published from these experimental facilities that would be available in the long term. And so NICE started with a 4-year development phase, which is where the 15 experimental facilities were kind of built out and created. The management consortium was organized, and then the NICE grid cyber infrastructure was developed. Now, I started as a professor in 1998. So in 2000, at the University of Texas, I was not involved with the cyber infrastructure. I was actually involved as an experimental facility, because Ken Stokey, my colleague, led a team that I was part of to buy these large-scale shakers to use for geophysical testing. So I was involved with NICE from day one, but as an experimental facility, working with the people not only doing experiments, but developing the cyber infrastructure. And the NICE grid goals were lofty and ambitious, particularly when you think this was the year 2000 when this started, right? A curated data repository. I still think it took us almost 10 years to figure out actually what that meant. They wanted to have tele-observation and tele-operation of experiments. Not just observation, operation. I mean, there was no Zoom in 2000, right? You know, how are we going to observe that? They did talk about computational resources and open source tools, things we're still talking about today. And then collaboration tools for planning, et cetera. So these were very, very lofty goals. Unfortunately, after the 4-year development phase, it was clear that there was a mismatch between the software developers developing the cyber infrastructure and the researchers in civil engineering. Like, our skill sets were miles and miles apart. They gave us something that we had no idea to use. There was no website. They said, oh, here's a API. That's not the American Petroleum Institute. That's an application program interface, right? In 2004, we just had no idea. And so when NICE went to operate in 2004, they recompeted the cyber infrastructure. And it was taken by a different entity. So for NICE, an operation phase, which I call Part 1, which goes from 2004 to 2009, we still had our experimental facilities, we had our management consortium, and we had NICE IT, and they built NICE Central. And the goals were pretty similar to what the NICE grid had proposed previously. You know, they had a different graphic. They talked about data curation and organizing data, how to reuse data. Nice little graphic here. They had some simulation. WebEx was around at this point, so we could actually do some teleconferencing. But similarly, the IT, or the cyber infrastructure component, was being led by software developers, not by the people who would need to use the software. And yeah, we talked, but we talked like once a year, twice a year, and then they went off and came back, and there really was very little that we could use. And so in 2009, there was a recompetition for all of NICE, and that's where it landed in 2009, and where JoAnn and I started working as part of the Produce team for the NICE Hub cyber infrastructure. We lost an experimental facility along the way, but we still had a management consortium. But NICE Hub, which was being built off of the successful Nano Hub cyber infrastructure that had been built at Purdue, we started on this process. And the key here was that people like me and JoAnn were leading the cyber infrastructure development. The software developers worked for us. We weren't working for them. And I think that is what made us successful with NICE Hub. We had an actually functioning website that had very useful information. We had the project warehouse where people were publishing experimental data from our experimental facilities in a way that was manageable. I can navigate this as an engineer, and I can see where there says file browser experiments. I'm going to find data. That's how I'm going to find my data. And so we were very fortunate to have that experience leading the cyber infrastructure component, and quite successful. Then came NERI, and there was we've heard a little bit about it, and again, everything was recompeted. So NERI has been operational since 2015. As JoAnn mentioned, we have a network coordinating office. We have 7 experimental facilities. We have a rapid reconnaissance facility that goes out after extreme events and natural hazards and collects field data. We have a simulation center. And then, of course, we have Design Safe. And I like putting this all, it's really kind of encapsulated in a circle where NERI encapsulates the NCO, the coordinating office, and then the physical experimentation, the digital experimentation, as well as looking at social impact and field reconnaissance. And it was here that I've been leading the Design Safe effort with the Texas Advanced Computing Center since 2015. So what are the components of Design Safe? They're going to kind of look similar to what I've talked about a little bit already. We have data. We have the data depot, and I am proud to announce all data that was published in NESHub was transferred to Design Safe, so it continues to be available now, almost 20 years after we started. We also have a reconnaissance portal, which is where you can get easy access to that post-event reconnaissance data. So kind of two different ways to look at data. We've tried to lower the bar of entry to using high-performance computing, and that's where our simulation and data analytics are supported in our tools and applications section. And of course, we have user guides, use cases. We've got our learning center with webinars to help you understand how to use all the resources that we've developed. But I want to focus on the data repository and then the tools and applications. So one thing that is a little bit different in Design Safe versus the other cyber infrastructures is we want people to be using the data depot as a collaborative space to share data with their research teams before they publish it. So when a user logs in to the Design Safe and goes to the data depot, you can see there are private sections. It says my data, it says my projects, and all of that is private. And it's not until you decide from a project to publish that it goes into the public section. So it's the same way as if you're doing a research paper and you're working on it, doesn't get published, so you send it to the journal, they review it, and it gets published. So we have a way to be part of the full research life cycle, so to speak, from data creation, data analysis, and ultimately to data publishing. And this is just a screenshot of what Design Safe Data Depot looks like when I log in. And these are all of the projects that I'm involved in right now. Now, one of the really important things I think that we did with the Data Depot is realizing that we wanted to give power back to the people. We wanted to give power to the researchers to organize the data as they wanted to. Previous iterations of cyber infrastructure said, you must have this, you must have that, you must have this, and sometimes that was a pain to do. Oh, I need that raw data of voltages. I don't even want that. Who's going to use that? And I still remember a colleague at UC Davis saying, I want tools, not rules, and it stuck with me. So we've tried to provide tools so that you as a researcher can organize the data as you think it should best be organized so that others can reuse your data. So this is what a published data set looks like. I figured since we're an earthquake country, I would highlight a seismic project. This comes from the UC San Diego large-scale shaking table. It's a 6-story mass timber structure with different types of energy dissipation that they looked at. You can see in some ways it looks like a paper. It's got a title, it's got a description, and then as you move down, you can start to get to where the data reside. Now when we get to the data, we help you organize it, but these titles are exactly what you want them to be, but you have to describe the model, you have to describe where the sensors are located, and then you describe the data. So we give you like a framework for you to organize your data, and they have a nice visual representation to help you navigate through all the data files that are there. So this is what a data set will look like when it's published, and hopefully someone else will look at it, potentially use it. But if they're going to use it, you want them to cite you. You want credit. This is a lot. This is work. I don't want to scare you. It is work. It's not too much work, but it is certainly work that you want to get credit for. And so every project, every published data set, you will see this wording, how to cite the data. It's got authors, it's got title, it's got Design Safe, where it's from, and importantly, it has that DOI, the Digital Object Identifier, which is a digital link that takes you right to the data set. And if someone reuses your data, they should cite your data in the references list, just like this, in the same way they would cite your paper. I see a lot of people citing data like in the acknowledgments or something. It's harder to track data reuse if you're not citing it in your reference list. So if you take one thing away from this talk, cite data in your reference list. The other thing that we're trying to do to help researchers understand what's happening with their data is, you can see we look at data downloads, data usage. Obviously, data has to be used and accessed before someone can use it and publish with it. So the first step is understanding how many people are doing downloads, and we have different ways to measure that. These are all using make data count criteria that have been developed. So we're tracking that quarterly, and then we're also tracking data citations. So we're trying to be your Google Scholar for your data, not just the Google Scholar for your papers. And so you can see these are the papers that have cited the data from this project. So really trying to help you get credit for that reuse of data. So now what about the tools and applications? So within DesignSafe, we really want to, as I mentioned earlier, lower the bar of access to high-performance computing, high-end data analytics, AI, machine learning, and that means co-locating data, tools, and resources, and that's what we do here. And we have lots of different types of tools that you could use. Perhaps you're interested in numerical simulation. We've got storm surge codes. We have OpenSeas, a finite element code for seismic applications. Commercial codes like ANSYS. So we allow you to, we help you do these simulations and take advantage of the high performance computers at the Texas Advanced Computing Center without needing to be an expert on how to get on the command line there and manage all of those things here. It's all web based, and I'll show you a little bit about that. You probably have heard of Jupyter. So our Python notebooks that really help interact with your data. So we have our entire Jupyter hub where Jupyter notebooks are available along with the data that you want to analyze. So you can actually do your simulations in the cloud in DesignSafe, dump your data into a project, post-process it with Python using Jupyter in the cloud, and then when you're ready to write the paper, all you do is download a subset of that data as opposed to filling up your hard drive with lots of data. You see we have MATLAB, we have other type of codes as well. I figured I would at least mention a little bit about OpenSeas as an example. So here we've got on the OpenSeas page, we've got links to webinars where you can learn more about how to use OpenSeas on DesignSafe. We have links to the user guide. And then down the right-hand side, you see we actually have multiple versions of OpenSeas that take advantage of different computing resources in different ways. And through our training, we help guide you to figure out which tool is right for the work that you do. So this idea of democratizing high-performance computing is to help train people to best use this. And then ultimately, you may come in, we lower the bar of access, you come in here, but then we want to train you to ultimately become a power user if that's where you need to be. So in moving towards impact and usage, we've seen over the 10 years that we've been in existence, that we have over 10,000 registered users that are using DesignSafe. We have over 2,000 data sets that have been published with DOIs. They encompass 50 million files, that's a lot. They've been accessed or viewed 800,000 times. So people are looking at the data. In terms of high performance computing, we're supporting 50,000 jobs, and here I mean like simulation jobs. I gave this talk somewhere and someone thought we actually created 50,000 jobs. I was like, no, these are computing jobs. In the last year, about 60 million core hours per year, so a lot of computing happening. And then you can see the plethora of tools available in DesignSafe. How else can you measure impact? One way to do it, and it's kind of like, this is kind of like the H-index for design safe, right? That's often, as academics, we're worried about our H-index, how many people have cited the work that we've done. Well, when we look at research that has been enabled by design safe, that work has been cited 17,853 times. So we are seeing design safe out there. What gets me really excited is when I hear someone talk about design safe and I have no idea who they are. Because I know that they're not just my friend who's using design safe because they like me. And so it is exciting that we are starting to see, you can see the slope on that curve is certainly curving up. The last thing to mention specifically about design safe and our data repository is that we are certified by the Core Trust Seal organization, which looks at data repositories and judges them on 16 different criteria, and you need to meet certain levels of certification within those different 16 components in order to be certified. And so this is actually quite a long process, and we had to have our documentation right, understanding how things are backed up, et cetera. And in fact, you can see fewer than 5% of data repositories around the world have gone through this process successfully to become Core Trust Seal certified. So we're quite proud of that. So with that as background of what is design safe, let me take you into my geotechnical earthquake engineering world to explain how design safe has influenced some of the work that I've done. And as you heard mentioned, some of the work that I do is on the seismic performance of earth slopes and earth dams. And in both cases here, what we're generally interested in predicting underground shaking is how much will the ground move. Will it be an inch? Will it be 2 centimeters? Will it be a meter? Will it be many meters? Will it be a kilometer? So the way we do that clearly is we look at, the one way to do that is through simulations where we're trying to predict some sort of downslope seismic movement, which I'll call D, due to the earthquake shaking. Now, traditionally, for many, many years, we've used sliding block approaches for this type of assessment. And this assessment starts with looking at our earth slope and do a what we call a pseudo-static analysis, probably should be called a pseudo-dynamic analysis. When we look at critical slip surfaces, and we look at what horizontal acceleration will bring the factor of safety equal to 1, so incipient failure. And we call that the yield acceleration. So KY is what we call the yield acceleration. So that level of acceleration should bring us to failure. And then after we did that hard work in our limit equilibrium slope stability analysis, we simplify the model and say we're going to treat the sliding mass as a rigid block sliding down a plane. And then we excite it with a ground motion, and as you can see, I'm afraid to see if this will work. Ooh, look at that. So we have, say, an acceleration time history. Yield acceleration is 0.1, and every time the acceleration exceeds 0.1, we get some cumulative downslope movement that is going to accumulate over time, and in this case, you can see after that motion went through with a KY of 0.1, we have about 22 centimeters of displacement. Then we can decide if that's too much. But of course, this is a simplified version of the real world. Every numerical model is a simplified version of the real world. But this one has some very important assumptions. We are assuming all of the movements that we're computing are localized on a very well-defined slip surface. We're saying that's the only place movement occurs. And it only occurs once the strength is exceeded. If the strength is not exceeded, if the yield acceleration is not exceeded, there is no displacement. And myself, as well as others through the years, have run thousands, hundreds of thousands of sliding block analyses focusing on the ground motion characteristics, as well as the slope sliding mass properties that are important to predict displacement. And we've developed what have been called empirical surrogate models, where we can give a practicing engineer an equation that says, if you know the yield acceleration, KY, if you know something about the sliding mass, say it's period of the sliding mass, TS, some characteristic of ground shaking, peak ground acceleration, peak ground velocity, you can predict the displacement. So they don't have to do that time series analysis, the sliding block analysis. But these predictions still are based on a very simplified version of the real world. So in this day and age, of course, we should be moving on to stress deformation analysis, either in finite elements or finite differences, where we can model the slope, we still subject it to a time series, and then we compute the displacement time series on the slope surface, inside the slope, and we can calculate displacements wherever we want, and then can evaluate if the overlying infrastructure is going to be damaged based on that displacement. And on specific projects, high-end projects, this may be done in practice, but they always start with some sort of empirical sliding block analysis to see if it's a problem and it warrants going to this level. But the question is, why not just develop the surrogate model from displacements that were computed from a better physically grounded simulation, such as finite elements? Because there is no assumed slip surface when you do a finite element analysis. Deformations do not need to be localized in the finite element analysis. We can fully model the nonlinear stress strain response, so we no longer are going to do rigid, perfectly plastic, which is essentially what the sliding block analysis assumes. And it will accumulate movement even before failure happens. But now we need to perform a much more sophisticated analysis, and we have to run it a lot of times. And so that means we need computational resources. And that's where Design Safe helped us in this case, and kind of similar to what Adolfo was talking about earlier today with using the computing resources at UTSA. So what did we do here? We developed 49 slope models and ran 1,051 ground motions through every single one of them. So we're talking about 50,000 nonlinear finite element analyses. We needed to vary the characteristics of the slope, so we varied the height of the slope, the depth of the soil below the toe of the slope. So you can see this is the kind of slope forming materials that go a depth D below the height of the slope. We have different slope angles, beta, between 20 and 40 degrees. We did different strengths using more coulombs, C phi, or some phi equal to 0 analyses. And we varied the stiffness or the shear wave velocity between 200 and 400 meters per second. So those were our finite element models. And then our 1,000 plus ground motions, I like to look at them in terms of plotting peak ground acceleration for each motion relative to the peak ground velocity of the same ground motion. So you can see there's orders of magnitude of intensity represented here. So anywhere from about 0.01 G to about 2 G in terms of PGA, and PGV is about 1 centimeter per second to about 200 centimeters per second. And a wide range of magnitudes and distances represented. Because we weren't trying to fit to a specific spectrum, we wanted anyone to be able to use this no matter where they were, no matter what their hazard level was. So we took all 50,000 displacements and developed a regression model, and it was relatively simple. There's a couple things here to point out that are relevant. So we're trying to predict the natural log of displacement as a function of one ground motion parameter and its peak ground velocity. If you've ever heard me talk about this before, I love peak ground velocity. It's my favorite ground motion intensity measure. My graduate students joke that is my third child because that's how much I love peak ground velocity. So that is our ground motion parameter. That's all we need. And then, interestingly, what we saw, which was really no one had identified previously, is how the distribution of displacements were different depending whether we had a shallow or deep slip surfaces. So we actually had different models for shallow versus deep sliding. So up top here, you can see the shallow slip surface. The black line is what our limit equilibrium analysis provided. The colors represent the displacements, and you can see the highest displacements are concentrated within that slip surface. But look at how much distributed shear is below the slip surface. Clearly, that assumption of localized, well-defined displacement is completely being violated here. So it's good that we're doing this analysis. The deeper slip surfaces, more agreed with our previous assumptions. You can see the deep slip surface, almost all the displacement, but not completely all of it happens within the slip surface. So we actually came up with two predictive models for displacement, one for shallow, which was defined where the depth of the slip surface was less than 60% of the slope height. So that's what H ratio is, the thickness of the slip surface relative to the slope height. So if it's shallow, if it's less than 0.6, and deeper if it's greater than 0.6. Interestingly, the deep slip surfaces were a function of yield acceleration, but the shallow slip surfaces, the period of the slope mattered, and in some ways, the yield acceleration had only a very minor impact, which was something quite surprising. But given this distributed shear, in retrospect, perhaps was not quite so surprising. But one thing really bothered me about this model that we developed. The two models do not agree at 0.6, H ratio of 0.6. They should, right? There's nothing different between 0.59 and 0.61. But the models weren't developed to explore that region. We hadn't even thought of H ratio when we developed our models. So we just could not come up with a functional form that would make it a continuous variation of H ratio. So then comes in our good friend, AI. So we decided to see what a neural network would allow us to do. Take the same exact data into the neural network, and we used as input KY, TS, PGV, and H ratio itself as one of the input parameters. And what's shown here is just some of the predictions, and it helps illustrate why this was so powerful. So we've got displacement versus yield acceleration. This is for a PGV of about 20 centimeters per second. And the four colors are for four different values of H ratio. So the deep slip surface in green, H ratio of 1.6. And then the black one, on the other hand, is really shallow, 0.2. Look at that. KY almost doesn't matter here, but for the deep it does, which is what we had seen before. But now what you see is for KY, for H ratios in between, you see we go from here to here to here to here. So the neural network was able to identify those trends, which were not very clear to us when we were looking at the data. So we had a continuous variation of predicted displacement with H ratio. And even though we allowed the model to use T-slope and KY all the time, look what happened here on the right-hand side. This is the prediction for deep, H ratio of 1.6, and 3 values of T-slope. Well, the neural network says, well, you gave me T-slope, but I don't care. I'm giving you the same answer. Whereas for the shallow slopes with H ratio of 0.2, you can see, again, flat, but the big effect of T-slope. So again, trends that were hard to identify in that large data set, the neural network was able to identify. Now, I should not be standing here if I don't put my money where my mouth is, as they say in the US, which means that data that we used and developed for those two studies are all published on DesignSafe. So this is our published data set related to that work. You can see we've got not only, we've got the actual, we did these in LS Dyna, not OpenSea, so we have the actual models themselves, all the ground motions that we used to run the models, and then all the compiled output, those displacements, and the KYs and the H ratios. We also have scripts that do the predictive models from our paper. So rather than you making sure you have to code it up right, you just come here and you can use it. And of course, we've got our DOI so people can reuse it. And I've already been at conferences where people were trying to explore different AI machine learning techniques and they were using this data set. They didn't have to go do a 50,000 simulations. All they wanted to do was test like different AI machine learning models. So of course, we're accelerating research right there. So with that, I want to close by with some thoughts on where I hope we're going, and maybe we're already somewhat there in extending the research life cycle. So when I started my talk today, we talked about this idea of generating data, analyzing data, then disseminating data by publishing a paper. Well, I hope now we will be not only publishing that paper, but also publishing that data set. But it goes beyond that, because if you do it and your friend does it and this other colleague does it, now we have 3 sets of related data, and maybe there's a little bit of there's some holes in that data, so you collect some more new data. You put all those data together and analyze it, and again, still publish the paper, and it is still valuable to publish the aggregated data set. And if we do this, I hope that there will be a web of data and researchers that will be accelerating our research discoveries far into the future. Thank you.
Muchas gracias, doctora Ellen Raggi. Interesante trabajo. Tenemos 3 intervenciones para comentarios al trabajo presentado. La primera de ellas por el doctor Juan de Dios Alemán, académico titular de la Comisión de Especialidad de Ingeniería Civil. Le ruego tomen la palabra. ¿Tiene un apagador, Rodrigo?
Okay. Gracias, señoras y señores, doctora Ellen Raggi, distinguidos miembros de la Academia de Ingeniería, colegas. Es para mí un verdadero honor participar en esta ceremonia y comentar el trabajo de ingreso de la doctora Ellen Raggi, titulado La evolución de la ingeniería de los recursos naturales mediante la ciberestructura de Design Safe. Lo hago con todo el sentido de responsabilidad que exige un acto académico de esta naturaleza. El texto que hoy nos convoca tiene una virtud poco común. Habla de una plataforma tecnológica, sí, es cierto, pero en realidad trata de algo mucho más profundo. Trata de cómo una comunidad científica aprende a conservar su memoria, a compartir su inteligencia colectiva y a ampliar sus capacidades para comprender y enfrentar los peligros naturales. En otras palabras, no estamos ante una simple descripción de una herramienta digital, estamos ante una reflexión madura sobre la evolución de una disciplina y sobre la infraestructura intelectual y técnica que esa disciplina necesita para avanzar. Quisiera comenzar destacando un primer mérito del trabajo de la doctora Raggi, su capacidad para reconstruir una historia larga, compleja y aleccionadora. La doctora Raggi nos presenta a Design Safe como un producto terminado que aparece de pronto, no lo resuelve de esa manera, de manera automática. Al contrario, lo sitúa dentro de una trayectoria de más de 25 años de aprendizaje institucional, desde NIST Grid, NIST IT, hasta NIST Hub, y finalmente Design Safe. Esta reconstrucción histórica es especialmente valiosa porque muestra que la innovación científica no depende solamente de tener mejores algoritmos o más capacidad de cómputo. Depende también de entender a la comunidad usuaria, sus prácticas, sus lenguajes, sus necesidades reales y sus resistencias. Uno de los pasajes más esclarecedores del trabajo es precisamente aquel en el que se reconoce que los primeros esfuerzos de esta ciberinfraestructura no lograron una adopción fácil, efectiva, porque existía una brecha entre la visión de los desarrolladores y la experiencia cotidiana de los investigadores. Es decir, por un lado había un grupo de desarrolladores y por otro lado un grupo de investigadores que tenían que utilizar esa herramienta y que no siempre fueron consultados. Esa observación, formulada con honestidad, contiene una lección de gran alcance. En ingeniería, la tecnología útil no es la que simplemente existe, sino la que logra insertarse de manera natural en el flujo del trabajo científico. Y es ahí donde la aportación de la doctora Raggi resulta notable. Su texto deja ver que el éxito de Design Safe no radica solamente en su arquitectura tecnológica, sino en haber comprendido que una plataforma de investigación debe diseñarse con la comunidad y no solo para la comunidad. Este me parece uno de los rasgos más originales del trabajo de la doctora Raggi. La doctora no concibe la estructura digital como un accesorio externo a la investigación, sino como una parte constitutiva del descubrimiento científico. En su visión, el repositorio de datos, las herramientas de análisis, los Jupyter Notebooks, los recursos de cómputo de alto desempeño y los mecanismos de publicación con identificadores digitales no son piezas separadas, son eslabones de una misma cadena de valor científico. Gracias a esa integración, la investigación deja de estar fragmentada entre discos duros personales, scripts imposibles de rastrear, archivos sin contexto y barreras de acceso al supercómputo. Lo que emerge es un entorno en el que los datos pueden conservarse, los procesos pueden reproducirse y el conocimiento puede circular con mayor rapidez y trazabilidad. Hay aquí una contribución de fondo para el análisis de riesgos y peligros naturales. En este campo, los fenómenos que se estudian son complejos, multiescalares y profundamente heterogéneos. Requieren integrar observaciones de campo, resultados experimentales, simulaciones numéricas, imágenes de satélite, series temporales, registros geotécnicos, variables sociales y evidencia histórica. Tradicionalmente, esa diversidad de fuentes ha hecho muy difícil construir bases de conocimientos acumulativas y comparables. El trabajo de la doctora Raggi nos recuerda que si queremos una ciencia del riesgo más robusta, necesitamos infraestructura que hagan posible esa integración. Design Safe aparece entonces no solo como un repositorio, sino como una condición habilitante para una investigación más abierta, más reproducible y también más ambiciosa. Me parece especialmente importante el énfasis que el texto pone en la publicación formal de datos. Durante mucho tiempo, en muchas áreas de la ingeniería, el producto legítimo del investigador parecía solamente el artículo. Los datos quedaban relegados a un plano secundario, útiles para quien los generó, pero pocas veces disponibles para otros. La doctora Raggi plantea con claridad que esa lógica ya no es suficiente. Los datos son también un producto de investigación y merecen curación, documentación, reconocimiento y citación. Esta es una información de enorme trascendencia académica y ética. Supone reconocer que detrás de cada campaña experimental, de cada reconocimiento post-evento, de cada simulación masiva, hay una inversión considerable de tiempo, dinero, talento y esfuerzo colectivo. Publicar sus datos con estructura, metadatos e identificadores de objetos digitales, los DOI, es una forma de honrar ese esfuerzo y de multiplicar su valor social y científico. En ese punto, el trabajo adquiere una relevancia especial para quienes trabajan en riesgos, porque los desastres dejan huellas efímeras y muchas veces ventanas de observación muy breves. Si los datos no se preservan bien, perdemos no solo la información, sino oportunidades de aprendizaje para generaciones futuras. La mención que hace la autora a conjuntos de datos históricos, incluidos los relativos al terremoto de 1985 en la Ciudad de México, es particularmente significativa. Nos recuerda que los grandes eventos no solo producen daño y dolor, también generan evidencia invaluable que, si se organiza adecuadamente, puede seguir enseñándonos décadas después. Esa sensibilidad es por la memoria científica, es una de las cualidades más notables de ese trabajo. Otro gran aporte del texto es mostrar que la democratización del acceso a herramientas avanzadas no es una consigna retórica, sino un problema concreto de diseño institucional y tecnológico. Design Safe, tal como lo presenta la doctora Raggi, reduce barreras de entrada al cómputo de alto desempeño, permite que investigadores con distintos niveles de experiencia accedan a recursos por varias vías, desde interfaces web amigables hasta entornos Jupyter y flujos más avanzados en líneas de comando. Esto es particularmente relevante en una comunidad donde no todos los grupos cuentan con la misma infraestructura local, el mismo apoyo técnico o los mismos presupuestos. En este sentido, el trabajo tiene un valor profundamente democratizador. Democratiza el acceso a datos, pero también democratiza el acceso a capacidad analítica. Y eso importa mucho, porque la desigualdad en las capacidades computacionales termina convirtiéndose muchas veces en desigualdad en la capacidad de formular preguntas, probar hipótesis y producir conocimiento competitivo. Una plataforma como Design Safe no elimina por sí sola todas esas asimetrías, pero sí las reduce de manera tangible. Abre la posibilidad de que grupos más pequeños, investigadores en jóvenes o equipos interdisciplinarios puedan trabajar con escalas de datos y simulación que antes estaban reservadas para unos cuantos. Los ejemplos que presenta la doctora Raggi son muy elocuentes y están bien elegidos. El caso del aprendizaje automático aplicado al desplazamiento lateral inducido por la ecuación muestra con claridad cómo la existencia de datos accesibles y de herramientas de análisis integradas puede traducirse en nuevo conocimiento. No se trata solo de estrenar modelos por novedad metodológica, se trata de aprovechar mejor información obtenida a partir de un evento real, en este caso el terremoto de Christchurch, para identificar patrones variables, influyentes y capacidades predictivas que luego pueden ser aprovechadas por otros investigadores. Es decir, Design Safe no aparece ahí como un depósito pasivo, sino como un entorno que convierte datos heredados en una plataforma para investigación nueva. El segundo ejemplo referido al desempeño sísmico de taludes es igualmente revelador. Aquí vemos que otra faceta de la contribución de la doctora Raggi, la articulación entre física, simulación numérica intensiva y modelos sustitutos, los surrogate models, más eficaces. El hecho es de que más de 50.000 análisis de elementos finitos pudieran ejecutarse y procesarse dentro del ecosistema del Design Safe, habla del papel decisivo que tiene la infraestructura en la ampliación del horizonte científico. Lo importante no es solo que se haya corrido un gran número de simulaciones, sino que ello permitió formular mejores modelos predictivos, identificar parámetros más eficientes y mostrar incluso las limitaciones de ciertos enfoques clásicos frente a modelos basados en inteligencia artificial. El mensaje de fondo es claro. Cuando los datos, el cómputo y la planificación están integrados, la frontera de lo investigable se desplaza. Hay otro aspecto del trabajo que merece reconocimiento. La doctora Raggi no presenta la apertura de datos como un fin en sí mismo, sino como una parte de una cultura de investigación reproducible y colaborativa. Por eso son relevantes los indicadores de eso que documenta: miles de usuarios, miles de conjuntos de datos publicados, millones de accesos, cientos de millones de horas núcleo y una intensa actividad en Jupyter Notebooks y espacios de interacción comunitaria. Más allá de la cifra puntual, lo que estos indicadores muestran es la consolidación de una comunidad de práctica. Y eso, en una plataforma científica, es quizá el indicador más importante de todos. Una infraestructura vale, en última instancia, por la comunidad que logra convocar, sostener y hacer crecer. Dicho esto, y justamente porque el trabajo es sólido, vale la pena ofrecer también algunas reflexiones críticas en clave constructiva. La primera tiene que ver con el hecho de que la democratización tecnológica no ocurre automáticamente por el simple hecho de que una plataforma exista. Requiere acompañamiento, formación, soporte y mediación humana. La propia autora lo reconoce cuando describe los apoyos a la curación de datos y los distintos niveles de acceso a las herramientas. Me parece que aquí hay una agenda futura muy importante. Seguir invirtiendo no solo en infraestructura computacional, sino en infraestructura pedagógica, porque una plataforma abierta puede seguir siendo en la práctica inaccesible para quien no domina ciertos lenguajes, estándares o culturas de trabajo digital. La segunda reflexión se refiere a la calidad y la interoperabilidad de los datos. Cuanto más crece una plataforma, más importante se vuelve asegurar consistencia en metadatos, trazabilidad de procesos y condiciones de utilización realmente efectivas. Publicar no siempre equivale a ser reutilizable, y quizás uno de los grandes desafíos para la siguiente etapa de Design Safe será profundizar aún más en esa dimensión. No solo alojar datos en gran escala, sino facilitar que esos datos dialoguen entre sí, entre disciplinas y entre comunidades nacionales e internacionales. La tercera reflexión apunta a una oportunidad estratégica que el propio trabajo ya insinúa: la convergencia entre ingeniería, ciencias de la tierra, ciencias sociales y estudios de resiliencia. Los peligros naturales no producen únicamente fallas estructurales, producen impactos territoriales, institucionales y humanos. En ese sentido, el futuro más prometedor de plataformas como Design Safe tal vez consista en integrar con mayor profundidad datos físicos y datos sociales, de modo que la ingeniería del riesgo dialogue todavía más con la comprensión integral del desastre. Pero esas observaciones no disminuyen el valor del trabajo, al contrario, lo engrandecen, porque muestran que estamos ante una contribución viva, fértil y abierta a evolución. Y eso me parece muy apropiado. En una ceremonia de ingreso a la academia no reconoce obras cerradas, reconoce trayectorias que abren camino, crean escuela y dejan capacidades instaladas para otros. Por todo ello, considero que el trabajo de la doctora Ellen Raggi es doblemente meritorio. Lo es por su aporte científico y técnico al campo de los peligros naturales y lo es también por su aporte institucional a la manera en que producimos, compartimos y preservamos conocimiento. Su texto nos invita a pensar en la ciberinfraestructura no como una cuestión secundaria de soporte, sino como una parte central de la responsabilidad académica contemporánea. En una época en que los riesgos son más complejos, los datos más voluminosos y las demandas de transparencia y colaboración más altas, esa visión resulta no solo pertinente, sino indispensable. Permíteme concluir con una reflexión final. El ingreso de la doctora Raggi a esta academia tiene un significado que rebasa el reconocimiento individual, aunque sin duda lo honra. Representa también el reconocimiento de una manera de hacer ingeniería que combina excelencia disciplinaria, apertura científica, visión institucional y compromiso con la utilidad social del conocimiento. En su trabajo encontramos rigor, memoria, innovación y sentido de comunidad. Y encontramos sobre todo una convicción que compartimos plenamente, que la ingeniería está llamada no solo a explicar y modelar los peligros naturales, sino a construir las capacidades colectivas para aprender de ellos y reducir sus impactos. Por ello, al dar la bienvenida a la doctora Ellen Raggi a esta academia, celebramos no solo a una investigadora distinguida, sino a una líder en que ha contribuido a transformar la ciberinfraestructura misma de la investigación en nuestro campo. Y al hacerlo, ha ampliado las posibilidades de la ciencia, de la ingeniería y, en última instancia, de la resiliencia de nuestras sociedades. Muchas gracias.
Muy bien, gracias, doctor Juan de Dios Alemán. Enseguida le doy la palabra al doctor Gustavo Ayala, académico titular de la Comisión de Ingeniería Civil ya comentado.
Muchas gracias. Con su anuencia, señor presidente. Nuevamente, buenas tardes, estimados colegas, señoras y señores. Antes de entrar en materia sobre el trabajo de ingreso de nuestra academia, que nos presenta la profesora Ellen Raggi, debo mencionar que ha sido un placer y un honor haber sido nombrado comentarista de trabajo de una profesional de ingeniería del calibre de esta candidata a miembro correspondiente. Extraño el no haber tenido la oportunidad de conocerla de los tiempos que coincidimos en Cornell. El documento ofrece una descripción competente y bien organizada del desarrollo de la ciberestructura. De la ciberestructura Design Safe para la ingeniería de riesgos naturales en Estados Unidos, enmarcada en una historia institucional de 25 años que abarca desde NESGRID, pasando por NESIT y NESHub, hasta la plataforma actual. La autora, quien ha liderado Design Safe desde su creación en 2015, escribe desde su experiencia operativa directa y el documento que nos presenta ofrece una visión clara de la arquitectura de la plataforma, su filosofía de gestión de datos y su trayectoria de uso. La inclusión de dos aplicaciones técnicas concretas de la ingeniería geotécnica sísmica, el aprendizaje automático para la expansión lateral inducida por la licuación y los modelos sustitutos para el desplazamiento sísmico de taludes, fundamenta el análisis de la infraestructura en problemas de investigación reconocibles. El documento también comienza con un gesto que este comentarista consideró verdaderamente significativo al citar el conjunto de datos del sismo de Michoacán de 1985, particularmente de la Ciudad de México, atendiendo a información contenida en documentos técnicos de diversos investigadores mexicanos como Roberto Meli, Emilio Rosenbluth, Eduardo Miranda, Luis Esteva, entre otros, como un conjunto de datos ejemplar cuyo valor podría simplificarse mediante una plataforma como Design Safe. Sin embargo, casi en su totalidad, este documento se centra en datos de Estados Unidos. Fundamentalmente, el documento presenta un problema estructural cuyo objetivo declarado es motivar a los investigadores a adoptar la ciberestructura, enfatizando los méritos sin presentar un análisis de las limitaciones de Design Safe, que este comentarista, al no detectarlas, considera que de existir son mínimas y de impacto reducido. En su texto, sería deseable una evaluación comparativa con equivalencias internacionales, entre los que se encuentra el Sistema Europeo de Observación de Placas, EPOS, la Fundación del Modelo Sísmico Global, OpenQuake, portales de datos mexicanos como los del Instituto de Ingeniería del Senapred, el consorcio Earthscope, entre otros. Los dos ejemplos técnicos contenidos en el documento provienen de contribuciones académicas del propio grupo de investigación de la autora. La descripción de estos ejemplos, al no contener con tratamientos técnicos rigurosos, particularmente en los temas de aprendizaje automático y simulación, es entendible por lectores no especialistas en estos temas. Es la opinión del comentarista que en versiones futuras y evoluciones de este documento, su objetivo debe incluir el examen crítico del desarrollo, la adopción y el impacto en la investigación de la ciberestructura. Durante su tiempo, ciberestructura, durante su primera década. Y a partir de estos derivar principios para el diseño de infraestructuras de investigación que sirvan a diversas comunidades internacionales de ingeniería en riesgos naturales. Un comentario que considero particularmente valioso es la posibilidad de involucrar a un grupo de investigadores mexicanos y por qué no, también de latinoamericanos, en trabajos que utilicen los datos del sismo de la Ciudad de México de 1985, citados en la introducción, o datos de reconocimientos posteriores al sismo de 2000, como los del sismo de 2017 o de otros sismos en la región, a los que accedan, en el caso de México, investigadores de la UNAM, la UAM, el Senapred y otras instituciones nacionales a través de Design Safe. De ser esto posible, esta sugerencia constituiría un gran logro en sintonía con los objetivos de nuestra academia y en beneficio de nuestras comunidades y países. Del análisis minucioso de este trabajo, el comentarista sugiere la pertinencia y relevancia de respuestas a las siguientes preguntas que formalmente solicita. ¿Es Design Safe accesible para las instituciones de investigación mexicanas en condiciones realistas de infraestructura de red? El almacenamiento de datos a escala de petatypes y el acceso a computación de alto rendimiento a través de una plataforma alojada en Estados Unidos plantean interrogantes importantes sobre el ancho de banda, la latencia y la soberanía de los datos, que son cualitativamente diferentes para los investigadores de la UNAM, el CIMBESTAB o el Senapred, y para aquellos en universidades de investigación estadounidenses con conexión directa a la red de la National Science Foundation. La segunda pregunta es: ¿cuál es el estado del conjunto de datos del sismo de la Ciudad de México en Design Safe? El trabajo sugiere en su introducción que los conjuntos de datos heredados de este tipo podrían y deberían ser gestionados y publicados formalmente en la plataforma. ¿Se ha hecho esto? De no ser así, ¿qué barreras institucionales o técnicas lo impiden? La respuesta es directamente relevante para las afirmaciones de la plataforma sobre la preservación de las inversiones de investigación y la facilitación de la reutilización. La tercera pregunta es cómo se compara Design Safe con la infraestructura de datos que mantiene el CENAPRED y los institutos de Ingeniería y Geofísica de la UNAM, entre otras instituciones, para el monitoreo sísmico de riesgos naturales en México o cómo interactúa con ella. Cualquier evaluación de una plataforma de ciberestructura para la ingeniería de riesgos naturales que ignore la infraestructura nacional de datos existentes en la Ciudad de México, una de las áreas urbanas más expuestas al riesgo sísmico en el mundo, resulta incompleta para este público. El sismo de Puebla, el punto 4, el sismo de Puebla de septiembre de 2017 constituye un ejemplo contemporáneo y de gran impacto del tipo de reconocimiento rápido e intercambio de datos que Design Safe, para los que Design Safe fue diseñado para respaldar. ¿Tuvo Design Safe algún papel en la documentación y el análisis de dicho evento? Esta pregunta es directamente relevante para las afirmaciones del trabajo sobre la gestión de datos de reconocimiento de campo y debe abordarse. En síntesis, considero, después de revisar en detalle y no poder emitir con el mismo nivel de detalle las limitaciones por falta de tiempo, el trabajo de ingreso como miembro correspondiente de nuestra academia que nos presenta la doctora JoAnn P. como un trabajo brillante y más que suficiente para ser considerada una digna miembro correspondiente de nuestra academia. Una referente más de las virtudes esperadas de nuestra comunidad. De igual manera, quizás la de mayor importancia es el impacto que su labor académico ha tenido, tiene y seguramente seguirá teniendo en beneficio de nuestras comunidades y países. Por esto, por la bondad que nos ha mostrado al compartir entre nosotros conocimientos, mismo que deseo continúe en el futuro, le expreso mi felicitación, dándole la más efusiva bienvenida como miembro correspondiente de nuestra academia. Por mi raza hablará el Espíritu.
Gracias. Muchas gracias, doctor Gustavo Ayala. Por último, tendremos la intervención del doctor Alberto Jaime Paredes en voz del doctor David de León, en virtud de que él envió un documento con sus comentarios. Adelante, doctor David de León.
Gracias, maestro Lepe. It is an honor and a pleasure, profesor Rache. Hablaré en nombre del doctor Alberto Jaime Paredes, que hizo estos comentarios. Él es académico titular de la Academia de Ingeniería. Estimados miembros del Presidium, colegas, profesores, estudiantes, amigos todos. Para mí es un privilegio ser comentarista del trabajo de ingreso a la Academia de Ingeniería como miembro correspondiente de la doctora JoAnn P. El excelente documento The Evolution of Natural Hazards Engineering Through the Design Safe Cyber Infrastructure, de su autoría, relata la evolución en los Estados Unidos en los últimos 25 años de la llamada ciberinfraestructura, con énfasis en la generación de bases de datos de campo y laboratorio, el estudio y la evaluación de riesgos provocados por eventos extremos naturales. Hace énfasis en el desarrollo, consolidación e impacto de la plataforma Design Safe. El objetivo central del texto es demostrar cómo la integración de datos, herramientas computacionales y recursos de alto desempeño facilita la investigación de los efectos de los eventos naturales extremos en la infraestructura física de los países, la cual puede extenderse también a las comunidades en sus aspectos sociales, económicos y políticos. Además, puntualiza y promueve la práctica de ciencia abierta. En este contexto, la doctora P. señala que los avances científicos dependen de la integración de 3 aspectos fundamentales: la investigación experimental en laboratorio, los estudios de campo y reconocimiento de efectos y daños después del impacto natural, la integración de datos curados y la modelación computacional. La experiencia indica que estos enfoques han generado grandes volúmenes de información. Sin embargo, gran parte de estos datos permanecieron inaccesibles, mal documentados o se perdieron, lo que es un desperdicio atroz. Como lo señala en su trabajo, la National Science Foundation desde el año 2000 ha patrocinado el desarrollo de una ciberinfraestructura para la comunidad de ingeniería sísmica. En 2015 se expandió el alcance a otros riesgos naturales, tales como huracanes, incendios, eventos geológicos y otros, bajo la iniciativa NERI, Natural Hazards Engineering Research Infrastructure. Y se creó Design Safe, una ciberinfraestructura desarrollada por la Universidad de Texas y el Texas Advanced Computing Center. El núcleo de Design Safe está compuesto de 2 grandes elementos: el Data Depot, que permite almacenar, organizar, publicar y reconocer el trabajo de los autores con identificadores digitales DOI, y un conjunto de herramientas y aplicaciones computacionales que brindan acceso a recursos de cómputo de alto desempeño. La plataforma no impone límites significativos al tamaño o número de archivos publicados. Además, ofrece apoyo directo a los investigadores para elaborar sus bases de datos mediante curadores de datos y sesiones de acompañamiento. Por curado de datos se entiende evaluar, clasificar y archivar datos con la finalidad de disponer de ellos para su uso actual y en el futuro. El documento presenta 2 ejemplos detallados del uso de Design Safe en ingeniería geotécnica sísmica. El primero aborda el uso de técnicas de aprendizaje automático para predecir el desplazamiento lateral inducido por licuación durante terremotos. El segundo ejemplo se centra en la evaluación del desempeño sísmico de taludes mediante modelos numéricos no lineales y el desarrollo de modelos sustitutos, incluyendo enfoques basados en redes neuronales artificiales. Design Safe no solo preserva el valor de los datos a largo plazo, sino que habilita nuevas oportunidades para el uso de técnicas avanzadas, como la inteligencia artificial, promoviendo además investigaciones más reproducibles, colaborativas y con mayor impacto social. Al leer el trabajo de la doctora Rafchi, recordé algunos de los grandes avances en las ingenierías sísmica y geotécnica, hechos por autores que han empleado tanto sus propios datos como los generados por otros. Por ejemplo, las funciones de atenuación de energía sísmica con la distancia desde el epicentro del sismo hasta el sitio de interés, Esteva, Newmark, SID y otros. El acelerograma del sismo del Centro California, en Estados Unidos, fue por mucho tiempo el más estudiado en ingeniería sísmica. La Carta de Plasticidad, parte esencial del Sistema Unificado de Clasificación de Suelos, la elaboró Casagrande, con base en sus propios datos y los que le facilitaron sus colegas, sobre arcillas y limos de diversas partes del mundo, incluyendo México. Las diferentes propuestas de Tomlinson, Basic, Peck, Kerisel y otros para calcular la capacidad de carga por fricción de pilotes de madera, concreto o acero en suelos cohesivos, en función de la resistencia no drenada del suelo afectada por un coeficiente alfa. Ellos utilizaron datos de pruebas de campo y de laboratorio de diversas fuentes. Lo mismo recordamos los diferentes mecanismos de falla basados en la teoría de plasticidad de Terzaghi, Meyerhoff, Basic y algunos más, que dan lugar a coeficientes de capacidad de carga, NC, NQ y N-gamma, de cimientos superficiales y profundos. Estos fueron atemperados por los resultados de ensayos de carga de zapatas, tanto en campo como en laboratorio, y de pilotes hechos por ellos y otros autores. Un ejemplo menos lejano es el trabajo de Sid e Idris para elaborar la gráfica para determinar si el suelo de un sitio es o no susceptible a licuación, en función de la aceleración del sismo de diseño y la resistencia a la penetración estándar normalizada del suelo en el sitio. Estos autores recabaron información de campo y de laboratorio de diversas partes del mundo para elaborar dicha figura. Invirtieron mucho tiempo en ello. Eran muchas las dificultades para tener acceso a datos de otros investigadores. Para ello, los congresos y simposios eran una oportunidad ideal para intercambiar datos e inquietudes técnicas. Y así también nacieron varios artículos para revistas especializadas. Las copias de los reportes y trabajos técnicos se hacían con papel carbón y figuras y tablas se reproducían con copias heliográficas. Podemos afirmar que compartir datos era un trabajo engorroso y que tomaba mucho tiempo. Muchos de los aportes a la ingeniería sísmica y geotécnica tomaron años para su conclusión e irónicamente se resumían en una tabla o una figura. Todo lo anterior permite contrastar y apreciar el gran avance que significa la plataforma DesignSafe, un repositorio de datos curados con libre acceso y en donde cada conjunto de datos tiene identificación digital DOI, que permite reconocer el trabajo de quien los elaboró, colectó o reunió. Herramientas de cómputo de fácil aplicación y acceso a supercómputo para el caso que lo requiera. Doctora Ellen Radfi, la felicito ampliamente por liderar la ciberinfraestructura DesignSafe y que el impulso que le da a la ciencia abierta a través de ella. Estoy convencido que su adhesión a la Academia de Ingeniería de México producirá resultados concretos para compartir datos y participar y colaborar en investigaciones conjuntas con investigadores y personas interesadas de Estados Unidos y México. Felicidades, doctora Rachi.
Bueno, por favor, denle las gracias a Alberto Jaime Paredes por su conducto. Bien, pues antes de entrar a nuestro último ingresante, vamos a hacer el cambio de esta mesa, de tomar una fotografía de recuerdo.
You said you were going to make it shorter, my introduction. It was too long. It was too long.
Congratulations.
Thank you.
Have a couple of comments. Just
Yeah.
using multi-hazard approach.
Oh, yeah, yeah.
The observation including rainstorm hazard.
Yeah.
Because here in Mexico, and I'm sure.
Oh, for landslides, you mean?
Yes.
For hill slopes, yes. Yeah. Oh, I think they want to take our picture first.
Yeah.
Thank you. Great, thank you. Thank you so much. Thank you.
Well deserved.
Oh, thank you. You had a lot of work today. You had to do two.
And many years.
Yeah, right. I'm sure.
A lot of work and
Okay,
many years.
keep in touch.
No, and no, I was just gonna say that, I agree. We're having the same thing in the US, right? Trying to figure out how to do the rainfall and do it as well.
Dice la señora Soledad que en qué orden va.
En el que intervinieron. Ahí está la lista.
It's my passion, yeah, for sure. Thank you so much.
Le confirmo, se les van a entregar en el orden en que se presentan. ¿Sí? Okay.
Sí, aquí está ahí. ¿No?
Sí,
claro.
Sí.
Órale. Otro resumen de notario.
Otro, sí, este está más fácil.
Bien, pues.
Ahí viene.
Ok. Welcome, doctor.
Welcome. Welcome to Mexico.
Yeah. Bien, pues a continuación tenemos la última participación como ingresante del doctor Taylor E. Como dice en la Biblia, los últimos serán los primeros. Y está la mesa pues realmente pesada, porque tenemos como comentaristas a 3 expresidentes de la academia. Primeramente le voy a pedir al doctor David de León Escobedo, que ya comentábamos, es nuestro protesorero y perteneciente a la Comisión de Ingeniería Civil, para que nos dé los datos del doctor Taylor E. Adelante, doctor.
Gracias, maestro Lepe. El doctor Taylor E. es el 6º presidente de la Universidad de Texas en San Antonio, UT San Antonio, y es el primer titular de la Cátedra Presidencial Distinguida Carlos Álvarez. Ahora es la 3ª universidad de investigación más grande de Texas. La institución es una universidad reconocida a nivel nacional como Carnegie Community Engaged y Carnegie Opportunity. UT San Antonio incluye ahora el Centro de Ciencias de la Salud de UT, el único centro académico de salud del sur de Texas y el principal productor de profesionales de la salud en la región, así como UT Health San Antonio, una amplia práctica clínica con más de 1,500 proveedores que atienden a pacientes en toda la región y que el año pasado atendió a más de 2.3 millones de pacientes junto con su socio University Health System. UT San Antonio es una institución ancla de San Antonio. Atiende a más de 43,000 estudiantes con 17,000 empleados, incluyendo a más de 4,000 profesores. Con 14 colegios y escuelas, la institución ofrece más de 350 títulos y certificados altamente competitivos y cuenta con aportes de apoyo a la investigación de más de $500 millones. Un presupuesto de $2,500 millones, una dotación de 1,300 millones y un impacto económico anual de $7,000 billones. Entre sus cargos recientes de liderazgo, el doctor E. cuenta con ser presidente de la Universidad de Texas en San Antonio desde 2017 al presente. Fue vicerrector de investigación y participación de la oficina de la Universidad de Tennessee en Knoxville de 2012 a 2017. Vicepresidente senior de la oficina del Research Texas Tech University en 2012. Vicepresidente de la oficina de investigación de la Universidad Tecnológica de Texas, Texas Tech, de 2009 a 2011. Vicepresidente interino de la Universidad de Investigación de New Hampshire en 2007 a 2009. vicepresidente adjunto de la misma oficina de investigación de 2006 a 2009, director de la Oficina de Iniciativas Estratégicas de la Oficina de la Vicepresidencia de Investigación de 2006 a 2009 en la Universidad de New Hampshire, miembro del profesorado de la Oficina del Vicepresidente de la Investigación, también en la misma universidad, de 2004 a 2006. Fundador y codirector interino del Centro de Investigación de Respuesta Costera de esta misma universidad en la alianza NOAA-UNH de 2003 a 2004. Director fundador del Centro de Recursos de Materiales Reciclados de la misma universidad, FHWA-UNH, del 98 a 2004. Cargos académicos actuales. Es profesor del Departamento de Ingeniería Civil y Medio Ambiente de 2017 al presente en la Universidad de Texas en San Diego. Tiene su doctorado en Ingeniería de Medio Ambiente en la Universidad de New Hampshire, su maestría en Ingeniería Civil en la misma universidad y su carrera de Biología en la Universidad de Tufts. Algunos premios y reconocimientos. Pertenece a la Sociedad Filosófica de Texas en 2026, Premio Otley en 2025, Premio Carlos Álvarez como presidente distinguido de 2025 a la fecha, miembro de la Asociación Americana para el Avance de la Ciencia de 2014 al presente, miembro de la Academia Nacional de Inventores de 2013 al presente, diplomado de la Academia Americana de Ingenieros y Científicos Ambientales de 2012 al presente. Nombramientos actuales en la Junta Directiva y de Consejo. Consejo de Presidentes y Cancilleres de Investigación de Impacto Público de Pew Charitable Trusts de 2024 al presente. Del Consejo de Competitividad de los Estados Unidos. Y es miembro del Consejo de Investigación del Gobierno, Universidad, Industria de las Academias Nacionales de 2017 al presente. Miembro desde 2018 al presente del Subcomité GIR OSTP sobre el futuro de la ciencia de 2023 al presente. De la Asociación de Universidades Públicas y Concesión de Tierras y es de la Junta Directiva, miembro de la Junta Directiva de 2020 al presente. Del Consejo de Presidentes de 2017 al presente. Presidente de la Comisión de Iniciativas Internacionales de 2020 al presente. De la Coalición de Universidades Urbanas, CUSU, de la Junta Directiva de 2017 al presente. De Excelencia en Educación, presidente por el Éxito Estudiantil Latino de 2020 al presente. Alianza de Universidades de Investigación que sirven a hispanos. Es de la Junta Directiva de 2022 al presente, del Comité Ejecutivo 2022 al presente, Fideicomiso Especial de 2018 al presente, del Instituto de Investigación del Suroeste, el Southwest Research Institute, del Fideicomiso Asesor de 2018 al presente. En investigación académica, el doctor Eichmann ha publicado 60 artículos indizados, 3 libros, 4 capítulos de libros y 65 artículos en actas de congresos revisados por pares y posee una patente. Sus áreas de investigación incluyen la especialización elemental, la química ambiental del comportamiento de lexiviados, el análisis electroscópico de superficies, la geoquímica aplicada, barreras reactivas, modelo de transporte reactivo, microbiología ambiental, bioincrustación, biofilmes, la sostenibilidad, la captura de carbono, la sostenibilidad y la caracterización y uso benéfico de materiales reciclados. En las consultas con Google Scholar Citations, su índice H de 32, con más de 5,200 citas. Como profesor, el doctor Eichmann contó con 41 proyectos y contratos de investigación para un total de más de $15 millones de financiamiento. para agencias como la FHWA, la NOAA, NSF, National Science Foundations, DoD, la DOE, y como administrador ha liderado esfuerzos que han resultado en premios competitivos de $420 millones en instituciones de los Estados Unidos, National Science Foundation, la NOAA, USGS, NIH, el Estado de Texas y el sector productivo. Y ha asesorado a más de 35 estudiantes de grado de maestro, doctorado y postdoctorado como director principal, y ha estado en más de 40 comités de tesis de máster y 20 tesis de doctorado. Bienvenido, doctor Aikmi. Eso es cuanto, señor presidente.
Muchas gracias, doctor David de León Escobar. Pues escucharemos ahora el trabajo del doctor Taylor Aikmi, que se denomina Ecosistemas regionales de innovación que impulsan el descubrimiento en la ingeniería, la I+D, la educación y el desarrollo de la fuerza laboral y económica. Las universidades de investigación como instituciones ancla del ecosistema.
It is a delight and pleasure and honor to be here. This is a very special moment, and I feel very lucky to be able to have this conversation with you, so gracias. I have to admit, if you were to look at my scholarship in my life, my thing that I spent my most time on as a faculty member and researcher was really applied geochemistry. But and my home department would always have been a civil and environmental engineering department. And the last time I actually went to a faculty meeting was probably 20 years ago. But I have to admit, being here today and yesterday with all of my colleagues from Texas, who are all civil engineers, it has felt very comfortable because it reminds me of my time in my department as a civil engineer. And I did have a period in my life where I worked on the beneficial reuse of waste materials in transportation and infrastructure construction, mostly highway construction. So I worked on concrete, I worked on asphalt, I worked on embankments, I worked on the impacts of recycled materials in these applications, including the engineering principles of these manufactured materials and how they were used, and how design considerations had to be changed and adopted by our certification agencies about use of these materials. So a lot of what I heard about today was very comforting and reminded me of my time then doing that. But what I'm going to talk about today is completely different than anything that's been discussed. And if I had to pick something that I have become very passionate about over my life as an administrator, is this notion of building innovation ecosystems. And this is so different that I hope that you'll walk away with this notion that these kinds of ecosystems are still essential, that there are ingredients that are important to make them work, that universities are foundational to these ecosystems, and that if done well, they have an immediate positive impact on advancing engineering education, advancing workforce development, and advancing economic development. So let me dive into this. And I also would like to say thank you from my heart to the three commentators, because they provided very important input to my earlier version of my manuscript. And I actually have changed it a little bit to be adaptive of the ideas that were shared by my colleagues, because I wanted today's conversation to be as helpful as possible. So even the title of my talk has changed, and some of the focus of my manuscript has changed to be reflective of things that are important that the commentators brought forward. So thank you, commentators. So I'm really here today to talk about innovation ecosystems, so let's dive in. I would like to talk a little bit about innovation. I'd like to talk about the triple helix model. I want to have you understand that innovation ecosystems can be scaled. They can be rather small in nature, facilitated by a single university and partners, or they can be regional in nature. They can be bilateral, binational in nature. They can involve many countries, and the level of investment is really the thing that drives the scale and magnitude of an innovation ecosystem. I really would like to spend a moment talking about some of the innovation ecosystems in the United States. I'll also talk about this concept of anchor institutions for innovation ecosystems. And again, universities are foundational to these ecosystems. And then I'm going to present only 2 case studies. In my original manuscript, I had 3. I decided to pare it back and talk about them a little bit more instead of doing all 3. So I'm going to talk about one that involves wind energy technology development in the West Texas region of the great state of Texas and the innovation ecosystem associated with that. And then I'm going to talk about one that's rather national in scope about advanced manufacturing. And in the course of my career as a senior administrator, I've had a chance to work on 6 or 7 innovation ecosystems, but these are 2 of my favorite. One, because they've been around long enough and have continued, that there are some tangible outcomes that have come from them that are worth sharing. And they also relate to elements that are very integral to the things that we care about, not only in the United States and in Texas, but here in Mexico. So alternative energy or advanced manufacturing for aircraft or automobile production are all very important things that are important to the economies of our 2 countries. So I've pared it back, and I'm going to use those 2 as examples. Then I'll spend a moment looking ahead at some ideas, and then we'll conclude. And I know it's the end of the day, so I will go forth and do this promptly. So let's start with this notion about what is innovation. And I'm going to turn to something that's always been on my shelf as a faculty member and as a researcher, and it's the book by John Gertner about the Bell Labs and this concept of the Bell Labs being an idea factory. And this whole notion of an idea factory is really around this concept of lots of interesting problems that have to be solved, transdisciplinary approaches to problem solving, making problem solving and ideation a continuous cultural piece of the institution, and making it part and parcel of a process that happens all the time. And that for every time that you've innovated something that worked out, failure to innovate and try something that just didn't work is also as important as trying something that ends up working. And this whole notion about innovation is it requires invention, and it requires a market to take the invention to, and it requires manufacturing to make this entity, to drive the market that drives the economy. And if you have an innovation ecosystem that's thriving, it's going to need a workforce that's trained up and aware of the technology that's involved and the impact to market. And if you're preparing young people coming out of engineering programs that are adapted to that innovation, to that invention, that market, that manufacturing process, you're doing a good thing. And if you're supplying a workforce for this innovation economy, you're advancing workforce development, which is essential for economic growth. The North American economy, just for referencing, is a 34 trillion GDP economy. It's the first or second largest global component to the global economy of about 30 or 35%. So We ought to be paying attention to this notion of innovation all the time to remain relevant at a global level, in spite of all the complexities that we've been dealing with of late. So what is really foundational to innovation ecosystems? It's the concept of this triple helix model advanced by Henry Etzkowitz. The triple helix involves universities driving basic research and knowledge generation. It involves industry producing commercial goods and services. It involves government at various levels, serving as the major public venture capitalist for that innovation ecosystem. You need all three of these components. Now, in both of our worlds, in the United States and Mexico, we also benefit from having national labs that are supported by our governments. In the case of the United States, we have many fine labs supported especially by the Department of Energy, and I'm going to be talking about them a lot, but here in Mexico you have an equivalent. Those are just as important components to generating research and knowledge as universities. So the original model for Triple Helix was really focused on universities, industry, and government, but you should throw your national assets, your national treasures, like TAC at the University of Texas at Austin, the Texas Advanced Computing Center. That's a national treasure, even though it's not a national laboratory. So there are things that we can put on the table that drive this concept of the integration of the three components of the triple helix model, all working together to drive innovation. There are plenty of interesting examples of innovation ecosystems around the globe. I could have shared hundreds of them with you, and they range in scale and scope to things that are new, things that have been around for 20 plus years, things that have involved billions and billions and billions of dollars of investment by federal governments, to things that are just starting because the innovation ecosystems are so new and the components are so new in that location. So we range from something giant and very impactful, the Horizons program out of the EU, that has followed the 6 or 7 framework programs before it, and it's a very elaborate triple helix model that has had great impact on the GDP of the EU. And we range to something very small about a program in Africa that's just starting up, creating the components of an innovation ecosystem. So some have been around for quite a while, some are brand new, some are small, some are big, some are involved in one part of one country, some involve 30 countries. It just depends on what you're trying to do and what your ecosystem is about. Okay. I will throw in there one brand new one that's coming out of the current administration in the United States, and that is the Genesis mission. I'll mention it again in a few slides, but it's out of the Department of Energy, and it's really focusing an initial $320 million investment. It will grow dramatically over time, and it involves all 17 of our Department of Energy national labs, universities, and industry, so it's a clear triple helix model, and it's focusing on AI and high-performance computing like TAC, and very specialized facilities for breakthrough in energy production, material science, fusion, quantum computing, and other advanced technologies. And that's just an example of the way our environment in the United States is going to be shifting around federal investment in innovation ecosystems, and this is going to be a large national one. And I don't know if it'll end up getting as big as the Horizons program in Europe, but it'll get close. But there are other things that are here that are reflective of good efforts over time, producing outcomes that drive economic development and workforce development and positive impact to society. Okay. I want to stop for a second and give a shout out to something here in Mexico. CICITI, which has evolved since 2025, coming out of CONACYT, is obviously a very important now ministry of the Mexican government, focusing on science and technology and on innovation. And it has a sub-ministry. One of the sub-ministries is for technology and innovation. And obviously, this is a new construct as a new ministry, and morphing what was CONACYT into CCT has been a big deal. And the fact that the secretary now is at the cabinet level with the president is an important thing for your country. And it has all of the components that you would want to be able to affect positive impacts to economic growth through workforce development, advancing education, R&D, innovation, the triple helix application. It has all the components that you would want to have to be able to have innovation ecosystems flourish here in Mexico. So it has some interesting components to it. It has an entrepreneurship and a startup component. It has a clear focus on workforce skills and talent pipeline growth. It is actually investing in labs, test beds, and shared facilities, which are these national treasures you need to help drive innovation ecosystems. It has an international cooperation component, which is important, given the fact that Mexico is a global economy. And it actually has a regional focus within Mexico, within certain states in Mexico, to drive technology clusters supporting localized innovation ecosystems. So this is a very good thing that's just started just a year ago, more or less. I've had a chance to visit the minister, and I'll explain in a second why we have connectivity to CCT, but I just want to make sure you understand that you have something good here. Okay, a little sidebar. In 2016, the University of Texas system comprised of 14 institutions established with CONACYT here in Mexico, the Context program. And the Context program was put together to drive access and opportunity, economic impact, and collaboration between our two countries. It had strategic themes, and they've evolved over time, and the current themes that are in place are very aligned with CCT's current focus around AI, water security, forest ecosystems, climate, food, energy, pharmaceuticals. It has a significant budget annually funded by both the University of Texas system and CCT as a federal agency. It has partners in that all 14 UT system institutions are partnering with over 70 public and private Mexican universities, including UNAM. It has been funding doctoral scholarships through fellowships and producing a lot of outcomes in terms of scholarship. There are postdoctoral fellows that are supported. There are binational collaborative R&D projects that are supported. And we've just launched this brand new public health fellowship pilot program where students who are here in Mexico getting their MDs can go and study for a year at one of the component medical schools, actually schools of public health in the University of Texas system, and get a master's in public health, but also spend a year at that institution in Texas. And my good colleague, Lupita Carmona, Dr. Lupita Carmona is here. She is the director of Context, and I just want to make sure you know how important this is and how connected it is to higher education here in Mexico. And it does have elements that feed into healthy innovation ecosystems. So this is something that we need to nurture as we go forward. Okay. This concept of innovation ecosystems has been around for a while in the United States. The Brookings Institute has been talking about it for 20-something years. The Council on Competitiveness has been advancing this notion for the same time frame. And the national academies in the United States and one of its component institutions, the Government University Industry Philanthropy Research Roundtable, also has been a driver for scaled innovation ecosystems. And I am very fortunate. I have been working closely with Brookings over my career. I am on the board of the U.S. Council on Competitiveness, and I'm on the board of GWIPR as part of the national academies. And there are other organizations in the United States that have been advancing this notion of scaled innovation, and it also includes some of our larger philanthropic organizations that fund specifically science and engineering. So it's a rich environment for us, and the momentum around scaled innovation ecosystems in the United States is a healthy thing. The triple helix model has now evolved in the United States to include philanthropic organizations. Some of this was a logical progression given the impact, especially that the Kavli Foundation has had on science in the United States. But it's also been driven by the fact that some of the recent reductions in funding of R&D at our 17 federal science agencies in the United States has caused the innovation ecosystem and enterprise of the United States to say we have to think about funding basic and applied research in a different way now in the United States as we evolve. So that's work in progress. But the fact that philanthropy is now at the table helping to shape the innovation ecosystem of the United States is an important thing. There have been a number of initiatives over the last 10 to 15 years that have driven innovation ecosystem development in the United States. The National Science Foundation has had regional innovation engines programs. They've had the I-Corps program. They've had NSF EPSCoR programs for certain states that do this. They've also, especially in 2022, during the Biden administration, we're very much into the CHIPS and Science Act because Congress had passed that and put a huge amount of investment into that for the U.S. innovation enterprise. The Department of Energy, with its user facilities at the national labs, its energy innovation hubs, its energy frontier research centers, was driving all of this innovation ecosystem as well. But more recently, under the Trump administration, we have the CHIPS to Accelerate Act, which is really kind of the evolution of the CHIPS and Science Act into the current administration. We continued this Manufacturing USA program that I'm going to talk about in a second. And the Genesis mission is actually being driven out of the Department of Energy. But in the Department of Commerce, we've had tech hubs, we've had the manufacturing extension partnerships, which has really benefited community colleges. And they are part now of this triple helix model. If you were to really be really smart about it, you would say that universities, national labs, and community colleges are really one of the triads of the triple helix or the quadruple helix model. So we have programs that are happening, still underway in the Department of Commerce, and in the Department of Defense, we still are, I don't know what we're going to call that now, but we still have this Manufacturing USA focus. This is a very special initiative, federal initiative. It started in the Obama administration. It went into the first Trump administration. It then went into the Biden administration. And it continues now into the second Trump administration. There are 17 manufacturing innovation institutes across the United States. And the total amount of investment over the last 10 years has been almost $3 billion in this program. I was very fortunate, and one of the examples I'm going to talk about is IACME, the Institute for Advanced Composites Manufacturing. That's one of the two examples I'll share. But we also have one of these institutes at the University of Texas at San Antonio, the Cyber Secure Manufacturing Innovation Institute. And because of my prior work, I was involved in helping to set up 4 other institutes. So I've had a lot of opportunity to work in this space, and this is probably the best example that I can share of a federal, national, large-scale effort to drive an innovation ecosystem around manufacturing, which is so important to our country. So this is a wonderful success story to talk about, and you'll hear more about it in a second. Okay. I want to talk a little bit about anchor institutions, and I'm going to use this as just one example. On the left-hand side are all of the 17 Department of Energy national labs, and I've had the pleasure to work very closely with 6 of them. And they're distributed around the country. And I am also very involved with the Alliance of Hispanic Serving Research Universities. We're 26 institutions ranging from California to New York. And across our ecosystem of how we do business with our work that's funded by the Department of Energy in particular, our 26 universities and the 17 national labs have active research agreements with many of these programs I was just talking about. And there are about 147 active collaborations between our 26 institutions and the 17 national labs. And that just tells you how integral and interchangeable a national lab model and a university model can be in terms of being one of the component triads or anchors of a triple helix or quadruple helix model. And so this is indicative of the nature of the relationship you need to have a very robust innovation economy. So, 2 case studies. Let's start with the first one. Wind in Texas is abundant. There's a map on the left that looks at average wind speed, and most of the wind farms that you see now in West Texas are where all the green color are located on the map. Today, there are about 20,000 wind turbines in Texas, producing 42 gigawatts, and 30% of the energy production that goes into the electric grid in Texas comes from wind when all of the wind turbines are working. So it was a big deal, and it's been part of the Texas economy for 20 to 30 years now, and it's, you know, Texas believes it's an energy state, and wind is still a component in spite of all the oil and gas that we have. So it's still an integral component. And back in the day, there was a lot of interest about helping Texas grow the number of wind farms that we have and the number of turbines we're putting up and the amount of energy we're producing in that state. And one of the things that you can do is you can optimize a wind turbine, but you cannot easily optimize an array of turbines. And that's because of the issues associated with turbulence from the leading turbines in the array. And here's an example of a turbine array out in the North Sea. And you can see the turbulent wakes coming off of the turbines in the lead part of the array, impacting the wind flow and the complexities of wind flow in the turbines that are downstream from the lead turbines. And the issue here is that the array optimization is so suboptimal that it's losing the opportunity to produce 10 or 15% of the energy it could produce if it wasn't dealing with these complex turbulent flows going through the array. So there was a keen interest 15 years ago to figure out array design and to try and control turbine placement in the array, but also to try and mitigate the effects of turbulence in the array so you could fine-tune the array to optimize its energy production. And this was a project that started actually back in 2012. It was funded by the Department of Energy with components from the private sector and from state funding. And what was interesting about it is we had partnerships with, at the time I was the vice president for research at Texas Tech, we were partnering with Sandia National Labs, the National Renewable Energy, now the National Laboratory of the Rocky Mountains, and with Vestas Wind Energy, but also with Alstom, Wind Flow, and General Dynamics. And these are all components that brought resources and talent, shared services to the project. And we located a scaled wind farm at a closed Air Force base west of Lubbock, Texas, where Texas Tech is. We ended up putting in turbines that we tested. We ended up putting in the turbines that were used for looking at array optimization. We ended up putting in a microgrid system there. We ended up putting in meteorological towers so we could understand the wind flow patterns coming through. We had all sorts of devices at elevation around the periphery of the property and on the property to really completely understand wind flow, laminar wind flow, turbulent wind flow during the very windy times that we were testing and understanding array performance. So this is an example of the 3 turbines that were put in place and the Met towers that were located and the control array building that allowed us to dial in how we were operating the turbines. And we ended up putting a sonar system in. We had mesonets around and upstream, typically from where the winds were coming from. We ended up doing a lot of work around modification of the turbines to do turbine wake steering to try and mitigate the impacts of downstream wakes on turbines that are downstream. We had Met towers with instrumentation with LiDAR. We used dual Ka band radars to image the turbulent wakes in the arrays. So we were able to get visual patterns similar to the ones that are shown there. We also developed blade instrumentation to understand pressure drops over the blade, vibrations in the blade. We put nasal optical sensors on the nasals so that we could understand the turbulent wakes downstream of the turbine itself. We ended up putting additional blade instrumentation in place that would allow us to look at fatigue and look at stress in the blades. We tried new kinds of blades. We did all sorts of things, and we actually connected the array when we were generating energy to operate a microgrid to manage energy production, storage, and different types of batteries and whatnot, so that we could actually help wind energy drive microgrid performance and optimization. So during the course of this, we created brand new graduate programs in wind science and engineering. We ended up creating a technical training program with the local community college. We ended up forming a brand new company to look at wind energy optimization and performance of arrays. We ended up being part of a very large DOE experiment to optimize arrays across 250 different turbine fields, turbine arrays in 7 different western states over a 2-year period to take what we had learned in Lubbock and optimize arrays in other parts of Texas and outside of Texas as a way to advance wind energy. And we were very happy to hear that Vestas and Alstom, who had partnered with us, were delighted with all of the outcomes that came from this work. And we ended up advancing in a good way this connection between wind and microgrids. So a good example of a pretty small innovation ecosystem that produced an impact around education, workforce development, benefit to the companies, benefit to energy production. A finite period, it's still actually going. They're still doing wonderful research there, and that's satisfying considering I worked on it 10 years ago, and I only had the pride of authorship of helping it get up and running. And I know nothing about wind energy, so it was good. The second one is the one that I spent almost 5 years of my life working on as the Vice Chancellor for Research at the University of Tennessee, Knoxville, and it had to do with the government's interest in bringing manufacturing back to the United States. And the one area that I really dove in on was this one related to advanced manufacturing and production of composites for use in automotive and aerospace. And where we were situated in eastern Tennessee, we were kind of at the epicenter of a whole bunch of focus on automotive manufacturing in the Southeast and also on aerospace manufacturing in the Southeast. So it ended up, our effort was national in nature, but we had so much focus on automotive and aerospace at Tennessee that this was a logical precursor to our momentum of bringing this initiative together. And the engineering innovation challenge here was the adoption of carbon fiber into polymer composites for manufacturing in automotive and aerospace principally, but we ended up morphing it a little bit into wind energy and compressed gas storage, and it's evolved over time. It's still running. But back in the day when we put our big proposal together to do this, we needed to focus really on automotive and aerospace. And so it had a very large component around material science, production methodologies, materials characterization, prototyping, scalability to full-scale production. And we were looking at working with Boeing on creating a prepreg resins that were embedded into carbon fibers that we were developing that were used for high temperature compression forming of thermoplastics to make components for aircraft, and we were doing the same for automotive components with VW. So some of these things were actually being put into use as prototypes back in the day, coming from the research from this effort. So what was special about it was that the original award, which was made in 2015, was $70 million from the Department of Energy, $60 million from these state economic development agencies, 6 states, and $130 million from all of our corporate partners that we brought on board. So we ended up having 122 federal, state, university, and private sector partners initially. It's actually grown now. And I was the lucky guy that got to be the principal investigator submitting this $250 million award to the Department of Energy back then. And like I said, I'm an applied geochemist. I know nothing about composites, but I was the lucky guy that got to do this. And we had a lot of focus from Purdue, from Colorado, the University of Colorado, and Colorado School of Mines. We had the University of Kentucky involved. We had Dayton, University of Dayton involved. We had Michigan State University involved. And these were the original components, along with Tennessee and Oak Ridge National Lab, working on this. We also had the National Renewable Energy Lab as a partner. And where we ended up really excelling was bringing the corporate world in as partners to invest and co-collaborate with us on our research. So we had all of the major players in automotive, all of the major players in aerospace, all of the major players in polymers and fibers. And we started to innovate very rapidly, and we had scopes of works that we had to adhere to. But one of the things we specialized in was building with Cincinnati Corp a big area additive manufacturing machine that would use ABS plastics with carbon fiber that we were making to thermally extrude and 3D print things. And we ended up using this 3D printer to make molds for pre-preg high temperature compression forming of thermoplastics with carbon fiber in them. So it was very special. And I have a little sidebar I have to share with you. So we used that big area additive manufacturing to make components to assemble a Shelby Cobra that was 3D printed, not the electric motor, not the metal chassis, not the steering wheel, but all of the structural components other than what the electric motor was were 3D printed and prepared using big area additive manufacturing. And we ended up, the day that the White House showed up to formally announce this award, we had President Obama with us, we had Vice President Biden with us. This car could go from 0 to 60, because it was a direct drive, electric motor driven car, could go from 0 to 60 in 3 seconds. And we had to hide the keys from the Vice President because the Secret Service was worried that the Vice President, Joe Biden, would want to drive this car outside the factory in Tennessee where we did this announcement. So these were the kinds of things that we did that were exciting and innovative. The one that was probably most interesting and complex was developing solution spinning to make carbon fiber and then building it at scale to produce the requisite tons per hour of carbon fiber that you would need to operate to make these composites, and then being able to impregnate them and to scale for compression molding of these thermoplastics with carbon fiber associated with them. And so part of our progress was to use our component institutions and the facilities that they had to demonstrate scaling of carbon fiber production, as well as actual forming of composite components that would be ready to go for automotive or aerospace. So all of this was advances in technologies that no one knew how to do at the time. And what we started with were money from the feds, money from others, a member consortium, core partners, leadership, a focus area, and we had to produce reductions in carbon fiber composites costs, embodied energy savings, avoiding greenhouse gases, the ability to recycle these materials if necessary, and producing jobs and production capacity. And we were able to drive all this. It was so successful that this Institute has been renewed by the Department of Energy, and it's well on its way to getting renewed again for another 5-year period. But since its inception 10 years ago, hundreds of paid internships have happened with industry, 1,800 STEM engagements between students and industry, 15,000 online and 5,000 in-person technical training events done with manufacturing extension partnership institutions, principally community colleges. Curricula provided to over 40 training centers nationally about composites production, 60 industry-led innovation projects that have resulted in technological advancements, new technologies, and new investments since its inception. So that has been something that is very gratifying, and the fact that this program has gone through 4 administrations now says something about the value that it provides. And what I want to end with now is something a little bit different, and it is reflective in some of the comments I got from my commentators. Separately, I'm very fortunate to work with my principal association for higher education in the United States, the Association of Public and Land-Grant Universities. I chair the Commission on International Initiatives, and I've been working with my colleagues on that commission and with colleagues at ENWIS here in Mexico and with Universities Canada, along with the business equivalents in our 3 countries, so the Council on Competitiveness, United States-Mexico Chamber of Commerce, and the Business Council of Canada, to bring forward a position paper about this concept of a North American zone of knowledge. And what we're advocating for in this is focused workforce development between our 3 countries, focused economic development between our 3 countries, focused innovation ecosystems between our 3 countries, and using all of this and our collaborations to inform USMCA 2.0. So we'll see how that goes. It's work in progress, but this too is ancillary to this concept of innovation ecosystems. But if we can advance this at this very hemispherical level, it's going to do a good thing. So with that, I would like to say I have many colleagues who have helped me with this, and I'm very fortunate to have them as dear friends and colleagues. They've contributed mightily to this. I just got in the way. The triple helix, or even the quadruple helix, is alive and well. Scaled innovation ecosystems remains vital for workforce and economic development, and it should be important for both countries. Universities and labs are essential anchors. Federal and state investments still must be the principal driver for venture capital investment in these innovation ecosystems. And this concept of innovation ecosystem is still broadly applicable globally. They're everywhere, but they're also relevant right here in North America. So what do we do with them? That's the question of the day. And with that, I would say thank you to the commentators for your earlier comments. I look forward to hearing your comments now, and I'm very fortunate and lucky to be here today, so gracias. And I end with this. Thank you.
Muy bien, después de esta interesante exposición, los comentarios a este trabajo corresponden a 3 de nuestros expresidentes en la academia. El primero de ellos, Sergio Alcocer Martínez de Castro, y que además pertenece como miembro titular a la Comisión de Especialidad de Ingeniería Civil. Suena obvio.
Sí, señor.
Adelante.
Gracias. Con su permiso, señor presidente, doctor Taylor Egme, académico correspondiente, señores comentaristas, señoras y señores, es para mí muy honroso y satisfactorio poder comentar el trabajo de un líder universitario cuya trayectoria ha tenido un impacto profundo en la educación superior, en la investigación aplicada y de manera muy destacada en la articulación entre universidad, industria y sociedad. Además, mi participación me es especialmente grata debido al respeto profesional que guardo por el doctor Egme, así como por la relevancia y oportunidad del tema que aborda en su trabajo de ingreso. Doctor Egmi, recibe usted una muy cordial felicitación por su ingreso como académico correspondiente de la Academia de Ingeniería de México. Su designación es reflejo de una trayectoria distinguida, caracterizada por el liderazgo institucional, la visión estratégica y un compromiso firme con el desarrollo del talento, la innovación y el crecimiento económico regional. Su incorporación honra a esta academia y fortalece los vínculos entre las comunidades académicas de México y de los Estados Unidos. Enhorabuena. El trabajo de ingreso que nos presenta el doctor Egmi aborda un tema de enorme relevancia para nuestros países: el desarrollo de ecosistemas regionales de innovación sustentados en la interacción entre universidades, industria y gobierno, y de manera creciente, como él mismo lo señala, con la filantropía. Si bien México tiene experiencia en la articulación de esfuerzos entre universidades, industria y gobierno, si bien no a la escala que nos presentó usted, no tenemos experiencia en la incorporación de filantropía, y me parece que ese será un reto importante. En nuestro país tenemos una excesiva visión centralizada, me parece, en los apoyos que pueda proveer el gobierno más allá de los que la filantropía pueda contribuir. En muchos casos la filantropía mexicana se concentra en la solución de problemas mucho más básicos de atención a la educación, a la salud, que no son cubiertos por el gobierno, cosa que es distinta de lo que pasa en los Estados Unidos. Pero partiendo del modelo de la llamada triple hélice y su evolución a la cuádruple hélice, el doctor Egmi nos ofrece una visión estructurada sobre cómo se construyen sistemas regionales capaces de generar innovación, formar talento y detonar crecimiento económico sostenible. En un contexto global caracterizado por la regionalización de las cadenas productivas, la competencia por talento especializado y la aceleración tecnológica, esta visión resulta no solo pertinente, sino estratégica. Uno de los méritos centrales del trabajo es que trasciende el plano conceptual y se sustenta en ejemplos concretos de implantación donde universidades, laboratorios nacionales, empresas y agencias gubernamentales colaboran de manera efectiva y eficiente para generar impacto tangible medido en generación y transferencia de conocimientos y de diversos productos protegidos intelectualmente, desarrollo de una fuerza laboral mejor preparada y pertinente, generación de empleos más atractivos y enriquecedores, así como creación de riqueza, entre otros impactos. En este sentido, el trabajo pone de relieve el papel de las universidades como instituciones ancla dentro de los ecosistemas de innovación. Las universidades no solo generan conocimiento mediante la investigación, sino que forman capital humano altamente especializado, deben promover el emprendimiento, así como actuar como nodos de conexión entre distintos actores. Quisiera destacar en particular la importancia que el doctor Egmi otorga al desarrollo de talento. La formación de capital humano debe incluir esquemas más amplios y flexibles de capacitación, actualización y reconversión laboral. Un ejemplo notable son los logros que en este y otros temas se han alcanzado en la Universidad de Texas en San Antonio, que él mismo preside. Asimismo, el trabajo abre la puerta a una discusión sobre la transformación de la educación en el contexto de nuevas tecnologías como la inteligencia artificial. Más allá de ser una amenaza para ciertos empleos, y para ello les invito a revisar el estudio de Brookings Institution, que fue referido en el Washington Post apenas hace una semana y media, la inteligencia artificial es una herramienta para aprender más y mejor. Se requiere, eso sí, ganas y tiempo para lograrlo. Por cierto, en dicho estudio, a los ingenieros civiles nos ubican como una profesión de vulnerabilidad baja, con importantes capacidades de adaptación a la inteligencia artificial en nuestro quehacer. Otro aspecto relevante es la gobernanza de los ecosistemas de innovación, donde la coordinación entre actores y la continuidad de políticas públicas resultan fundamentales. Un ejemplo por destacar es lo que ha logrado Indonesia, un país con una economía algo más pequeña que la mexicana, que ha avanzado a un ritmo mayor gracias, en parte, a políticas públicas sostenidas en materia de ciencia, tecnología, innovación, emprendimiento y educación superior. Quisiera resaltar el concepto de las 3 C que están incluidos en su artículo, se refieren a 3 palabras en inglés, que se refieren a convene, connect y catalyze, que el doctor Egmi nos presenta como una síntesis del papel de las instituciones líderes en estos ecosistemas. En efecto, las universidades son instituciones reconocidas, apreciadas y aceptadas por nuestras sociedades, tal que les permite convocar, y es la primera de las Cs, a los distintos sectores, expertos y personas con experiencia en un tema. De modo que mediante las conexiones, que sería la segunda C, que logren establecer, puedan de manera colaborativa resolver un problema o atender una situación que aqueja al entorno desde un ámbito social, económico, ambiental, comercial o de cualquier otro tipo. Es decir, son instituciones catalizadoras, donde viene la tercera de las Cs. Permita hacer una reflexión breve sobre el significado de este ingreso, como lo hice con el caso de la doctora Browning. El ingreso como académico correspondiente implica no solamente un reconocimiento, sino un compromiso con el avance de la ingeniería, así como en este caso la búsqueda de soluciones a los grandes retos de nuestras sociedades. Doctor Amy, más allá de sus contribuciones institucionales y académicas, quienes hemos tenido la oportunidad de interactuar con usted, reconocemos su visión integradora, su capacidad de construir puentes y su genuino compromiso con la formación de nuevas generaciones. Su liderazgo ha fortalecido a la Universidad de Texas en San Antonio como un actor clave en innovación y desarrollo regional con un impacto más allá del propio estado de Texas. Pero sobre todo quisiera destacar algo que en lo personal valoro mucho, su disposición para acercar a nuestras instituciones, para atender puentes reales entre universidades de Estados Unidos y México y para construir espacios de colaboración que trascienden lo formal. Y quisiera presentar dar dos, tres ejemplos de ello. El caso de Context que usted refería, tuvimos la oportunidad, un grupo de estudiantes, de investigadores de esta universidad, de este instituto, después del temblor de 2017, de desarrollar un proyecto colaborativo con la Universidad de Texas en Austin para poder hacer un recorrido, una recopilación de datos que no hemos subido a Design Safe todavía, Ellen, pero que están dispuestos para poder hacer un análisis del comportamiento de edificios que en su momento se dañaron y posteriormente fueron rehabilitados, al tiempo que nuestros colegas de la Universidad de Texas en Austin hacían lo propio con algunos edificios en el estado de California, como un ejemplo de carácter colaborativo. Debo decir que Design Safe está abierto a todo el mundo, no es una plataforma que está ubicada en la nube encima del estado de Texas, digamos, pero es una plataforma que está abierta a todo el mundo y no tiene que ser un investigador de los Estados Unidos. Nos acompaña, pero hace ratito estaba por aquí la ingeniera Diana Ramírez, quien como parte de sus trabajos de licenciatura desarrolló una base de datos de edificios de mampostería y de diferentes técnicas de rehabilitación de estructuras de mampostería, base de datos que está en Design Safe disponible para quien lo quiera utilizar. Y me parece que hace todo el sentido del mundo en que podamos apoyarnos en las capacidades que uno u otro país ha construido. En un contexto global complejo, este tipo de liderazgo al que yo me refería, abierto, generoso y con visión de largo plazo, es exactamente el que necesitamos. Un par de ejemplos son su claro liderazgo en el Comité de Temas Internacionales de la APLU, que él mismo mencionaba en su última lámina o penúltima lámina, así como su apoyo a la iniciativa de incorporar a la ciencia, la tecnología, la innovación y la educación superior en el logro de una mayor competitividad regional, tal que se incorpore dentro del Tratado México-Estados Unidos-Canadá, versión 2, cuya revisión apenas inicia. Muy estimado Taylor, gracias por tu cercanía y por tu apertura, por tu compromiso con una visión compartida de la educación superior. Hago votos porque tu participación en la academia sea activa y fructífera. Estamos seguros que tus ideas y liderazgo contribuirán significativamente al desarrollo de nuestra ingeniería. Recibe mi más cordial bienvenida. Muchas felicidades por este merecido reconocimiento. Muchas gracias.
Gracias por sus valiosos comentarios, doctor Sergio Alcocer Martínez de Castro. Enseguida le doy la palabra al doctor José Luis Fernández Sayas, expresidente de la Academia y titular de la Comisión de Especialidad de Mecánica y Mecatrónica.
Muchas gracias, maestro Alberto Lepe Zúñiga, presidente de la Academia de Ingeniería, distinguidos miembros de esta mesa, todos de la Academia, distinguida audiencia que nos acompaña. Debo explicar primero que quien me entrenó para participar en estas celebraciones es un ingeniero, miembro de la Academia, de la Comisión de Energía Nuclear, que se llama JoAnn P. Y él me convenció de que para que pudiera yo hablar con claridad, dado que soy tartamudo, debería tener mucha claridad el texto que voy a leer y no leerlo sino memorizarlo. Entonces, si cometo algún error, avísenme para que corrija el texto que le debo entregar a la Academia. Yo quiero felicitarme por participar en esta última, la quinta presentación de un brillantísimo nuevo miembro correspondiente de la Academia, también de la Universidad de Texas, no de la Universidad de Texas con la que yo trabajo, que está en Austin, sino la Universidad de Texas, que ahora trabajan los estructuristas, porque no soy ingeniero civil, lamentablemente, unos creen que yo soy perfecto, ¿no? Pero yo creo que es muy importante lo que han dicho quienes me han precedido en la palabra. En particular, aplaudo la buena disposición y dirección en que introdujo el tema el profesor E, que en una versión que me tocó leer, que es anterior a la que nos presentó el día de hoy, hacía menos énfasis en la total percepción de éxito de la triple hélice como una consecuencia de una política de un país desarrollado que cuida a su gente, que cuida a su economía, cuida su cultura y por lo tanto a sus universidades. Ese país empuja de manera muy decisiva la triple hélice, partiendo de la suposición de que todo el mundo entiende que la triple hélice está populada por individuos que quieren mejorar sin violar la ley. En el caso de México eso no se da. Y yo quiero felicitar en primer lugar, lo voy a hacer varias veces si me permiten, al profesor E porque nos da terminología nueva para hablar del mismo asunto, pero de una manera mucho más relevante a la realidad mexicana. A mí me ha tocado, por muchas razones que no quiero recordar, me ha tocado enfrentar a individuos que condenan la situación política de México. Me tocó en los años 70, por ejemplo. México, a diferencia de los Estados Unidos, ha demostrado que se pueden hacer muchas cosas sin que nos muramos de hambre. Por ejemplo, quebrar cabalmente la economía nacional, ¿no? Nosotros lo logramos a finales de los años 70, principios de los años 80, unos 10 años o 12 después, también lo logramos, donde quebrar significa tener tantos compromisos de gasto que exceden de tal manera las expectativas de ingreso nacional, que se publican, por cierto, que por lo tanto disminuyen el acceso al crédito y de esta manera no hay forma de satisfacer las necesidades de los sectores educativo, de salud y de muchas otras estructuras que nos permiten combatir la pobreza. El resultado neto en esta comparación entre las tres naciones del tratado que ahora están platicando es que México se mantiene muy pobre y que con todo y todo algo ha mejorado, la pobreza extrema, pero no hemos resuelto el problema fundamental porque no hemos entendido que nos toca a nosotros hacerlo. Y a nosotros nos toca mucho en la Academia de Ingeniería y nos toca mucho en la Universidad Nacional. Esta es una tarea para la gente educada, esta es una tarea que sin que lo haya dicho en esas palabras el profesor E, pertenece a una de las hélices, que es el de la academia, el de las universidades, de la gente que tiene el privilegio de hacer investigación, leer en diferentes idiomas, hablar con gente culta como ustedes, educar a los muchachos, ayudarlos a que hagan su posgrado de la manera más exitosa posible y luego contribuir a que haya esas estructuras productivas que permitan que los jóvenes se eduquen para hacer más valor, para hacer mejor la economía nacional, que de esta manera les da mejores ingresos, mejor nivel de vida y por supuesto pagan más impuestos. Yo creo que todo eso estaba en la mente de quienes produjeron y propusieron hace probablemente 30 años o 35 este modelo de la triple hélice, que ha sido también empujado por las universidades, el gobierno y las organizaciones en Estados Unidos. Aquí la gente o tiene prohibido, si trabaja yo trabajé en el gobierno, uno trabaja en el gobierno, le prohíben hablar de ciertas cosas que no son populares con el partido en el poder. Y eso es tremendamente desdichado, porque el partido que sea en el poder, ya he trabajado yo con 5 partidos en el poder, los partidos cambian de idea y como no son muy hábiles para poder interpretar esta idea de la colaboración entre las hélices, lo que hacen es ignorar una muy buena parte. Esto lo vimos al principio de esta administración, que está presidido por una egresada del Instituto de Ingeniería con el doctorado en Planeación Energética de la UNAM. O sea, la culpa no la tiene ella, la culpa la tienen ustedes, la tienen los mexicanos. Y yo creo que eso es algo que podemos resolver y el profesor Egmi nos ayuda a ver cómo, cambiando la terminología, dejamos atrás la pugna política, las rencillas sociales, el celo que les hace a algunos de ustedes preferir al Cruz Azul en vez de los Pumas, por ejemplo, y no hablan de fútbol como debieran, ¿no? Y yo creo que esa es una cosa que nos cuesta mucho trabajo entender y que podemos, con el liderazgo y la ayuda de la Academia de Ingeniería, ahora celebrando los 70 años del Instituto de Ingeniería, que es muy importante que se unan estas dos instituciones para procurar este cambio de discurso, este cambio de lenguaje y avanzar en la construcción de lo que en alguna de las versiones del profesor Egmi se llamó la cuarta hélice, la de la fuerza de trabajo. ¿Por qué queremos que los jóvenes salgan mejor capacitados? Para que tengan oportunidades de desempeñarse en la fuerza de trabajo, para que puedan tener actividades económicas bien remuneradas, para que tengan cómo pasar el día sin andar pensando en cómo violar la ley, cómo poder satisfacer sus necesidades sociales, de tiempo, económicas, de alimento, de salud, de su familia, sin pensar en las opciones ilegales, que por cierto son gigantescas en este país. Somos un país exportador de fentanilo de primera orden mundial. Y eso ya lo hemos demostrado y no es satisfactorio. No es satisfactorio que nuestros muchachos tengan esa como principal meta atractiva para su desarrollo. Yo quisiera terminar felicitándome y agradeciendo a la Academia esta oportunidad de recomendar la lectura en extenso de la propuesta del profesor Egmi, que tiene mucho detalle de lo que yo rápidamente mencioné como cambio de lenguaje. Yo creo que esto es una cosa que en Estados Unidos no hace falta. En Estados Unidos decimos que trabajamos para mejorar la economía o trabajamos para mejorar la seguridad o trabajamos para mejorar la salud, y ese trabajamos es una primera persona del plural que nos agrupa a todos, de todos los colores, de todas las tradiciones. En el caso de Texas hay muchos mexicanos, ¿no? O sea que no tenemos problema. En el caso de la situación mexicana es completamente diferente. Pareciera que, aunque utilicemos las mismas palabras que utilizan los grandes políticos mexicanos, pareciera que estamos o haciendo burla de ellos o que les estamos haciendo una reclamación que no está bienvenida. Yo creo que lo que hay que hacer es procurar traducir al español la ponencia, la propuesta, el artículo y el trabajo del profesor Egmi, que es espléndido, es excelente. Yo soy de los que opinaron que no había que hacerle ningún cambio, pero que si está en español probablemente tendrá mejores lectores entre las gentes que toman decisiones, tanto en el sector privado como en el sector público. Hay otros que no saben leer ningún idioma, pues esos no los podemos hacer, habremos de hablar con ellos. Y yo me felicito por esta oportunidad, agradezco a mi academia que me haya distinguido con esta manera de apreciar con detalle la obra, que por cierto está muy bien publicada, la del profesor Egmi. Eso demuestra esa ventaja de un currículum multidisciplinario, una formación científica sumamente sólida, de acuerdo con la mejor tradición decimonónica británica. Es un doctor en ciencias. Es un señor que habla de ingeniería con una enorme autoridad moral por los mismos antecedentes que él tuvo en diferentes organizaciones que buscan resolver problemas, que es lo que hacemos los ingenieros. Algunos ingenieros tenemos formación científica, pero eso no nos hace científicos de tiempo completo, nos permite participar de manera más exitosa en la formación de nuevos conocimientos cuando son necesarios. Y la tercera cosa que el profesor Egmi tiene muy clara, que yo felicito y quisiera que todos imitáramos, es esa voluntad por participar en la formación de gente joven, y no tan joven, que empuje la economía, que unifique las capacidades de los sectores productivo, académico, industrial y desde luego social, para que el país siga creciendo. El profesor Egmi habló con mucha precisión de estos programas muy antiguos y otros mucho más novedosos que están caminando por la triple hélice, y yo diría sin duda por la cuarta hélice que el día de hoy no comentó, pero que yo la tengo muy presente, que es la capacitación para que la gente participe en una nueva forma, en la creación de una economía que como nos hace falta que se desarrolle. Muchas felicidades al profesor Egmi por esta oportunidad de darnos una clase magistral que no es nada más la que para los que estamos aquí presentes, porque se está transmitiendo, se graba y luego lo oyen en otros círculos y resulta en un beneficio de cientos de gentes, pero también esta es una oportunidad para felicitar a mi academia del magnífico tino para poder invitar a estos 5 brillantes expositores. Yo en la mañana, por cierto, en la presentación del profesor Arturo Schultz, encontré una cosa que no sabía que existía, y era que un juego de datos experimentales de la resistencia de la mampostería postensada, que no habían sido validados, al ser correlacionados exitosamente con un modelo matemático, dijo él que daban validados. Esa es una forma de ver las cosas de manera diferente, pero esa es una forma justa. Muchas gracias, señor presidente. Muchas gracias, doctor profesor.
Gracias, doctor José Luis Fernández Sayas, siempre interesante e importante escucharlo. Y para qué decir lo que todos sabemos, ¿no? Le vamos a dar ahora la palabra al doctor Jaime Parada Ávila, que es expresidente también de la Academia y titular de la Comisión de Especialidad de Ingeniería Industrial. Adelante, don Jaime Parada.
Muchas gracias. Saludo con gran gusto al presidente de nuestra Academia de Ingeniería, don Alberto Lepe. Un gran abrazo a todos nuestros académicos, en especial de la Comisión de Ingeniería Civil, y desde luego, pues una entusiasta bienvenida a un distinguido académico, funcionario, investigador, formador de gente calificada como es el doctor Taylor E. Su trabajo de ingreso a la Academia de Ingeniería es un documento notable, déjenme decirlo, donde se resalta el importante papel que tienen las universidades, gobierno, empresas y sociedad en la creación de ecosistemas regionales para impulsar la innovación, la economía basada en el conocimiento y la generación de empleos de calidad. Su vasta experiencia como académico, investigador, funcionario y actualmente como presidente de la Universidad de Texas, con sede en San Antonio, lo acredita sobradamente para darle la más calurosa bienvenida a nuestra Academia de Ingeniería de México. Quiero hacer algunos comentarios sobre el valioso documento de ingreso del doctor Iwi, basado en la experiencia de 3 casos donde estuvo directamente involucrado la producción de energía a partir del viento, la producción de materiales especiales y la manufactura avanzada. En primer lugar, destaco el importantísimo papel del gobierno, que es destinar recursos fiscales del gobierno a la ciencia, tecnología e innovación, que es absolutamente relevante para la competitividad de un país. En el caso de Estados Unidos, se destina el 3.4% del Producto Interno Bruto a estos temas, de los mayores a nivel mundial, sin lugar a dudas. De esta cifra corresponde al gobierno el 25% aproximadamente y el 75% a empresas y organizaciones de la sociedad civil y filantropía. El gasto gubernamental lo hace Estados Unidos a través de múltiples agencias como la National Science Foundation, las secretarías de gobierno federal, los laboratorios nacionales y los gobiernos de los estados. El doctor Iwi destaca el papel relevante en los casos que le tocó vivir, la participación de agencias gubernamentales como la National Science Foundation, el Departamento de Energía, el Departamento de Investigación para la Defensa y otras, donde los recursos gubernamentales jugaron un importante papel en la investigación de frontera, el desarrollo de aplicaciones para la industria y la formación de recursos humanos especializados. Segundo, el papel de la academia, muy relevante. El documento destaca la importancia estratégica de las universidades en la creación de comunidades o distritos de innovación, destacando sus experiencias de Texas y de Tennessee. El compromiso de una universidad con la excelencia académica, la investigación de frontera, el desarrollo tecnológico y la colaboración con las empresas del sector productivo es de fundamental importancia. Señala que las universidades de investigación son aquellas con un claro propósito de destinar recursos a la investigación y a la formación de posgrados en las áreas STEM, de ciencia, tecnología, ingeniería y matemáticas. Tercero, el papel de las empresas y de la filantropía. El papel relevante de las empresas queda muy claro en el documento, destacando que la única posibilidad que trascienda al mundo real de la creación de valor económico y la generación de buenos empleos es el involucramiento temprano de las empresas. Transformar las investigaciones y artículos científicos en patentes de nuevos productos y procesos es la clave para generar impactos de alto valor estratégico. En Estados Unidos, las empresas tienen una clara visión de la importancia de innovar. Ya he mencionado que se invierte el 3.4% y de esta cifra el 70% lo hacen las empresas del sector privado en aquel país. También el 5% proviene de organizaciones civiles de filantropía que apoyan la causa de la investigación, el emprendimiento, la formación de capital humano y otros temas. Cuarto, el territorio y las comunidades para generar distritos de innovación. El trabajo del doctor Igmi destaca la importancia de generar en las ciudades, distritos o comunidades de innovación, donde de manera conjunta el gobierno, las universidades, los centros de investigación, las empresas, emprendedores y los estudiantes colaboran en temas y proyectos de interés colectivo para impulsar la economía y sociedad basada en el conocimiento. Hay claros ejemplos en Estados Unidos y otros países de estos polos de innovación. Boston, Austin, San Francisco, el Valle del Silicio, Seattle, Carolina del Norte, Raleigh, Durham y otras zonas, donde la sociedad en su conjunto se compromete y participa activamente para que la formación de talento, la investigación, la innovación y el emprendimiento genere bienestar para toda la comunidad. Quinto, los retos para México y la cooperación con Estados Unidos. Finalmente, quiero compartir con ustedes que celebro enormemente el ingreso del doctor Taylor Ibmi a la Academia de Ingeniería. Estoy seguro que sin duda él y otros colegas de Estados Unidos y Canadá serán un natural enlace y puente para convertir la región de Norteamérica en la más competitiva e innovadora a partir de la cooperación de los tres países. Doy a continuación los argumentos para esto. México, Estados Unidos y Canadá han acumulado experiencias positivas a partir de 1984 con el libre comercio, así como en otras áreas, seguridad, migración, medio ambiente y otros temas. El total de las exportaciones de bienes de los tres países en la zona de Norteamérica sumó para el año 2024 un total de 1.630 miles de millones de dólares. De esto, el 42% corresponde a Estados Unidos, el 32% a Canadá y una porción significativa, desde luego, a nuestro vecino país del norte. Es importante mencionar que el avance económico de China, con un PIB que tiene 18.750 miles de millones de dólares y exportaciones al mundo de 3.580 miles de millones de dólares, que es el 19% de su Producto Interno Bruto, así como el progreso tecnológico de los últimos años, representa un reto a la competitividad de Norteamérica. De las 20 millones de patentes vigentes en el mundo, más del 25% pertenecen a China, 18% a Estados Unidos, 12% Japón y 45% restante a otros países. De las 3.4 millones de solicitudes de patentes en 2024, el 50% pertenecen a China, 14 a Estados Unidos, 12 a Japón y el 24 a otros países. El desarrollo de nuevos productos y servicios para ser fabricados en Estados Unidos, Canadá o México y sustituir a las provenientes de Asia es una gran área de oportunidad para las empresas de la región de Norteamérica. Además de contar con abundancia y diversidad de recursos naturales, los tres países integramos un PIB conjunto de 33.300 miles de millones de dólares, versus la Unión Europea con 19.4, China 18.7. La región de Norteamérica, por lo tanto, tiene un poderoso mercado de consumo de más de 500 millones de personas. Hay otros países como India con 1.463 millones, China 1.400, la Unión Europea 450, Brasil 212, Rusia 144. Contamos con 27 millones de jóvenes en educación superior, 70% Estados Unidos, 23% México y 7% Canadá. Sin embargo, para aprovechar la oportunidad que ofrece la integración de Norteamérica, se tienen que resolver las grandes disparidades de la región, para que ese 3.4% del Producto Interno Bruto que invierte Estados Unidos en investigación e innovación, el 2.2% de Canadá y la baja cifra de 0.3% de México, tiene que cambiar en los próximos años. Es decir, el reto que tiene México es multiplicar por 10 justamente lo que estamos invirtiendo en ciencia, tecnología e innovación. Además de los esfuerzos que hagan por su cuenta los tres países, es pertinente pensar en nuevos instrumentos para incorporar mecanismos trilaterales que permitan fomentar esfuerzos conjuntos de los tres países. Deberíamos tomar la experiencia y lecciones aprendidas del fondo y programa Horizons, que ya fue mencionado por el doctor Taylor Ewey, que apoyan de manera compartida a los países de la Unión Europea para proyectos de ciencia, tecnología e innovación desde el año 1984 y con un presupuesto que rebasa los 75.000 millones de euros. Esto es una gran oportunidad, queridos colegas, poner, ahora que se están iniciando las negociaciones del TECMEC, la renovación del Tratado de Libre Comercio entre los tres países, que podamos incorporar en la agenda de cooperación la educación superior, la ciencia, la tecnología y la innovación, y que pensemos en instrumentos que le den vida a esa intención política para convertir a Norteamérica en una de las regiones más innovadoras del mundo. Con esto termina mi comentario al espléndido trabajo del doctor Taylor Ewing y le doy la más calurosa bienvenida. Estoy seguro, doctor Ewing, que con su gran poder de convocatoria, su amplia disposición para estrechar los lazos con México y Canadá, sea un puente natural para que esta idea la podamos sembrar en las próximas conversaciones que comienzan justamente en este primer semestre del año entre Canadá, Estados Unidos y México. Le doy la más calurosa bienvenida a la Academia de Ingeniería y es un gran honor recibirlo con nosotros. Muchísimas gracias.
Muchas gracias al doctor Jaime Parada Ávila por sus datos y sus consejos. Vamos a tomar unos 5 minutos porque queremos arreglar las mesas de distinta manera para ya otorgar el reconocimiento, diploma, medalla e insignia a nuestros nuevos académicos. Pueden estirar las piernas. La foto primero.
Se la sabe, es la última. Ya se la sabe. Sí, sí.
¿De quién es?
Así le vamos a dejar. Todavía no le vamos a dejar.
Best wishes. Many thanks for your gift. Thank you very much.
Hold on, water.
Ya, querido, por favor.
Gracias.
Sí, nos van a ayudar ahorita para hacer la cuestión. No te preocupes.
Nada más deja uno por mesa.
Adolfo, you have to stand.
There's a chair in the corner. Oh, they took it.
They have the same problem. Falta una silla.
Quiero que te sientes también. Esa cosa que te dejen sin silla.
Ah, ahí está. Dice Ellen que arriba hay sillas.
Already have it. Now we have more chairs. Now we have more chairs.
No, they're all there.
Bien, pues vamos a continuar. Pues qué mejor que ahora sigue el darle la bienvenida a nuestros nuevos académicos y qué mejor que lo haga el doctor Sergio Alcocer Martínez de Castro, desde luego por su desempeño, por su bonomía en el presente acto, y le solicito que en nombre de la academia pues le dé las buenas nuevas y las nuevas y la bienvenida a nuestros nuevos académicos. Es que no.
Muchas gracias, señor presidente. A nombre de la Academia de Ingeniería y del mío propio, con gran satisfacción y orgullo, les doy la bienvenida a la Academia de Ingeniería de México, a las doctoras JoAnn Browning y Ellen Radji, así como los doctores Arturo Schultz, Adolfo Matamoros y Taylor Egme, todos nuevos miembros de la Comisión de Especialidad en Ingeniería Civil, teniendo además, en función de lo que establece nuestro estatuto, el derecho de pertenecer a otra comisión de especialidad, siempre y cuando se comprometan a colaborar también en ella. Nuestra academia se verá sin duda enriquecida con el ingreso de todas y todos ustedes, que son personas valiosas para el logro de sus objetivos. Es importante recordarles que, como lo señala nuestro estatuto, el reconocimiento que hoy reciben de la Academia de Ingeniería por sus méritos personales trae consigo compromisos y responsabilidades, por lo que los invitamos a involucrarse en las actividades de la academia con el dinamismo, entusiasmo y profesionalismo que les son característicos. Por todo lo anterior, la Comisión de Especialidad en Ingeniería Civil, de la que formo parte, se felicita por su ingreso, siendo para mí un honor reiterarles la más efusiva bienvenida. Muchas gracias.
Muchas gracias, maestro y doctor Sergio Alcocer Martínez de Castro. Pues llegamos a la parte más simbólica de este acto. Procederemos a la entrega de la medalla, la insignia y el diploma a nuestros nuevos académicos, a quienes les iré nombrando para que pasen aquí al frente, y solicito a nuestro presidente, vicepresidente, futuro presidente también, a Guillermo Aguirre Esponda, me asista en ello. Pues en el orden en que desarrollamos este acto, primeramente requiero que el doctor Arturo E. Schultz el doctor Aguirre le medalla y insignia, y yo leeré el texto del diploma que lo acredita como académico en la Bien, pues para no repetir todos los diplomas, leeré el detalle del primero de ellos, donde la Academia de Ingeniería México, en atención a sus conocimientos científicos y a la obra que ha desarrollado en favor de la ingeniería, designa al doctor Arturo E. Schultz, individuo suyo en la clase de académico correspondiente de la Comisión de Especialidad en Ingeniería Civil, y para constancia le otorga el presente diploma en la Ciudad de México a 24 de marzo del 2026. Suscriben el doctor Nahum Hamed García Villanueva, presidente de la Comisión de Especialidad en Ingeniería Civil, el doctor Guillermo José Aguirre Esponda, vicepresidente, y el maestro Alberto Lepe Zúñiga, presidente, su servidor. Bienvenido a la Academia. De una vez. Bueno, ahora el doctor Adolfo Matamoros Hidalgo. Es ingeniero mecánico, es que no nos debemos de preocupar. Sí, es mecánico. Bien, y el diploma, pues, que establece lo mismo, se le otorga al doctor Adolfo B. Matamoros Hidalgo. Así que un aplauso y bienvenido. Bien, pues ya. Ay, que es en la otra hoja. Ya sabe JoAnn Browning que le toca. Bien, y igual el diploma que le otorga la Academia a la doctora JoAnn P. Browning para que se ostente como miembro de esta bella organización. La doctora Ellen Rachi. Este es el diploma que le da a la Academia la doctora Ellen M. Rachi como nueva académica en la especialidad de Ingeniería Civil. Y ahora al doctor Taylor Amy. Bien, y para recordar lo que este diploma dice, voy a leerlo todo. Miren, la Academia de Ingeniería México en atención a sus conocimientos científicos y a la obra que ha desarrollado en favor de la ingeniería, designa al doctor Taylor Amy, individuo suyo en la clase de académico correspondiente de la Comisión de Especialidad en Ingeniería Civil, y para constancia le otorga el presente diploma en la Ciudad de México. El 24 de marzo del 2026 suscriben el doctor Nahum Hamed García Villanueva, que es el presidente de la Comisión de Especialidad en Ingeniería Civil, el doctor Guillermo José Aguirre Esponda, vicepresidente, y el maestro Alberto Lepe Zúñiga, su servidor, presidente. Bienvenido. Doctor Taylor. Okay. Oh, thank you. Why? Well, in a moment, I see what is. Bien, ya como clausura de este evento, después de la exposición que nos ofrecieron tan distinguidas y distinguidos doctores, les expreso que es para mí motivo de orgullo darles la más cordial bienvenida al seno de nuestra organización como académicos correspondientes de la Comisión de Especialidad en Ingeniería Civil. Con su ingreso, nuestra organización se fortalece, ya que sus conocimientos, habilidades, experiencia y capacidad acumulados a lo largo de los años nos ayudarán a contribuir de manera activa y decidida con soluciones a los grandes desafíos y problemas que nos plantea este siglo, donde los avances científicos y tecnológicos de la ingeniería en sus muy diversos campos nos ofrecen ventajas y altos estándares para procurar mayor bienestar para todos, aunque la academia reconoce también la complejidad social, administrativa y política que muchas veces se presenta para lograrlo. La Academia de Ingeniería siempre se distinguirá por ser una organización de profesionales con compromiso social, conscientes del papel de la educación, la ciencia, la tecnología y la innovación para lograr la equidad y mitigar las crecientes asimetrías en el desarrollo de nuestro país. Debemos emplear el conocimiento y el entusiasmo de nuestras académicas y nuestros académicos para fortalecer esta organización y lograr que sea una referencia obligada en la toma de decisiones de nuestros gobernantes, legisladores y la sociedad que permita la buena marcha de la nación. Por todo lo anterior, la Academia de Ingeniería se felicita por el ingreso de todas y todos ustedes. Les reiteré la más efusiva bienvenida con la que damos por concluida esta ceremonia protocolaria de ingreso. Agradezco a quienes nos acompañaron, a los académicos que comentaron este trabajo de ingresos, a quienes participaron de manera presencial y por transmisión. Su tiempo e interés enaltecieron este evento. Señoras académicas, señores académicos, ingenieras e ingenieros, señoras y señores, que tengan muy buena noche.
Rápidamente dos anuncios, si me permite. Nada más mencionar que llegamos a tener 430 personas conectadas por internet, 370 en el Instituto de la serie de la redes del instituto y 60 de la academia, sus 430 digamos en el pico máximo. Pues no sé si es récord Guinness, pero cercano. Y vamos a tener enseguida la firma de un convenio de colaboración entre la Universidad de Texas en San Antonio y el Instituto de Ingeniería, para lo cual nos acompaña nuestra directora. Entonces, estaría presentada en mi lugar, en fin, para que pueda dar unas palabras, y si el doctor Amy igualmente, para que se pueda hacer la firma del convenio de una manera simbólica con el testigo de todos ustedes. Muchas gracias. Ah, sí, claro.
I think it'll look good with all of our medals.
Medals
showing.
Yeah. You look like Pete.
What?
You look like Pete.
That's nice.
Es
Taylor, Amy, it's a pleasure. Yeah, thank you for the opportunity to do this with you. We have very, very strong bonds. And the fact that we can do this in the engineering realm is really, really important. I'm going to sit here and sign. Okay, shall we?
No sé si hablen. A ver si pintan porque son abajo.